Chemistry deals with varieties of matter and change of one kind of matter into the other. Transformation of matter from one kind into another occurs through the various types of reactions. One important category of such reactions is redox reactions. A number of phenomena, both physical as well as biological, are concerned with redox reactions. These reactions find extensive use in pharmaceutical, biological, industrial, metallurgical and agricultural areas. The importance of these reactions is apparent from the fact that burning of different types of fuels for obtaining energy for domestic transport and other commercial purposes, electrochemical processes for extraction of highly reactive metals and nonmetals, manufacturing of chemical compounds like caustic soda, operation of dry and wet batteries and corrosion of metals fall within the purview of redox processes. Of late, environmental issues like hydrogen economy, use of liquid hydrogen as fuel and development of ozone hole have started figuring under redox phenomenon. 8.1 Classical idea of redox reactions. Oxidation and reduction reactions. Originally, the term oxidation was used to describe the addition of oxygen to an element or a compound. Because of the presence of dioxygen in the atmosphere, many elements combine with it, and this is the principal reason why they commonly occur on the Earth in the form of their oxides. The following reactions represent oxidation processes according to the limited definition of oxidation: 2 mg SO2G 2 mgOS 8.1 SSO2G SO2G 8.2. After studying this unit, you will be able to identify redox reactions as a class of reactions in which oxidation and reduction reactions occur simultaneously. Define the terms oxidation, reduction, oxidant oxidizing agent and reductant reducing agent. Explain mechanism of redox reactions by electron transfer process. Use the concept of oxidation number to identify oxidant and reductant in a reaction. Classify redox reaction into combination synthesis, decomposition, displacement and disproportionation reactions. Suggest a comparative order among various reductants and oxidants. Balance chemical equations using I-oxidation number 2 half reaction method. Learn the concept of redox reactions in terms of electrode processes. Unit 8 Redox reactions. Where there is oxidation, there is always reduction. Chemistry is essentially a study of redox systems. 264 Chemistry and reactions. 8.1 and 8.2. The elements magnesium and sulfur are oxidized on account of addition of oxygen to them. Similarly, methane is oxidized owing to the addition of oxygen to it. CH4G2O2GCO2G2H2OL. 8.3 A careful examination of reaction 8.3 inches which hydrogen has been replaced by oxygen prompted chemists to reinterpret oxidation in terms of removal of hydrogen from it, and, therefore, the scope of term oxidation was broadened to include the removal of hydrogen from a substance. The following illustration is another reaction where removal of hydrogen can also be cited as an oxidation reaction. 2H2SGO2G2SS2H2OL. 8. For his knowledge of chemists grew, it was natural to extend the term oxidation for reactions similar to 8.1 to 8.4, which do not involve oxygen but other electronegative elements. The oxidation of magnesium with fluorine, chlorine and sulfur etc. occurs according to the following reactions: MgSF2G MgF2S 8.5 mg SCl2G MgCl2S 8.6 mg SSS MgSS 8.7. Incorporating the reactions 8.5 to 8.7 within the fold of oxidation reactions encouraged chemists to consider not only the removal of hydrogen as oxidation, but also the removal of electropositive elements as oxidation. Thus the reaction 2K4FeCN6Ac2O2Ac2K3FeCN6Ac2CoAc is interpreted as oxidation due to the removal of electropositive element potassium from potassium ferrocyanide before it changes to potassium ferrocyanide. To summarize, the term oxidation is defined as the addition of oxygen electronegative element to a substance or removal of hydrogen electropositive element from a substance. In the beginning, reduction was considered as removal of oxygen from a compound. However, the term reduction has been broadened these days to include removal of oxygen electronegative element from a substance or addition of hydrogen electropositive element to a substance. According to the definition given above, the following are the examples of reduction processes: 2HGOS 2HGLO2G 8.8 removal of oxygen from mercuric oxide 2FeCl3Ac H2G 2FeCl2Ac 2HCl Ac 8.9 removal of electronegative element chlorine from ferric chloride CH2CH2GH2GH3C CH3G 8.10 addition of hydrogen 2HgCl2Ac SnCl2Ac Hg2Cl2S SnCl4Ac 8.11 addition of mercury to mercuric chloride in reaction 8.11 simultaneous oxidation of stannous chloride to stannic chloride is also occurring because of the addition of electronegative element chlorine to it. It was soon realized that oxidation and reduction always occur simultaneously, as will be apparent by re-examining all the equations given above. Hence, the word redox was coined for this class of chemical reactions. Problem 8.1 in the reactions given below. Identify the species undergoing oxidation and reduction. IH2SgCl2G2HCl2Fe3O4S8Ls9Fe4Al2O3S32Na SH2G2Na solution. IH2S is oxidized because a more electronegative element, chlorine, is added to hydrogen, or a more electropositive element, hydrogen, has been removed from S. Chlorine is reduced due to addition of hydrogen to it. 2. Aluminium is oxidized because oxygen is added to it. Ferrous oxide. 265 Redox reactions. Fe3O4 is reduced because oxygen has been removed from it. 3. With the careful application of the concept of electronegativity only, we may infer that sodium is oxidized and hydrogen is reduced. Reaction 3 chosen here prompts us to think in terms of another way to define redox reactions. 8.2 Redox reactions in terms of electron transfer reactions. We have already learnt that the reactions 2 Na SCl2G2 Na ClS 8.124 Na SO2G2 Na 2OS 8.132 Na SSS Na 2SS 8.14 are redox reactions because in each of these reactions sodium is oxidized due to the addition of either oxygen or more electronegative element to sodium. Simultaneously, chlorine, oxygen and sulfur are reduced because to each of these, the electropositive element sodium has been added. From our knowledge of chemical bonding, we also know that sodium chloride, sodium oxide and sodium sulfate are ionic compounds, and perhaps better written as NaClS, Na2O2S, and Na2S2S. Development of charges on the species produced suggests us to rewrite the reactions 8.12 to 8.14 in the following manner, for convenience. Each of the above processes can be considered as two separate steps, one involving the loss of electrons and the other the gain of electrons. As an illustration, we may further elaborate one of these, say, the formation of sodium chloride. 2 Na S2 Na G2ECl2G2E2Clg. Each of the above steps is called a half reaction, which explicitly shows involvement of electrons. Sum of the half reactions gives the overall reaction. 2 Na SCl2G2 Na ClS or 2 NaClS. Reactions 8.12 to 8.14 suggest that half reactions that involve loss of electrons are called oxidation reactions. Similarly, the half reactions that involve gain of electrons are called reduction reactions. It may not be out of context to mention here that the new way of defining oxidation and reduction has been achieved only by establishing a correlation between the behavior of species as per the classical idea and their interplay in electron transfer change. In reactions 8.12 to 8.14, sodium, which is oxidized, acts as a reducing agent because it donates electron to each of the elements interacting with it and thus helps in reducing them. Chlorine, oxygen and sulfur are reduced and act as oxidizing agents because these accept electrons from sodium. To summarize, we may mention that oxidation, loss of electron S by any species, reduction, gain of electron S by any species. Oxidizing agent, acceptor of electron S, reducing agent, donor of electron S. Problem 8.2 justify that the reaction 2 Na SH2G2 Na S is a redox change. Solution. Since in the above reaction the compound formed is an ionic compound, which may also be represented as NaHS. This suggests that one half reaction in this process is 2 Na S2 Na G2E. 266 Chemistry. In the other half reaction is H2G2E2Hg. This splitting of the reaction under examination into two half reactions automatically reveals that here sodium is oxidized and hydrogen is reduced, therefore, the complete reaction is a redox change. 8.2. 1 Competitive electron transfer reactions. Place a strip of metallic zinc in an aqueous solution of copper nitrate as shown in Fig. 8.1. For about 1 hour, you may notice that the strip becomes coated with reddish metallic copper and the blue color of the solution disappears. Formation of Cn2 ions among the products can easily be judged when the blue color of the solution due to Cu2 has disappeared. If hydrogen sulfide gases pass through the colorless solution containing Zn2 ions, appearance of white zinc sulfide, ZnS, can be seen on making the solution alkaline with ammonia. The reaction between metallic zinc and the aqueous solution of copper nitrate is ZnS Cu2 Zn2 Aqueous 8.15 in reaction 8.15. Zinc has lost electrons to form Zn2N, therefore, zinc is oxidized. Evidently, now if zinc is oxidized, releasing electrons, something must be reduced, accepting the electrons lost by zinc. Copper ion is reduced by gaining electrons from the zinc. Reaction 8.15 may be rewritten as, at this stage we may investigate the state of equilibrium for the reaction represented by equation 8.15. For this purpose, let us place a strip of metallic copper in a zinc sulfate solution. No visible reaction is noticed and attempt to detect the presence of Cu2 ions by passing H2S gas through the solution to produce the black color of cupric sulfide. COS does not succeed. Cupric sulfate has such a low solubility that this is an extremely sensitive test, yet the amount of Cu2 formed cannot be detected. We thus conclude that the state of equilibrium for the reaction 8.15 greatly favors the products over the reactants. Let us extend electron transfer reaction now to copper metal and silver nitrate solution in water and arrange a setup as shown in Fig. 8.2. The solution develops blue color due to the formation of Cu2 ions on account of the reaction. Fig. 8.1 Redox reaction between zinc and aqueous solution of copper nitrate occurring in a beaker. 8.16 Here, Cu(S) is oxidized to Cu2Ag and Ag(Ag) is reduced to Ag(S). Equilibrium greatly favors the products Cu2Ag and Ag(S). By way of contrast, let us also compare the reaction of metallic cobalt placed in nickel sulfate solution. The reaction that occurs here is 8.17. 267 Redox reactions. Figure 8.2 Redox reaction between copper and aqueous solution of silver nitrate occurring in a beaker. At equilibrium, chemical tests reveal that both Ni2Ag and CO2Ag are present at moderate concentrations. In this case, neither the reactants CoS and Ni2Ag nor the products CO2Ag and Ni(S) are greatly favored. This competition for release of electrons incidentally reminds us of the competition for release of protons among acids. The similarity suggests that we might develop a table in which metals and their ions are listed on the basis of their tendency to release electrons, just as we do in the case of acids to indicate the strength of the acids. As a matter of fact, we have already made certain comparisons. By comparison, we have come to know that zinc releases electrons to copper and copper releases electrons to silver, and therefore, the electron-releasing tendency of the metals is in the order Zn, Cu, Ag. We would love to make our list more vast and design a metal activity series or electrochemical series. The competition for electrons between various metals helps us to design a class of cells, named as galvanic cells, in which the chemical reactions become the source of electrical energy. We would study more about these cells in Class 12. 8.3 Oxidation number. A less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction 2H2GO2G2H2OL. 8.18 Though not simple in its approach, yet we can visualize the H atom as going from a neutral zero state in H2 to a positive state in H2O. The O atom goes from a zero state in O2 to a negative state in H2O. It is assumed that there is an electron transfer from H2O and consequently H2 is oxidized and O2 is reduced. However, as we shall see later, the charge transfer is only partial and is perhaps better described as an electron shift rather than a complete loss of electron by H and gain by O. What has been said here with respect to equation 8.18 may be true for a good number of other reactions involving covalent compounds. Two such examples of this class of the reactions are H2SCl2G2HClG 8.19 and CH4G4Cl2GCCl4L4HClG 8.20. In order to keep track of electron shifts in chemical reactions involving formation of covalent compounds, a more practical method of using oxidation number has been developed. In this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. For example, we rewrite equations 8.18 to 8.20 to show charge on each of the atoms forming part of the reaction. 001-22H2GO2G2H2OL 8.210001-1H2SCl2G2HClG 8.21-4104-1CH4G4Cl2GCCl4L4HClG 8.23. It may be emphasized that the assumption of electron transfer is made for bookkeeping purpose only, and it will become obvious at a later stage in this unit that it leads to the simple description of redox reactions. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules formulated on the basis that 268 chemistry electron pair in a covalent bond belongs entirely to more electronegative element. It is not always possible to remember or make out easily in a compound ion which element is more electronegative than the other. Therefore, a set of rules has been formulated to determine the oxidation number of an element in a compound ion. If two or more than two atoms of an element are present in the molecule ion such as Na2S2O3Cr2072, the oxidation number of the atom of that element will then be the average of the oxidation number of all the atoms of that element. We may at this stage state the rules for the calculation of oxidation number. These rules are: 1. In elements, in the free or the uncombined state, each atom bears an oxidation number of 0. Evidently each atom in H2, O2, Cl2, O3, P4, S8, Na, Mg, Al has the oxidation number 0. 2. For ions composed of only one atom, the oxidation number is equal to the charge on the ion. Thus Na ion has an oxidation number of 1, Mg2 ion, 2, Fe3 ion, 3, Cl ion, -1, O2 ion, -2, and so on. In their compounds, all alkali metals have oxidation number of 1, and all alkaline earth metals have an oxidation number of 2. Aluminium is regarded to have an oxidation number of 3 in all its compounds 3. The oxidation number of oxygen in most compounds is -2. However, we come across two kinds of exceptions here. One arises in the case of peroxides and superoxides, the compounds of oxygen in which oxygen atoms are directly linked to each other. While in peroxides, e.g., H2O2, Na2O2, each oxygen atom is assigned an oxidation number of -1. In superoxides, e.g., KO2, RbO2, each oxygen atom is assigned an oxidation number of 1/2. The second exception appears rarely, that is when oxygen is bonded to fluorine. In such compounds, e.g., oxygen difluoride of 2 and dioxygen difluoride O2F2, the oxygen is assigned an oxidation number of 2 and 1, respectively. The number assigned to oxygen will depend upon the bonding state of oxygen, but this number would now be a positive figure only. 4. The oxidation number of hydrogen is 1, except when it is bonded to metals in binary compounds, that is, compounds containing 2 elements. For example, in Lin, Na, and Ca2, its oxidation number is -1, 5. In all its compounds, fluorine has an oxidation number of -1. Other halogens Cl, Br, and I also have an oxidation number of -1, when they occur as halide ions in their compounds. Chlorine, bromine and iodine, when combined with oxygen, for example in oxoacids and oxonions, have positive oxidation numbers. 6. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. In polyatomic ion, the algebraic sum of all the oxidation numbers of atoms of the ion must equal the charge on the ion. Thus, the sum of oxidation number of 3 oxygen atoms and 1 carbon atom in the carbonate ion, CO32, must equal -2. By the application of above rules, we can find out the oxidation number of the desired element in a molecule or in an ion. It is clear that the metallic elements have positive oxidation number and non-metallic elements have positive or negative oxidation number. The atoms of transition elements usually display several positive oxidation states. The highest oxidation number of a representative element is the group number for the first 2 groups and the group number -10 following the long form of periodic table for the other groups. Thus, it implies that the highest value of oxidation number exhibited by an atom of an element generally increases across the period in the periodic table. In the third period, the highest value of oxidation number changes from 1 to 7 as indicated below in the compounds of the elements. A term that is often used interchangeably with the oxidation number is the oxidation state. Thus in CO2, the oxidation state of carbon is 4, that is also its oxidation number, and similarly the oxidation state as well as oxidation number of oxygen is 2. This implies that the oxidation number denotes the oxidation state of an element in a compound. 269 Redox reactions. The oxidation number state of a metal in a compound is sometimes presented according to the notation given by German chemist, Alfred Stock. It is popularly known as Stock notation. According to this, the oxidation number is expressed by putting a Roman numeral representing the oxidation number in parenthesis after the symbol of the metal in the molecular formula. Thus Ors chloride and auric chloride are written as AuICl and Al3Cl3. Similarly, stannous chloride and stannic chloride are written as SN2Cl2 and SNIVCl4. This change in oxidation number implies change in oxidation state, which in turn helps to identify whether the species is present in oxidized form or reduced form. Thus, Hg2ICl2 is the reduced form of Hg2Cl2. Problem 8.3. Using Stock notation, represent the following compounds: HaCl4, Tl2O, FeO, Fe2O3, Qui, CuO, MnO and MnO2. Solution by applying various rules of calculating the oxidation number of the desired element in a compound. The oxidation number of each metallic element in its compound is as follows. HaCl4O has 3 Tl2O, Tl has 1 FeO, Fe has 2 Fe2O3, Fe has 3 Qui, Cu has 1 CuO, Cu has 2 MnO, Mn has 2 MnO2, Mn has 4. Therefore, these compounds may be represented as Ha3Cl4, Tl2IO, Fe2O, Fe23O3, Cui, Cu2O, Mn2O, MnIVO2. The idea of oxidation number has been invariably applied to define oxidation, reduction, oxidizing agent oxidant, reducing agent reductant and the redox reaction. To summarize, we may say that oxidation, an increase in the oxidation number of the element in the given substance. Reduction, a decrease in the oxidation number of the element in the given substance. Oxidizing agent, a reagent which can increase the oxidation number of an element in a given substance. These reagents are called as oxidants also. Reducing agent, a reagent which lowers the oxidation number of an element in a given substance. These reagents are also called as reductants. Redox reactions, reactions which involve change in oxidation number of the interacting species. Problem 8.4 justify that the reaction 2Cu2OS Cu2SS6 CuSO2G is a redox reaction. Identify the species oxidized reduced, which acts as an oxidant and which acts as a reductant. Solution: let us assign oxidation number to each of the species in the reaction under examination. This results into 1 minus 2 1 minus 2 0 4 minus 2 2 Cu2OS Cu2SS6 CuSO2. We therefore concluded in this reaction copper is reduced from 1 state to 0 oxidation state and sulfur is oxidized from -2 state to 4 state. The above reaction is thus a redox reaction. Group 1 2 13 14 15 16 17 element NaMgAlCpSCl compound NaClMgSO4Al3CCl4P4010SF6HClO4 highest oxidation 1 2 3 4 5 6 7 number state of the group element. 270 Chemistry further. Cu2O helps sulfur in Cu2S to increase its oxidation number. Therefore, Cu is an oxidant, and sulfur of Cu2S helps copper both in Cu2S itself and Cu2O to decrease its oxidation number. Therefore, sulfur of Cu2S is reductant. 8.3.1 Types of redox reactions. 1. Combination reactions. A combination reaction may be denoted in the manner ABC. Either A and B or both A and B must be in the elemental form for such a reaction to be a redox reaction. All combustion reactions, which make use of elemental dioxygen, as well as other reactions involving elements other than dioxygen, are redox reactions. Some important examples of this category are 004-2CSO2G 8.24002-33 mg SN2GMG3 and 2S8.25-4104-2CH4G2O2GCO2G2H2OL2. Decomposition reactions. Decomposition reactions are the opposite of combination reactions. Precisely, a decomposition reaction leads to the breakdown of a compound into two or more components, at least one of which must be in the elemental state. Examples of this class of reactions are 1-2002H2OL2H2GO2G 8.261-1002 NaS2 NaSH2G 8.2715-2 1-102 KClO3S2 KClS3O2G 8.28. It may carefully be noted that there is no change in the oxidation number of hydrogen and methane under combination reactions and that of potassium and potassium chloride in reaction 8.28. This may also be noted here that all decomposition reactions are not redox reactions. For example, decomposition of calcium carbonate is not a redox reaction. 2,4-2,2-2,4-2 CaCO3SCaOSCO2G3. Displacement reactions. In a displacement reaction, an ion or an atom in a compound is replaced by an ion or an atom of another element. It may be denoted as XYZ-XY. Displacement reactions fit into two categories: metal displacement and non-metal displacement. A metal displacement. A metal in a compound can be displaced by another metal in the uncombined state. We have already discussed about this class of the reactions under section 8.2.1. Metal displacement reactions find many applications in metallurgical processes in which pure metals are obtained from their compounds and ores. A few such examples are 26-20026-2 CuSO4Ac ZNS CuSO4Ac 8.295-2002-2 V2O5S5 CaS2VS5 CaOS 8.304-1002-1 TCl4Al2 mg STS2MgCl2S 8.313-203-20 CR2O3S2 LSL2O3S2 CRS 8.32. In each case, the reducing metal is a better reducing agent than the one that is being reduced, which evidently shows more capability to lose electrons as compared to the one that is reduced. B. Non-metal displacement. The non-metal displacement redox reactions include hydrogen displacement and a rarely occurring reaction involving oxygen displacement. 271 Redox reactions. All alkali metals and some alkaline earth metals Ca, Sr, and Ba, which are very good reductants, will displace hydrogen from cold water. 0-1-2-1-2-1-0-2 NaS2H2OL2 NaOAc H2G 8.3301-22-2-2-1-0 Ca-S2H2OL Ca2Ac H2G 8.34. Less active metals such as magnesium and iron react with steam to produce dihydrogen gas. 0-1-22-2-2-1-0 mg S2H2OL MgO2SH2G 8.3501-23-202 Fe-S3H2OL Fe2O3S3 H2G 8.36. Many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Dihydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. A few examples for the displacement of hydrogen from acids are 0 1 -1 2 -1 0 ZnS2HCl AC ZnCl2 AC H2G 8.37 01 -1 2 -1 0 mg S2HCl AC MgCl2 AC H2G 8.38 01 -1 2 -1 0 Fe S2HCl AC FeCl2 AC H2G 8.39 Reactions 8.37 to 8.39 are used to prepare dihydrogen gas in the laboratory. Here, the reactivity of metals is reflected in the rate of hydrogen gas evolution, which is the slowest for the least active metal Fe, and the fastest for the most reactive metal, Mg. Very less active metals, which may occur in the native state such as silver Ag, and gold Au do not react even with hydrochloric acid. In section 8.2.1 we have already discussed that the metals, zinc Cn, copper Cu and silver Ag through tendency to lose electrons show their reducing activity in the order Zn, Cu, Ag. Like metals, activity series also exists for the halogens. The power of these elements as oxidizing agents decreases as we move down from fluorine to iodine in group 17 of the periodic table. This implies that fluorine is so reactive that it can replace chloride, bromide and iodide ions in solution. In fact, fluorine is so reactive that it attacks water and displaces the oxygen of water. 1 -20 1 -102 H2OL2 F2G4 HFACO2G 8.40 It is for this reason that the displacement reactions of chlorine, bromine and iodine using fluorine are not generally carried out in aqueous solution. On the other hand, chlorine can displace bromide and iodide ions in an aqueous solution as shown below. 0 1 -1 1 -1 0 Cl2G2K Br AC2K Cl AC Br2L 8.4101 -11 -1 0 Cl2G2K AC2K Cl AC I2S 8.42 as Br2 and I2 are colored and dissolve in CCl4, can easily be identified from the color of the solution. The above reactions can be written in ionic form as 0 -1 -1 0 Cl2G2 Br AC2 Cl AC Br2L 8.41 0 -1 -1 0 Cl2G2 I AC2 Cl AC I2S 8.42 B. Reactions 8.41 and 8.42 form the basis of identifying Br and I in the laboratory through the test popularly known as layer test. It may not be out of place to mention here that bromine likewise can displace iodide ion in solution. 0 -1 -1 0 Br2L2 I AC2 Br AC I2S 8.43 The halogen displacement reactions have a direct industrial application. The recovery of halogens from their halides requires an oxidation process, which is represented by 2xx22e 8.44 here X denotes a halogen element. Whereas chemical means are available to oxidize Cl, Br and I, as fluorine is the strongest oxidizing 272 chemistry agent, there is no way to convert F ions to F2 by chemical means. The only way to achieve F2 from F is to oxidize electrolytically, the details of which you will study at a later stage. 4. Disproportionation reactions. Disproportionation reactions are a special type of redox reactions. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. One of the reacting substances in a disproportionation reaction always contains an element that can exist in at least 3 oxidation states. The element in the form of reacting substance is in the intermediate oxidation state, and both higher and lower oxidation states of that element are formed in the reaction. The decomposition of hydrogen peroxide is a familiar example of the reaction, where oxygen experiences disproportionation. 1 -1 1 -202 H2O2 AC2 H2OLO2 G 8.45 Here the oxygen of peroxide, which is present in -1 state, is converted to 0 oxidation state in O2 and decreases to -2 oxidation state in H2O, phosphorus. Sulfur and chlorine undergo disproportionation in the alkaline medium as shown below. 0 -31 P4S3O AC3 H2OL pH3G3 H2PO2 AC 8.46 0 -22 S8 S12O AC4 S2 AC2 S2O3 2 AC6 H2OL 8.47 01 -1 Cl2G2O AC Cloac Cl AC H2OL 8.48 The reaction 8.48 describes the formation of household bleaching agents. The hypochlorite ion ClO formed in the reaction oxidizes the color-bearing stains of the substances to colorless compounds. It is of interest to mention here that whereas bromine and iodine follow the same trend as exhibited by chlorine in reaction 8.48, fluorine shows deviation from this behavior when it reacts with alkali. The reaction that takes place in the case of fluorine is as follows. 2F2G2O AC 2F AC of 2GH2OL 8.49 It is to be noted with care that fluorine in reaction 8.49 will undoubtedly attack water to produce some oxygen also. This departure shown by fluorine is not surprising for us as we know the limitation of fluorine that, being the most electronegative element, it cannot exhibit any positive oxidation state. This means that among halogens, fluorine does not show a disproportionation tendency. Problem 8.5. Which of the following species do not show disproportionation reaction, and why? ClO2, ClO3 and ClO4 also write reaction for each of the species that disproportionates. Solution: among the oxonions of chlorine listed above, ClO4 does not disproportionate because in this oxonion chlorine is present in its highest oxidation state, that is, 7. The disproportionation reactions for the other three oxonions of chlorine are as follows: 1-153 ClO2Cl ClO3 35-16 ClO2 4 ClO3 2Cl 5-174 ClO3 Cl3 Problem 8.6 Suggest a scheme of classification of the following redox reactions: An2GO2G2 No Gb2Pb Number 3 2S2 PbOS4 Number 2 GO2Gc Na SH2OL NaO Ag H2GD2 Number 2 G2O Ag Number 2 Ag Number 3 Ag H2OL. 273 Redox reactions. Solution: in reaction A, the compound nitric oxide is formed by the combination of the elemental substances, nitrogen and oxygen. Therefore, this is an example of combination redox reactions. The reaction B involves the breaking down of lead nitrate into 3 components. Therefore, this is categorized under decomposition redox reaction. In reaction the paradox of fractional oxidation number. Sometimes, we come across with certain compounds in which the oxidation number of a particular element in the compound is in fraction. Examples are C3O2 where oxidation number of carbon is 4,3, Br3O8 where oxidation number of bromine is 16,3 and Na2S4O6 where oxidation number of sulfur is 2.5. We know that the idea of fractional oxidation number is unconvincing to us, because electrons are never shared transferred in fraction. Actually, this fractional oxidation state is the average oxidation state of the element under examination, and the structural parameters reveal that the element for whom fractional oxidation state is realized is present in different oxidation states. Structure of the species C3O2, Br3O8 and S4O62 reveal the following bonding situations: 2020CCCO structure of C3O2 carbon suboxide structure of Br3O8 tribromotate oxide structure of S4O62 tetrophenate ion. The element marked with asterisk in each species is exhibiting the different oxidation state oxidation number from rest of the atoms of the same element in each of the species. This reveals that in C3O2, 2 carbon atoms are present in 2 oxidation state each, whereas the third one is present in 0 oxidation state and the average is 4,3. However, the realistic picture is 2 for 2 terminal carbons and 0 for the middle carbon. Likewise in Br3O8, each of the 2 terminal bromine atoms are present in 6 oxidation state and the middle bromine is present in 4 oxidation state. Once again the average, that is different from reality, is 16,3. In the same fashion, in the species S4O62, each of the 2 extreme sulfurs exhibits oxidation state of 5 and the 2 middle sulfurs is 0. The average of 4 oxidation numbers of sulfurs of the S4O62 is 2.5, whereas the reality being 5, 0, 0 and 5 oxidation number respectively for each sulfur. We may thus, in general, conclude that the idea of fractional oxidation state should be taken with care and the reality is revealed by the structures only. Further, whenever we come across with fractional oxidation state of any particular element in any species, we must understand that this is the average oxidation number only. In reality revealed by structures only, the element in that particular species is present in more than one whole number oxidation states. Fe3O4, Mn3O4, Pb3O4 are some of the other examples of the compounds, which are mixed oxides, where we come across with fractional oxidation states of the metal atom. However, the oxidation states may be in fraction as in O2 and O2 where it is 1/2 and -1/2 respectively. C. Hydrogen of water has been displaced by hydride ion into dihydrogen gas, therefore, this may be called as displacement redox reaction. The reaction D involves disproportionation of number 2,4 state into number 2,3 state and number 3,5 state. Therefore reaction D is an example of disproportionation redox reaction. 274 Chemistry Problem 8.7 Why do the following reactions proceed differently? Pb3O48HCl3 PbCl2Cl24H2O and Pb3O44HNO32 PbNO32 PbO2 2H2O Solution: Pb3O4 is actually a stoichiometric mixture of 2 mol of PbO and 1 mol of PbO2. In PbO2, lead is present in 4 oxidation state, whereas the stable oxidation state of lead in PbO is 2. PbO2 thus can act as an oxidant oxidizing agent and, therefore, can oxidize Cl ion of HCl into chlorine. We may also keep in mind that PbO is a basic oxide, therefore, the reaction Pb3O48HCl3 PbCl2Cl24H2O can be splitted into 2 reactions, namely, 2PbO4HCl2 PbCl2 2H2O acid-base reaction 4-120 PbO2 4HCl PbCl2 Cl2 2H2O redox reaction. Since HNO3 itself is an oxidizing agent, therefore, it is unlikely that the reaction may occur between PbO2 and HNO3. However, the acid-base reaction occurs between PbO and HNO3 as 2PbO4HNO3 2Pb number 322H2O. It is the passive nature of PbO2 against HNO3 that makes the reaction different from the one that follows with HCl. 8.3. Balancing of redox reactions. Two methods are used to balance chemical equations for redox processes. One of these methods is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on splitting the redox reaction into two half reactions, one involving oxidation and the other involving reduction. Both these methods are in use, and the choice of their use rests with the individual using the oxidation number method in writing equations for oxidation-reduction reactions. Just as for other reactions, the compositions and formulas must be known for the substances that react and for the products that are formed. The oxidation number method is now best illustrated in the following steps. Step 1. Write the correct formula for each reactant and product. Step 2. Identify atoms which undergo change in oxidation number in the reaction by assigning the oxidation number to all elements in the reaction. Step 3. Calculate the increase or decrease in the oxidation number per atom and for the entire molecule ion in which it occurs. If these are not equal, then multiply by suitable number so that these become equal. If you realize that two substances are reduced and nothing is oxidized, or vice versa, something is wrong. Either the formulas of reactants or products are wrong, or the oxidation numbers have not been assigned properly. Step 4. Ascertain the involvement of ions. If the reaction is taking place in water, add HRO ions to the expression on the appropriate side so that the total ionic charges of reactants and products are equal. If the reaction is carried out in acidic solution, use H ions in the equation. If in basic solution, use O ions. Step 5. Make the numbers of hydrogen atoms in the expression on the two sides equal by adding water H2O molecules to the reactants or products. Now, also check the number of oxygen atoms. If there are the same number of oxygen atoms in the reactants and products, the equation then represents the balanced redox reaction. Let us now explain the steps involved in the method with the help of a few problems given below. Problem 8.8. Write the net ionic equation for the reaction of potassium dichromate 6 K2Cr2O7 with sodium sulfite, Na2SO3, in an acid solution to give chromium 3 ion and the sulfate ion. 275 Redox reactions solution. Step 1. The skeletal ionic equation is Cr2O7 2XO3 2XCr3 XO4 2X. Step 2. Assign oxidation numbers for Cr and S6-2 4-2 3 6-2 Cr2O7 2XO3 2XCr XO4 2X. This indicates that the dichromate ion is the oxidant and the sulfite ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number, and make them equal. From step 2 we can notice that there is change in oxidation state of chromium and sulfur. Oxidation state of chromium changes from 6 to 3. There is decrease of 3 in oxidation state of chromium on right-hand side of the equation. Oxidation state of sulfur changes from 4 to 6. There is an increase of 2 in the oxidation state of sulfur on right-hand side. To make the increase and decrease of oxidation state equal, place numeral 2 before chromium ion on right-hand side and numeral 3 before sulfate ion on right-hand side, and balance the chromium and sulfur atoms on both the sides of the equation. Thus we get 6-2 4-2 3 Cr2O7 2Ac3 SO3 2Ac 2 Cr3 Ac 6-2 3 SO4 2Ac. Step 4. As the reaction occurs in the acidic medium, and further the ionic charges are not equal on both the sides, add 8H on the left to make ionic charges equal. Cr2O7 2Ac3 SO3 2Ac 8H2 Cr3 Ac3 SO4 2Ac. Step 5. Finally, count the hydrogen atoms, and add appropriate number of water molecules, that is, 4H2O on the right, to achieve balanced redox change. Cr2O7 2Ac3 SO3 2Ac 8H Ac 2 Cr3 Ac3 SO4 2Ac 4H2OL. Problem 8.9. Permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. Write the balanced ionic equation for the reaction. Solution. Step 1. The skeletal ionic equation is MnO4Ac Br Ac MnO2S Bro 3Ac. Step 2. Assign oxidation numbers for Mn and Br 7-145 MnO4Ac Br Ac MnO2S Bro 3Ac. This indicates that permanganate ion is the oxidant and bromide ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number, and make the increase equal to the decrease. 7-1452 MnO4Ac Br Ac 2 MnO2S Bro 3Ac. Step 4. As the reaction occurs in the basic medium, and the ionic charges are not equal on both sides, add 2 O ions on the right to make ionic charges equal. 2MnO4 Ac Br Ac 2MnO2S Bro 3 Ac 2O Ac. Step 5. Finally, count the hydrogen atoms and add appropriate number of water molecules, that is, 1 H2O molecule on the left side to achieve balanced redox. Change 2MnO4 Ac Br Ac H2OL 2MnO2S Bro 3 Ac 2O Ac B half reaction method. In this method, the two half equations are balanced separately and then added together to give balanced equation. Suppose we are to balance the equation showing the oxidation of Fe2 ions to Fe3 ions by dichromate ion Cr2O72 in acidic medium, wherein Cr2O72 ions are reduced to Cr3 ions. The following steps are involved in this task. Step 1. Produce unbalanced equation for the reaction in ionic form. Fe2 Ac Cr2O72 Ac Fe3 Ac Cr3 Ac 8.50. 276 Chemistry. Step 2. Separate the equation into half reactions. 2,3 oxidation half, Fe2 Ac Fe3 Ac 8.516 minus 2,3 reduction half, Cr2O72 Ac Cr3 Ac 8.52. Step 3. Balance the atoms other than O and H in each half reaction individually. Here the oxidation half reaction is already balanced with respect to Fe atoms. For the reduction half reaction, we multiply the Cr3 by 2 to balance Cr atoms. Cr2O72 Ac 2 Cr3 Ac 8.53. Step 4. For reactions occurring in acidic medium, add H2O to balance O atoms and H to balance H atoms. Thus, we get Cr2O72 Ac 14H Ac 2 Cr3 Ac 7 H2OL 8.54. Step 5. Add electrons to one side of the half reaction to balance the charges. If need be, make the number of electrons equal in the two half reactions by multiplying one or both half reactions by appropriate number. The oxidation half reaction is thus rewritten to balance the charge. Fe2 Ac Fe3 Ac 8.55. Now in the reduction half reaction there are net 12 positive charges on the left-hand side and only 6 positive charges on the right-hand side. Therefore, we add 6 electrons on the left side. Cr2O72 Ac 14H Ac 62 Cr3 Ac 7 H2OL 8.56 to equalize the number of electrons in both the half reactions. We multiply the oxidation half reaction by 6 and write as 6 Fe2 Ac 6 Fe3 Ac 68.57. Step 6. We add the two half reactions to achieve the overall reaction and cancel the electrons on each side. This gives the net ionic equation as 6 Fe2 Ac Cr2O72 Ac 14H Ac 6 Fe3 Ac 2 Cr3 Ac 7 H2OL 8.58. Step 7. Verify that the equation contains the same type and number of atoms and the same charges on both sides of the equation. This last check reveals that the equation is fully balanced with respect to number of atoms and the charges. For the reaction in a basic medium, first balance the atoms as is done in acidic medium, then for each H ion, add an equal number of O ions to both sides of the equation. Where H and O appear on the same side of the equation, combine these to give H2O. Problem 8.10 Permanganate 7 ion. MnO4 in basic solution oxidizes iodide ion, I to produce molecular iodine I2 and manganese IV oxide MnO2. Write a balanced ionic equation to represent this redox reaction. Solution. Step 1. First we write the skeletal ionic equation, which is MnO4 Ac Iac MnO2S I2S. Step 2. The two half reactions are -10 oxidation half, Iac I2S 74 reduction half, MnO4 Ac MnO2S. Step 3. To balance the I atoms in the oxidation half reaction, we rewrite it as 2 Iac I2S. Step 4. To balance the O atoms in the reduction half reaction, we add 2 water molecules on the right, MnO4 Ac MnO2S 2H2OL to balance the H atoms. We add 4 H ions on the left, MnO4 Ac 4H Ac MnO2S 2H2OL as the reaction takes place in a basic solution. Therefore, for 4 H ions, we add 4 O ions to both sides of the equation, MnO4 Ac 4H Ac 4O Ac MnO2S 2H2OL 4O Ac, replacing the H and O ions with water. 277 Redox reactions. The resultant equation is MnO4 Ac 2H2OL MnO2S 4O Ac. Step 5. In this step we balance the charges of the two half reactions in the manner depicted as 2 Iac I2S 2 EMnO4 Ac 2H2OL 3 EMnO2S 4O Ac. Now to equalize the number of electrons, we multiply the oxidation half reaction by 3 and the reduction half reaction by 2. 6 Iac 3 I2S 62 MnO4 Ac 4H2OL 62 MnO2S 8O Ac. Step 6. Add two half reactions to obtain the net reactions after cancelling electrons on both sides. 6 Iac 2 MnO4 Ac 4H2OL 3 I2S 2 MnO2S 8O Ac. Step 7. A final verification shows that the equation is balanced in respect of the number of atoms and charges on both sides. 8. 3. Redox reactions as the basis for titrations in acid-base systems. We come across with a titration method for finding out the strength of one solution against the other using a pH-sensitive indicator. Similarly, in redox systems, the titration method can be adopted to determine the strength of a reductant oxidant using a redox-sensitive indicator. The usage of indicators in redox titration is illustrated below. In one situation, the reagent itself is intensely colored, e.g., permanganate ion, MnO4. Here MnO4 acts as the self-indicator. The visible endpoint in this case is achieved after the last of the reductant Fe2RC2042 is oxidized and the first lasting tinge of pink color appears at MnO4 concentration as low as 10-6 mol DM3 10-6 mol L1. This ensures a minimal overshoot in color beyond the equivalence point, the point where the reductant and the oxidant are equal in terms of their mole stoichiometry. 2. If there is no dramatic autocolor changes with MnO4 titration, there are indicators which are oxidized immediately after the last bit of the reactant is consumed, producing a dramatic color change. The best example is afforded by Cr2072, which is not a self-indicator, but oxidizes the indicator substance diphenylamine just after the equivalence point to produce an intense blue color, thus signaling the endpoint. 3. There is yet another method which is interesting and quite common. Its use is restricted to those reagents which are able to oxidize ions. Say, for example, Cu2, 2Cu2Ag4 Iag2I2Si2Ag 8.59. This method relies on the facts that iodine itself gives an intense blue color with starch and has a very specific reaction with thiosulfate ions S2032, which too is a redox reaction. I2Ag2S2032 Ag2 Iag S4062 Ag 8.60 I2, though insoluble in water, remains in solution containing Ki3. On addition of starch after the liberation of iodine from the reaction of Cu2 ions on iodide ions, an intense blue color appears. This color disappears as soon as the iodine is consumed by the thiosulfate ions, thus, the endpoint can easily be tracked and the rest is the stoichiometric calculation only. 8. 4 Limitations of concept of oxidation number. As you have observed in the above discussion, the concept of redox processes has been evolving with time. This process of evolution is continuing. In fact, in recent past the oxidation process is visualized as a decrease in electron density and reduction process as an increase in electron density around the atom S involved in the reaction. 8.4 Redox reactions and electrode processes. The experiment corresponding to reaction 8.15 can also be observed if zinc rod is dipped in copper sulfate solution. The redox reaction takes place during the reaction. 278 Chemistry. Zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to direct transfer of electrons from zinc to copper ion. During this reaction heat is also evolved. Now we modify the experiment in such a manner that for the same redox reaction transfer of electrons takes place indirectly. This necessitates the separation of zinc metal from copper sulfate solution. We take copper sulfate solution in a beaker and put a copper strip or rod in it. We also take zinc sulfate solution in another beaker and put a zinc rod or strip in it. Now reaction takes place in either of the beakers and at the interface of the metal and its salt solution in each beaker both the reduced and oxidized forms of the same species are present. These represent the species in the reduction and oxidation half reactions. A redox couple is defined as having together the oxidized and reduced forms of a substance taking part in an oxidation or reduction half reaction. This is represented by separating the oxidized form from the reduced form by a vertical line or a slash representing an interface, e.g. solid solution. For example, in this experiment the two redox couples are represented as Zn2Zn and Cu2Cu. In both cases, oxidized form is put before the reduced form. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side. Fig. 8.3. We connect solutions in two beakers by a salt bridge, a U-tube containing a solution of potassium chloride or ammonium nitrate usually solidified by boiling with agar and later cooling to a jelly-like substance. This provides an electric contact between the two solutions without allowing them to mix with each other. The zinc and copper rods are connected by a metallic wire with a provision for an ammeter and a switch. The setup as shown in figure 8.3 is known as Daniell cell. When the switch is in the off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As soon as the switch is in the on position, we make the following observations. 1. The transfer of electrons now does not take place directly from Zn to Cu2 but through the metallic wire connecting the two rods, as is apparent from the arrow which indicates the flow of current. 2. The electricity from solution in one beaker to solution in the other beaker flows by the migration of ions through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rods known as electrodes here. The potential associated with each electrode is known as electrode potential. If the concentration of each species taking part in the electrode reaction is unity if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure and further the reaction is carried out at 298 K, then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential E0 of hydrogen electrode is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in the process to remain in the oxidized reduced form. A negative E0 means that the redox couple is a stronger figure 8.3. The setup for Daniell cell. Electrons produced at the anode due to oxidation of CN travel through the external circuit to the cathode where these reduce the copper ions. The circuit is completed inside the cell by the migration of ions through the salt bridge. It may be noted that the direction of current is opposite to the direction of electron flow. 279 Redox reactions. Reaction oxidized form now reduced form E00000 VF2G2E2F2.87 CO3 ECO2 1.81 H2O2 2H2E2 H2O 1.78 MnO48 H5 EMN2 4H2O 1.51O33 EOS 1.40 Cl2G2E2 Cl 1.36 CR2O7214 H6E2 CR37 H2O 1.33O2 G4H4E2 H2O 1.23 MnO2 S4 H2E Mn2 2H2O 1.23 Br2 2E2 Br 1.09 number 3 4H3 ENO G2 H2O 0.97 2Hg2 2EHG2 0.92 Ag S 0.80 Fe3 Fe2 0.7702 G 2H2EH2O2 0.68 I2S2E2I 0.54 QE/QS 0.52 Q2 2E/QS 0.34 Ag CLSE Ag SCL 0.22 Ag BRSE Ag SBR 0.10 2H2EH2G 0.00 PB2 2E PBS minus 0.13 SN2 2E SNS minus 0.14 Ni2 2E NES minus 0.25 Fe2 2E Fe-S minus 0.44 CR33 ECRS minus 0.74 ZN2 2E ZNS minus 0.76 2H2O 2EH2 G2O minus 0.83 L33 ELS minus 1.66 MG2 2E MGS minus 2.369 NAS minus 2.71 Ka2 2E KS minus 2.87 KEKS minus 2.93 LES minus 3.05 increasing strength of oxidizing agent increasing strength of reducing agent 1. A negative E0 means that the redox couple is a stronger reducing agent than the HH2 couple. 2. A positive E0 means that the redox couple is a weaker reducing agent than the HH2 couple. Table 8.1 The standard electrode potentials at 298 K ions are present as aqueous species and H2O as liquid. Gases and solids are shown by G and S respectively. Reducing agent than the HH2 couple. A positive E0 means that the redox couple is a weaker reducing agent than the HH2 couple. The standard electrode potentials are very important and we can get a lot of other useful information from them. The values of standard electrode potentials for some selected electrode processes reduction reactions are given in Table 8.1. You will learn more about electrode reactions and cells in Class 12. 280 Chemistry Summary Redox reactions form an important class of reactions in which oxidation and reduction occur simultaneously. 3-tier conceptualization viz. Classical, electronic and oxidation number, which is usually available in the texts, has been presented in detail. Oxidation, reduction, oxidizing agent oxidant and reducing agent reductant have been viewed according to each conceptualization. Oxidation numbers are assigned in accordance with a consistent set of rules. Oxidation number and ion electron method both are useful means in writing equations for the redox reactions. Redox reactions are classified into 4 categories: combination, decomposition, displacement and disproportionation reactions. The concept of redox couple and electrode processes is introduced here. The redox reactions find wide applications in the study of electrode processes and cells. Exercises 8.1 Assign oxidation number to the underlined elements in each of the following species. Na2PO4B NaSO4CH4P2O7DK2MnO4ECAO2F NAD4GH2S2O7H CalSO4 2.12H2O 8.2 What are the oxidation number of the underlined elements in each of the following and how do you rationalize your results? Ke3BH2S4O6C Fe3O4DCH3CH2OECH3Q 8.3 Justify that the following reactions are redox reactions. A CuOSH2G2SH2OGB Fe2O3S3COG2 Fe S3 H3CO2Gc4BCl3G3 LiAlH4S2B2H6G3 LiClS3LCl3SD2KFSE4NH3G5O2G4 NO G6H2OG8.4 Fluorine reacts with isan, results in the change, H2OSF2GHFG HOFG. Justify that this reaction is a redox reaction. 8.5 Calculate the oxidation number of sulfur, chromium and nitrogen in H2SO5, Cr2O72 and number 3. Suggest structure of these compounds, count for the fallacy. 8.6 Write formulas for the following compounds: a mercury 2 chloride B nickel 2 sulfate C tin IV oxide D thallium I sulfate E iron 3 sulfate F chromium 3 oxide. 8.7 Suggest a list of the substances where carbon can exhibit oxidation states from -4 to 4 and nitrogen from -3 to 5. 8.8 While sulfur dioxide and hydrogen peroxide can act as oxidizing as well as reducing agents in their reactions, ozone and nitric acid act only as oxidants. Why 8.9 Consider the reactions: a 6CO2G6H2OLC6H12O6Ac6O2G. 281 Redox reactions BO3GH2O2LH2OL2O2G. Why it is more appropriate to write these reactions as a 6CO2G12H2OLC6H12O6Ac6H2OL6O2G BO3GH2O2LH2OLO2G. O2G also suggest a technique to investigate the path of the above A and B redox reactions. 8.10 The compound AgF2 is unstable compound. However, if formed, the compound acts as a very strong oxidizing agent. Why 8.11 Whenever a reaction between an oxidizing agent and a reducing agent is carried out, a compound of lower oxidation state is formed if the reducing agent is in excess, and a compound of higher oxidation state is formed if the oxidizing agent is in excess. Justify this statement giving 3 illustrations. 8.12 How do you count for the following observations? Alkaline potassium permanganate and acidic potassium permanganate both are used as oxidants. Yet in the manufacture of benzoic acid from toluene we use alcoholic potassium permanganate as an oxidant. Why write a balanced redox equation for the reaction B when concentrated sulfuric acid is added to an inorganic mixture containing chloride? We get colorless pungent smelling gas HCl, but if the mixture contains bromide then we get red vapor of bromine. Why 8.13 Identify the substance oxidized reduced. Oxidizing agent and reducing agent for each of the following reactions: a 2-Ag-BRSC6H6O2 Ag-2-Ag-S2H-BrOxC6H4O2 Ag-BHCHOL2 Ag-NH3 Ag-3O Ag-2 Ag-SHCOO Ag-4NH3 Ag-2H2OLCHCHOL2 Cu2 Ag-5O Ag-Cu2OSHCOO Ag-3H2OLD and 2H4L2H2O2 Ln2G4H2OLE PBS PbO2S2H2SO4 Ag-tube SO4S2H2OL. 8.14 Consider the reactions: 2S2O32 Ag-I2SS4062 Ag-2I Ag-S2O32 Ag-2Br2L5H2OL2 SO42 Ag-4Br Ag-10H Ag. Why does the same reductant, thiosulfate, react differently with iodine and bromine? 8.15 Justify giving reactions that among halogens, fluorine is the best oxidant and among hydrohalic compounds, hydroiodic acid is the best reductant. 8.16 Why does the following reaction occur? Zia6,4 Ag2F Ag6H Ag Zia3GF2G3H2OL. What conclusion about the compound Na4 Zia6 of which Zia6,4 is a part can be drawn from the reaction? 8.17 Consider the reactions: a H3PO2 Ag4 OgNO3 Ag2H2OL H3PO4 Ag4 Ag-S4HNO3 Ag-BH3PO2 Ag2QSO4 Ag2H2OL H3PO4 Ag2QSH2SO4 Ag-CC6H5CHOL2 Ag-NH32 Ag-3O Ag-C6H5COO Ag-2 Ag-S4NH3 Ag-2H2OLD C6H5CHOL2 Cu2 Ag-5O Ag. No change observed. 282 Chemistry. What inference do you draw about the behavior of Ag and Cu2 from these reactions? 8.18 Balance the following redox reactions by ion-electron method: a MnO4 Ag Ag MnO2Si2S in basic medium, B MnO4 Ag SO2G Mn2 Ag HSO4 Ag in acidic solution, CH2O2 Ag Fe2 Ag Fe3 Ag H2OL in acidic solution, DCr2O72 SO2G Cr3 Ag So4 Ag in acidic solution. 8.19 Balance the following equations in basic medium by ion-electron method and oxidation number methods and identify the oxidizing agent and the reducing agent. A P4SO Ag PH3GHPO2 Ag BN2H4L ClO3 Ag No GCl GCl2O7GH2O2 Ag ClO2 Ag O2GH. 8.20 What sorts of informations can you draw from the following reaction? CN 2 grams 2O Ag CN Ag CNO Ag H2OL. 8.21 The Mn3 ion is unstable in solution and undergoes disproportionation to give Mn2, MnO2, and H ion. Write a balanced ionic equation for the reaction. 8.2 consider the elements, C's, Neg, I and F. Identify the element that exhibits only negative oxidation state. B. Identify the element that exhibits only positive oxidation state. C. Identify the element that exhibits both positive and negative oxidation states. D. Identify the element which exhibits neither the negative nor does the positive oxidation state. 8.23 Chlorine is used to purify drinking water. Excessive chlorine is harmful. The excessive chlorine is removed by treating with sulfur dioxide. Present a balanced equation for this redox change taking place in water. 8.24 Refer to the periodic table given in your book and now answer the following questions. A. Select the possible nonmetals that can show disproportionation reaction. B. Select 3 metals that can show disproportionation reaction. 8.25 In Ostwald's process for the manufacture of nitric acid, the first step involves the oxidation of ammonia gas by oxygen gas to give nitric oxide gas and steam. What is the maximum weight of nitric oxide that can be obtained starting only with 10.00 grams of ammonia and 20.00 grams of oxygen? 8.26 Using the standard electrode potentials given in the table. 8.1 Predict if the reaction between the following is feasible. A Fe3Ac and IAC B Ag and QSC Fe3Ac and QSD Ag S and Fe3Ac EBR2Ac and Fe2Ac. 283 Redox reactions. 8.27 Predict the products of electrolysis in each of the following. I. An aqueous solution of OgNO3 with silver electrodes. 2. An aqueous solution OgNO3 with platinum electrodes. 3. A dilute solution of H2SO4 with platinum electrodes. I. An aqueous solution of CuCl2 with platinum electrodes. 8.28 Arrange the following metals in the order in which they displace each other from the solution of their salts. Al, Cu, Fe, Mg and Zn. 8.29 Given the standard electrode potentials, Kk-2.93 V, Ag 0.80 V, Hg2 Hg 0.79 V, Mg2 Mg-2.37 V, Cr3 Cr -0.74 V. Arrange these metals in their increasing order of reducing power. 8.30 Depict the galvanic cell in which the reaction ZnS2 Ag Zn2 Ag2 Ag S takes place. Further show, I which of the electrode is negatively charged, 2 the carriers of the current in the cell, and 3 individual reaction at each electrode. 2018-1. Unit 9 After studying this unit, you will be able to present informed opinions on the position of hydrogen in the periodic table, identify the modes of occurrence and preparation of dihydrogen on a small and commercial scale, describe isotopes of hydrogen, explain how different elements combine with hydrogen to form ionic, molecular and non-stoichiometric compounds, describe how an understanding of its properties can lead to the production of useful substances and new technologies, understand the structure of water and use the knowledge for explaining physical and chemical properties, explain how environmental water quality depends on a variety of dissolved substances, difference between hard and soft water and learn about water softening, acquire the knowledge about heavy water and its importance, understand the structure of hydrogen peroxide, learn its preparatory methods and properties leading to the manufacture of useful chemicals and cleaning of environment, understand and use certain terms e.g., electron deficient, electron precise, electron rich, hydrogen economy, hydrogenation etc. Hydrogen, the most abundant element in the universe and the third most abundant on the surface of the globe, is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form it consists of only 1 proton and 1 electron. However, in elemental form it exists as a diatomic H2 molecule and is called dihydrogen. It forms more compounds than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance, as you will learn in this unit. 9.1 Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past, as you know by now that the elements in the periodic table are arranged according to their electronic configurations. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration ns1 of alkali metals, which belong to the first group of the periodic table. On the other hand, like halogens with ns2 and p5 configuration belonging to the 17th group of the periodic table, it is short by 1 electron to the corresponding noble gas configuration, helium-1s2. Hydrogen, therefore, has resemblance to alkali metals, which lose 1 electron to form unipositive ions, as well as with halogens, which gain 1 electron to form a negative ion. Like alkali metals, hydrogen forms oxides, halides and sulfides. However, unlike alkali metals, it has a very high ionization enthalpy and does not 285 Hydrogen possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. IH of Li is 520 kJ-mol-1, F is 1680 kJ-mol-1 and that of H is 1312 kJ-mol-1. Like halogens, it forms a diatomic molecule, combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens, in spite of the fact that hydrogen, to a certain extent resembles both with alkali metals and halogens, it differs from them as well. Now the pertinent question arises as where should it be placed in the periodic table? Loss of the electron from hydrogen atom results in nucleus H of 1.5 x 10-3 pm size. This is extremely small as compared to normal atomic and ionic sizes of 50 to 200 pm. As a consequence, H does not exist freely and is always associated with other atoms or molecules. Thus, it is unique in behavior and is, therefore, best placed separately in the periodic table. Unit 3. 9.2 Dihydrogen. H2 2. 1 occurrence. Dihydrogen is the most abundant element in the universe, 70 of the total mass of the universe, and is the principal element in the property hydrogen deuterium tritium relative abundance 99.985 0.0156 10 -15 relative atomic mass g mol -11 008 2 014 3 016 melting point K 13.96 18.73 20.62 boiling point K 20.39 23.67 25.0 density GL -10 0.090.18 0.27 enthalpy of fusion KJ mol -10 0.117 0.197 enthalpy of vaporization KJ mol -10 0.904 1.226 enthalpy of bond dissociation KJ mol -1 at 298.2 K 435.88 443.35 internuclear distance PM 74.14 74.14 ionization enthalpy KJ mol -1 1312 electron gain enthalpy KJ mol -1 -73 covalent radius PM 37 ionic radius H PM 208 solar atmosphere. The giant planets Jupiter and Saturn consist mostly of hydrogen. However, due to its light nature, it is much less abundant, 0.15 by mass, in the Earth's atmosphere. Of course, in the combined form it constitutes 15.4 of the Earth's crust and the oceans. In the combined form, besides in water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrides including hydrocarbons and many other compounds. 9.2. 2 isotopes of hydrogen. Hydrogen has 3 isotopes: protium, 11H, deuterium, 21H or D, and tritium, 31H or T. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinary hydrogen, protium, has no neutrons. Deuterium, also known as heavy hydrogen, has 1, and tritium has 2 neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156 of deuterium, mostly in the form of HD. The tritium concentration is about 1 atom per 1018 atoms of protium. Of these isotopes, only tritium is radioactive and emits low-energy Greek letter beta particles. 12.33 years. Table 9.1 Atomic and physical properties of hydrogen. 286 Chemistry. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reactions, mainly due to their different enthalpy of bond dissociation. Table 9.1. However, in physical properties these isotopes differ considerably due to their large mass differences. 9.3 Preparation of dihydrogen, H2. There are a number of methods for preparing dihydrogen from metals and metal hydrides. 9.3. 1 Laboratory preparation of dihydrogen iode is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. ZN2H ZN2H22. It can also be prepared by the reaction of zinc with aqueous alkali. ZN2NaO to ZnO2H2 sodium zincate. 9.3. 2 Commercial production of dihydrogen. The commonly used processes are outlined below. Electrolysis of acidified water using platinum electrodes gives hydrogen. Electrolysis 222 Trasisoff acidase 2HOL2HgOg2 high purity, 99.95 dihydrogen is obtained by electrolyzing warm aqueous barium hydroxide solution between nickel electrodes. 3. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reactions that take place are: at anode, 2Cl(Cl2G2e), at cathode, 2H2OL2EH2G2OAC. The overall reaction is 2NiAC2ClAc2H2OLCl2G2NiAc2OAC. Reaction of steam on hydrocarbons or coke at high temperatures in the presence of catalyst yields hydrogen. 1270 K-N2N222 Nic HNHONCO2N1HEG, 1270 K42 Nich GHOGCOG3HG. The mixture of CO and H2 is called water gas. As this mixture of CO and H2 is used for the synthesis of methanol and a number of hydrocarbons, it is also called synthesis gas or syngas. Nowadays syngas is produced from sewage, sawdust, scrap wood, newspapers etc. The process of producing syngas from coal is called coal gasification. 1270 K22 Cs Hog COGHG. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixtures with steam in the presence of iron chromate as catalyst. 673 K222 Catalyst COG Hog COGHG. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenide solution. Presently 77 of the industrial dihydrogen is produced from petrochemicals, 18 from coal, 4 from electrolysis of aqueous solutions and 1 from other sources. 9.4 Properties of dihydrogen. 9.4. 1 Physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is lighter than air and insoluble in water. Its other physical properties along with those of deuterium are given in Table 9.1. 9.4. 2 Chemical properties. The chemical behavior of dihydrogen and for that matter any molecule is determined, to a large extent, by bond dissociation enthalpy. The HH bond dissociation enthalpy is the highest for a single bond between 2 atoms of any element. What inferences would you draw from this fact? It is because of this factor that the dissociation of dihydrogen into its atoms is only 0.081 around 2000 K, which increases to 95.5 at 5000 K. Also, it is relatively inert at room temperature due to Th. 287 hydrogen high HH bond enthalpy. Thus, the atomic hydrogen is produced at a high temperature in an electric arc or under ultraviolet radiations. Since its orbital is incomplete with 1s1 electronic configuration, it does combine with almost all the elements. It accomplishes reactions by I loss of the only electron to give H, to gain of an electron to form H, and 3 sharing electrons to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reactions. Reaction with halogens. It reacts with halogens. X2 to give hydrogen halides, HX, 2,2-HGXG2HXGXF, Cl, Br, I. While the reaction with fluorine occurs even in the dark, with iodine it requires a catalyst. Reaction with dioxygen. It reacts with dioxygen to form water. The reaction is highly exothermic. 2H2GO2G2H2OL, H-285.9 kJ-mol. 1 Reaction with dinitrogen. With dinitrogen it forms ammonia. 673 K, 200 ATN 22 3Fe13 HGNG2NHG, 92.6 kJ-mol H. This is a method for the manufacture of ammonia by the Haber process. Reactions with metals. With many metals it combines at a high temperature to yield the corresponding hydrides. Section 9.5 H2G2Mg2MHS, where M is an alkali metal. Reactions with metal ions and metal oxides. It reduces some metal ions in aqueous solution and oxides of metals less active than iron into corresponding metals. 2,2-Zi-2-HGPDAC-PDS-2-HACAGMOSXMSEOL. Reactions with organic compounds. It reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, hydrogenation of vegetable oils using nickel as catalyst gives edible fats, margarine and vanaspati ghee. 2 Hydroformylation of olefins yields aldehydes which further undergo reduction to give alcohols. 2,222-HCORCHCHRCHCHCHO222 222-HRCHCHCHORCHCHCHO. Problem 9.1 Comment on the reactions of dihydrogen with I-chlorine. 2 Sodium and 3 copper to oxide solution. Dihydrogen reduces chlorine into chloride Cl ion and itself gets oxidized to H ion by chlorine to form hydrogen chloride. An electron pair is shared between H and Cl leading to the formation of a covalent molecule. 2 Dihydrogen is reduced by sodium to form Na. An electron is transferred from Na to H leading to the formation of an ionic compound. NaH3 dihydrogen reduces copper to oxide to copper in zero oxidation state and itself gets oxidized to H2O, which is a covalent molecule. 9.4. 3 Uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soybean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol cobalt-23 catalyst COG2HGCHOL. It is widely used for the manufacture of metal hydrides. Section 9.5. It is used for the preparation of hydrogen chloride. A highly useful chemical. 288 Chemistry. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxyhydrogen torches find use for cutting and welding purposes. Atomic hydrogen atoms produced by dissociation of dihydrogen with the help of an electric arc are allowed to recombine on the surface to be welded to generate the temperature of 4000 K. It is used as a rocket fuel in space research. Dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases greater energy per unit mass of fuel in comparison to gasoline and other fuels. 9.5 Hydrides. Dihydrogen, under certain reaction conditions, combines with almost all elements, except noble gases, to form binary compounds, called hydrides. If E is the symbol of an element, then hydride can be expressed as EHXEG, MgH2 or MHNEG, B2H6. The hydrides are classified into three categories: ionic or saline or salt-like hydrides, 2 covalent or molecular hydrides, 3 metallic or non-stoichiometric hydrides, 9, 5, 1 ionic or saline hydrides. These are stoichiometric compounds of dihydrogen formed with most of the S-block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as Lit, Bet2 and MgH2. In fact, Bet2 and MgH2 are polymeric in structure. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of H-ion. Anode 22 ELTHG2E saline hydrides react violently with water producing dihydrogen gas. 2,2-NaSHOAC NaOAC Hg lithium hydride is rather unreactive at moderate temperatures with O2 or Cl2. It is, therefore, used in the synthesis of other useful hydrides, e.g., 8-Li-Al2Cl6-2-Li-ALH46-Li Cl2-Lib2H62-Lib4-9, 5. 2 covalent or molecular hydride. Dihydrogen forms molecular compounds with most of the p-block elements. Most familiar examples are CH4, NH3, H2O and HF. For convenience, hydrogen compounds of nonmetals have also been considered as hydrides, being covalent. They are volatile compounds. Molecular hydrides are further classified according to the relative numbers of electrons and bonds in their Lewis structure into I electron deficient, 2 electron precise, and 3 electron-rich hydrides. An electron-deficient hydride, as the name suggests, has too few electrons for writing its conventional Lewis structure. Diborane B2H6 is an example. In fact, all elements of group 13 will form electron-deficient compounds. What do you expect from their behavior? They act as Lewis acids, that is, electron acceptors. Electron-precise compounds have the required number of electrons to write their conventional Lewis structures. All elements of group 14 form such compounds, e.g., CH4, which are tetrahedral in geometry. Electron-rich hydrides have excess electrons which are present as lone pairs. Elements of group 15-17 form such compounds. NH3 has 1 lone pair, H2O2 and HF-3 lone pairs. What do you expect from the behavior of such compounds? They will behave as Lewis bases, that is, electron donors. The presence of lone pairs on highly electronegative atoms like N, O and F in hydrides results in hydrogen bond formation between the molecules. This leads to the association of molecules. Problem 9.2. Would you expect the hydrides of N, O and F to have lower boiling points than the hydrides of their subsequent group members? Give reasons. 289 Hydrogen solution on the basis of molecular masses of NH3, H2O and HF. Their boiling points are expected to be lower than those of the subsequent group member hydrides. However, due to higher electronegativity of N, O and F, the magnitude of hydrogen bonding in their hydrides will be quite appreciable. Hence, the boiling points NH3, H2O and HF will be higher than the hydrides of their subsequent group members. 9, 5. 3 metallic or non-stoichiometric or interstitial hydrides. These are formed by many D-block and F-block elements. However, the metals of group 7, 8 and 9 do not form hydride. Even from group 6, only chromium forms CRH. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do, unlike saline hydrides. They are almost always non-stoichiometric, being deficient in hydrogen. For example, La2.87, YBH2.55, to 1.5 to 1.8, ZRH 1.3 to 1.75, BH 0.56, Ni 0.6 to 0.7, PDH 0.6 to 0.8, etc. In such hydrides, the law of constant composition does not hold good. Earlier it was thought that in these hydrides, hydrogen occupies interstices in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of Ni, Pd, Se and Ac, other hydrides of this class have lattice different from that of the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction hydrogenation reactions for the preparation of large number of compounds. Some of the metals, e.g., Pd, Pt, can accommodate a very large volume of hydrogen and, therefore, can be used as its storage media. This property has high potential for hydrogen storage and as a source of energy. Problem 9.3. Can phosphorus with outer electronic configuration 3s23 page 3 form pH5 solution? Although phosphorus exhibits 3 and 5 oxidation states, it cannot form pH5. Besides some other considerations, high A value of dihydrogen and egg value of hydrogen do not favor to exhibit the highest oxidation state of P, and consequently the formation of pH5. 9.6. Water. A major part of all living organisms is made up of water. Human body has about 65 and some plants have as much as 95 water. It is a crucial compound for the survival of all life forms. It is a solvent of great importance. The distribution of water over the Earth's surface is not uniform. The estimated world water supply is given in Table 9.2. Table 9.2. Estimated world water supply source of total oceans 97.33 saline lakes and inland seas 0.008 polar ice and glaciers 2.04 groundwater 0.61 lakes 0.009 soil moisture 0.005 atmospheric water vapor 0.001 rivers 0.0001961 Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in Table 9.3 along with the physical properties of heavy water. The unusual properties of water in the condensed phase liquid and solid states are due to the presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization and high heat of fusion in comparison to H2S and H2SN. In comparison to other liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment and dielectric constant, etc. These properties allow water to play a key role in the biosphere. 290. Chemistry. The high heat of vaporization and heat capacity are responsible for moderation of the climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrates dissolve in water. 9.6. Structure of water. In the gas phase, water is a bent molecule with a bond angle of 104.5 degrees, and OH bond length of 95.7 pm as shown in figure 9.1a. It is a highly property H2O D2O molecular mass G mol-118, 0151, 20, melting point K 273.0, 276.8, boiling point K 373.0, 374.4, enthalpy of formation Kj mol-1 285.9 294.6, enthalpy of vaporization 373 K Kj mol-140.66, 41.61, enthalpy of fusion Kj mol-1 6.01, tenth of max. Density K 276.98, 284.2, density 298 kgcm-31 viscosity centipoise 0.8903 dielectric constant C2Nm 278.3978.06 electrical conductivity 293 Ko-1 centimeters -1 5.7 x 10-8 Table 9.3 Physical properties of H2O and D2O, polar molecule, figure 9.1b. Its orbital overlap picture is shown in figure 9.1c. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperatures it condenses to cubic form. Density of ice is less than that of water. Therefore, an ice cube floats on water. In winter season, ice formed on the surface of a lake provides thermal insulation which ensures the survival of the aquatic life. This fact is of great ecological significance. 9.6.3 Structure of ice. Ice has a highly ordered three-dimensional hydrogen-bonded structure as shown in Fig. 9.2 Examination of ice crystals with figure 9.1 at the bent structure of water. B. The water molecule is a dipole and C. The orbital overlap picture in water molecule. Figure 9.2 The structure of ice. 291 hydrogen X-ray shows that each oxygen atom is surrounded tetrahedrally by 4 other oxygen atoms at a distance of 276 pm. Hydrogen bonding gives ice a rather open-type structure with wide holes. These holes can hold some other molecules of appropriate size interstitially. 9. 6. 4 chemical properties of water. Water reacts with a large number of substances. Some of the important reactions are given below. 1. Amphoteric nature. It has the ability to act as an acid as well as a base, that is, it behaves as an amphoteric substance. In the Bronsted sense, it acts as an acid with NH3 and a base with H2S. 23. 4 HOLNH ACOAC NHAC 22 3 HOLHS AC HOAC HS AC. The autoprotalysis self-ionization of water takes place as follows. 22 3 Hol HOAQ AQ acid 1 base 2 acid 2 base 1 acid base conjugate acid base 2 redox reactions involving water. Water can be easily reduced to dihydrogen by highly electropositive metals. 222 HOL2 NaS2 NaOAC Hg. Thus, it is a great source of dihydrogen. Water is oxidized to O2 during photosynthesis. 6 CO2G12H2OLC6H12O6 AC6H2OL6O2G with fluorine. Also it is oxidized to O2. To F2G2H2OL4H AC4F AC O2G3 hydrolysis reaction. Due to high dielectric constant, it has a very strong hydrating tendency. It dissolves many ionic compounds. However, certain covalent and some ionic compounds are hydrolyzed in water. 410-234 POS6 HOL4H POAC 422 CCLL2 HOLCOS4 HCl AC 323 NS3 HOL NHG3 OAC 4 hydrates formation. From aqueous solutions many salts can be crystallized as hydrated salts. Such an association of water is of different types, viz. I-coordinated water, e.g. 326CrHO3Cl2 interstitial water, e.g. 22 BaCl.2HO3 hydrogen bonded water, e.g. 222-424 CuHO and 42 Cuso.5HO. Problem 9.4 How many hydrogen bonded water molecules are associated in Cuso4.5H2O solution? Only one water molecule, which is outside the brackets coordination sphere, is hydrogen bonded. The other 4 molecules of water are coordinated. 9, 6, 5 Hard and soft water. Rainwater is almost pure, may contain some dissolved gases from the atmosphere. Being a good solvent, when it flows on the surface of the earth, it dissolves many salts. Presence of calcium and magnesium salts in the form of hydrogen carbonate, chloride and sulfate in water makes water hard. Hard water does not give lather with soap. Water free from soluble salts of calcium and magnesium is called soft water. It gives lather with soap easily. Hard water forms scum precipitate with soap. Soap containing sodium stearate C17H35 CuNa reacts with hard water to precipitate out Mg stearate. 21735 22CH CuNa AC MAC CHCOOM2 NaAC. Mg. It is, therefore, unsuitable for laundry. It is harmful for boilers as well, because of deposition of salts in the form of scale. This reduces the efficiency of the boiler. Th. 292 Chemistry. Hardness of water is of 2 types, I temporary hardness, and 2 permanent hardness. 9, 6 temporary hardness. Temporary hardness is due to the presence of magnesium and calcium hydrogen carbonates. It can be removed by I boiling. During boiling, the soluble MgHCO32 is converted into insoluble MgO2 and CaHCO32 is changed to insoluble CaCO3. It is because of high solubility product of MgO2 as compared to that of MgO3, that MgO2 is precipitated. These precipitates can be removed by filtration. Filtrate thus obtained will be soft water. Heating 222 mg HCO MgO2 CO. Heating 33222 CaHCO CaCO HOCO2 Clark's method. In this method calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide which can be filtered off. 3222 CaHCO CaO2 CaCO2 HO3 322 22 mg HCO2 CaO2 CaCO MgO2 HO9, 6, 7 Permanent hardness. It is due to the presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by the following methods. I treatment with washing soda. Sodium carbonate. Washing soda reacts with soluble calcium and magnesium chlorides and sulfates in hard water to form insoluble carbonates. 22334 MCl NaCO MCO2 NaCl MMG, KMSO NaCO MCO NaSO2 Calgon's method, sodium hexametaphosphate Na6P6018. commercially called calgon. When added to hard water, the following reactions take place: 266-18-46-18-22-246-18-26-18 Na PO2 Na Na PO mmg, Ka M Na PO Na MPO2 Na. The complex anion keeps the Mg2 and Ka2 ions in solution. 3. Ion exchange method. This method is also called zeolite permutate process. Hydrated sodium aluminium silicate is zeolite permutate. For the sake of simplicity, sodium aluminium silicate NaLCO4 can be written as NaS, when this is added in hard water. Exchange reactions take place: 222 NaS SMAC MZS2 NaAC mmg. Ka permutate zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treating with an aqueous sodium chloride solution 2,2-MZS2 NaClAc2 NaS SMClAc synthetic resins method. Nowadays hard water is softened by using synthetic cation exchangers. This method is more efficient than zeolite process. Cation exchange resins contain large organic molecule with SO3H group and are water insoluble. Ion exchange resin RSO3H is changed to RNA by treating it with NaCl. The resin exchanges Na ions with Ka2 and Mg2 ions present in hard water to make the water soft. Here R is resin anion 222 RNA-SMAC RMS2 NaAC. The resin can be regenerated by adding aqueous NaCl solution. Pure demineralized ionized water free from all soluble mineral salts is obtained by passing water successively through a cation exchange in the H form and an anion exchange in the O form resins. 222RH-SMAC MRS2H. In this cation exchange process, H exchanges for Na, Ka2, Mg2 and other cations present in water. This process results in proton release and thus makes the water acidic. In the anion exchange process, 293 hydrogen 223 RNHSHOL RNH.OS33 RNH.OSXAC RNH.XSOAC exchanges for anions like Cl, HCO3, SO4 etc. present in water. O ions, thus, liberated neutralize the H ions set free in the cation exchange. 2 hectares QOHA-QHOL. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solutions respectively. 9.7 Hydrogen peroxide H2O2. Hydrogen peroxide is an important chemical used in pollution control treatment of domestic and industrial effluents. 9.7. 1 Preparation. It can be prepared by the following methods: acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. 2224 422 2.8 HOSH SOAC base OSHOAC 8 HOL2 pure oxydisulfate. Obtained by electrolytic oxidation of acidified sulfate solutions at high current density, on hydrolysis yields hydrogen peroxide. Electrolysis 433 hydrolysis 422 2HSOAC HOSUZOHAC 2HSOAQ 2 hectares QHOAQ. This method is now used for the laboratory preparation of D2O2. 22.824 22 KSOS2 DOL2 KDSOAC DOL3. Industrially it is prepared by the auto-oxidation of 2-alkyl anthraquinols. 2,2-O 22 HPD2 ethylenthraquinol HO oxidized product. In this case 1H2O2 is formed. It is extracted with water and concentrated to 30 by mass by distillation under reduced pressure. It can be further concentrated to 85 by careful distillation under low pressure. The remaining water can be frozen out to obtain pure H2O2. 9.7. 2 Physical properties. In the pure state H2O2 is an almost colorless very pale blue liquid. Its important physical properties are given in Table 9.4. H2O2 is miscible with water in all proportions and forms a hydrate H2O2 H2O MP221K. A 30 solution of H2O2 is marketed as 100 volume hydrogen peroxide. It means that 1 milliliter of 30 H2O2 solution will give 100 milliliters of oxygen at STP. Commercially marketed sample is 10 V. Which means that the sample contains 3 H2O2. Problem 9.5. Calculate the strength of 10 volume solution of hydrogen peroxide. Solution 10 volume solution of H2O2 means that 1 L of this H2O2 solution will give 10 L of oxygen at STP 22 to 22 HOLOG Hol 2x 34 grams 22.7 L at STP 68 grams. On the basis of above equation 22.7 L of O2 is produced from 68 grams H2O2 at STP 10 L of O2 at STP is produced from X22 68 10 grams 29.9 grams 30 grams HO 22.7. Therefore, strength of H2O2 in 10 volume H2O2 solution 30 grams L3 H2O2 solution melting point K 272.4 density liquid at 298 kgcm-3 1.44 boiling point extrapolated K 423 viscosity 290 K centipoise 1.25 vapor pressure 298 kmm Hg 1.9 dielectric constant 298 Kc2n 270.7 density solid at 268.5 kgcm-3 1.64 electrical conductivity 298 K Greek letter omega -1 cm -1 5.1 x 10-8 table 9.4 physical properties of hydrogen peroxide. 294 Chemistry 9, 7, 3 structure hydrogen peroxide has a nonplanar structure. The molecular dimensions in the gas phase and solid phase are shown in figure 9.3 Fig. 9.3 A H2O2 structure in gas phase. Dihedral angle is 111.5 degrees p. H2O2 structure in solid phase at 110 K. Dihedral angle is 90.2 degrees. 9, 7, 4 chemical properties. It acts as an oxidizing as well as reducing agent in both acidic and alkaline media. Simple reactions are described below. Ioxidizing action in acidic medium 222-3 222-4 22 FeAc 2HAc HOAc FeAc 2HOL PbSS4 HOAc PSOS4 HOL22 reducing action in acidic medium 2422 222-3 22 MnO6H5 HO2 Mn8 HO50 HOCl HOHOClO3 oxidizing action in basic medium 2322 422 FeHO2 Fe2O MnHO Mn2O reducing action in basic medium 222 422 22 IHO2O2 I2HOO2 MnO3 HO2 MnO3O2 HO2O 9, 7, 5 storage H2O2 decomposes slowly on exposure to light. 22 HOL2 HOLOG in the presence of metal surfaces or traces of alkali present in glass containers, the above reaction is catalyzed. It is, therefore, stored in wax-lined glass or plastic vessels in dark. Urea can be added as a stabilizer. It is kept away from dust because dust can induce explosive decomposition of the compound. 9, 7, 6 uses. Its wide-scale use has led to tremendous increase in the industrial production of H2O2. Some of the uses are listed below. In daily life it is used as a hair bleach and as a mild disinfectant. As an antiseptic it is sold in the market as perhydrol 2. It is used to manufacture chemicals like sodium perborate and percarbonate, which are used in high-quality detergents. 3. It is used in the synthesis of hydroquinone, tartaric acid and certain food products and pharmaceuticals, cephalosporin, etc. 5. It is employed in the industries as a bleaching agent for textiles, paper pulp, leather, oils, fats, etc. Nowadays it is also used in environmental green chemistry, for example, in pollution control, treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage wastes, etc. 9.8 Heavy water, D2O. It is extensively used as a moderator in nuclear reactors and in exchange reactions for the study of reaction mechanisms. It can be prepared by exhaustive electrolysis of water or as a byproduct in some fertilizer industries. Its physical properties are given in Table 9.3. It is used for the preparation of other deuterium compounds. For example, 2222 232 24 43 243 CAC2 DOCD CAO DSO DO LC 12 DO3 CD4 ALO D 9.9 Dihydrogen as a fuel. Dihydrogen releases large quantities of heat on combustion. The data on energy released by combustion of fuels like dihydrogen, methane, LPG, etc. are compared in terms of the SAM. 295 hydrogen amounts in mole, mass and volume, are shown in Table 9.5. From this table it is clear that on a mass-for-mass basis dihydrogen can release more energy than petrol, about 3 times. Moreover, pollutants in combustion of dihydrogen will be less than petrol. The only pollutants will be the oxides of dinitrogen due to the presence of dinitrogen as impurity with dihydrogen. This, of course, can be minimized by injecting a small amount of water into the cylinder to lower the temperature so that the reaction between dinitrogen and dioxygen may not take place. However, the mass of the containers in which dihydrogen will be kept must be taken into consideration. A cylinder of compressed dihydrogen weighs about 30 times as much as a tank of petrol containing the same amount of energy. Also, dihydrogen gas is converted into liquid state by cooling to 20 K. This would require expensive insulated tanks of metal alloy like Non-E5. TT2, MgMgH2 etc. are in use for storage of dihydrogen in small quantities. These Table 9.5 the energy released by combustion of various fuels in moles. Mass and volume energy released on dihydrogen LPG CH4 gas octane combustion in kJ and gaseous in liquid and liquid state per mole 286 285 2000 228 185,511 per gram 143 142 50 53 47 per liter 12 9968 25590 35 34005. Limitations have prompted researchers to search for alternative techniques to use dihydrogen in an efficient way. In this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gaseous dihydrogen. Advantage of hydrogen economy is that energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as fuel was launched in October 2005 for running automobiles. Initially 5-dihydrogen has been mixed in CNG for use in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for generation of electric power. It is expected that economically viable and safe sources of dihydrogen will be identified in the years to come, for its usage as a common source of energy. Summary: hydrogen is the lightest atom with only one electron. Loss of this electron results in an elementary particle, the proton. Thus, it is unique in character. It has three isotopes, namely, protium 11H, deuterium D or 21H and tritium T or 31H. Amongst these three, only tritium is radioactive. In spite of its resemblance both with alkali metals and halogens, it occupies a separate position in the periodic table because of its unique properties. Hydrogen is the most abundant element in the universe. In the free state it is almost not found in the Earth's atmosphere. However, in the combined state, it is the third most abundant element on the Earth's surface. Dihydrogen on the industrial scale is prepared by the water-gas shift reaction from petrochemicals. It is obtained as a byproduct by the electrolysis of brine. 296 Chemistry: the HH bond dissociation enthalpy of dihydrogen 435.88 kJ-mol-1 is the highest for a single bond between two atoms of any elements. This property is made use of in the atomic hydrogen torch, which generates a temperature of 4000 K and is ideal for welding of high-melting metals. Though dihydrogen is rather inactive at room temperature because of very high negative dissociation enthalpy, it combines with almost all the elements under appropriate conditions to form hydrides. All the type of hydrides can be classified into three categories: ionic or saline hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Alkali metal hydrides are good reagents for preparing other hydride compounds. Molecular hydrides, e.g., B2H6, CH4, NH3, H2O, are of great importance in day-to-day life. Metallic hydrides are useful for ultrapurification of dihydrogen and as dihydrogen storage media. Among the other chemical reactions of dihydrogen, reducing reactions leading to the formation hydrogen halides, water, ammonia, methanol, vanaspati, etc. are of great importance. In metallurgical process, it is used to reduce metal oxides. In space programs, it is used as a rocket fuel. In fact, it has promising potential for use as a non-polluting fuel of the near future hydrogen economy. Water is the most common and abundantly available substance. It is of a great chemical and biological significance. The ease with which water is transformed from liquid to solid and to gaseous state allows it to play a vital role in the biosphere. The water molecule is highly polar in nature due to its bent structure. This property leads to hydrogen bonding, which is the maximum in ice and least in water vapor. The polar nature of water makes it a very good solvent for ionic and partially ionic compounds, B to act as an amphoteric acid as well as base substance, and C to form hydrates of different types. Its property to dissolve many salts, particularly in large quantity, makes it hard and hazardous for industrial use. Both temporary and permanent hardness can be removed by the use of zeolites and synthetic ion exchangers. Heavy water, D2O, is another important compound which is manufactured by the electrolytic enrichment of normal water. It is essentially used as a moderator in nuclear reactors. Hydrogen peroxide, H2O2, has an interesting nonpolar structure and is widely used as an industrial bleach and in pharmaceutical and pollution control treatment of industrial and domestic effluents. Exercises 9.1 justify the position of hydrogen in the periodic table on the basis of its electronic configuration. 9.2 Write the names of isotopes of hydrogen. What is the mass ratio of these isotopes? 9.3 Why does hydrogen occur in a diatomic form rather than in a monoatomic form under normal conditions? 9.4 How can the production of dihydrogen obtained from coal gasification be increased? 9.5 Describe the bulk preparation of dihydrogen by electrolytic method. What is the role of an electrolyte in this process? 9.6 Complete the following reactions: I2MOGMOS22 catalyst COGHG 297 hydrogen 338 2 catalyst Hg3HOG Thiazns NaOH 9.7 Discuss the consequences of high enthalpy of HH bond in terms of chemical reactivity of dihydrogen. 9.8 What do you understand by I electron deficient, 2 electron precise, and 3 electron rich compounds of hydrogen? Provide justification with suitable examples. 9.9 What characteristics do you expect from an electron deficient hydride with respect to its structure and chemical reactions? 9.10 Do you expect the carbon hydrides of the type CnH2n2 to act as Lewis acid or base? Justify your answer. 9.11 What do you understand by the term non-stoichiometric hydrides? Do you expect this type of the hydrides to be formed by alkali metals? Justify your answer. 9.12 How do you expect the metallic hydrides to be useful for hydrogen storage? Explain. 9.13 How does the atomic hydrogen or oxyhydrogen torch function for cutting and welding purposes? Explain. 9.14 Among NH3, H2O and HF, which would you expect to have highest magnitude of hydrogen bonding and why? 9.15 Selene hydrides are known to react with water violently producing fire. Can CO2, a well-known fire extinguisher, be used in this case? Explain. 9.16 Arrange the following ICA 2, that 2 and T2 in order of increasing electrical conductance. 2 Lit, Na and CSH in order of increasing ionic character. 3 HH, DD and FF in order of increasing bond dissociation enthalpy. 5 Na, MgH2 and H2O in order of increasing reducing property. 9.17 Compare the structures of H2O and H2O2. 9.18 What do you understand by the term autoprotalysis of water? What is its significance? 9.19 Consider the reaction of water with F2 and suggest. In terms of oxidation and reduction, which species are oxidized reduced? 9.20 Complete the following chemical reactions. I22 PbSSHOAC 2422 MNOAC HOAC 32 CaOSHOGV 32 AlClGHOLV 32 2 KNSHOL. Classify the above into a hydrolysis. B. Redox and C. Hydration reactions. 9.21 Describe the structure of the common form of ice. 9.22 What causes the temporary and permanent hardness of water? 9.23 Discuss the principle and method of softening of hard water by synthetic ion exchange, resins. 9.24 Write chemical reactions to show the amphoteric nature of water. 9.25 Write chemical reactions to justify that hydrogen peroxide can function as an oxidizing as well as reducing agent. 298 Chemistry. 9.26 What is meant by demineralized water and how can it be obtained? 9.27 Is demineralized or distilled water useful for drinking purposes? If not, how can it be made useful? 9.28 Describe the usefulness of water in biosphere and biological systems. 9.29 What properties of water make it useful as a solvent? What types of compound can it dissolve? And 2 Hydrolyzed. 9.30 Knowing the properties of H2O and D2O, do you think that D2O can be used for drinking purposes? 9.31 What is the difference between the terms hydrolysis and hydration? 9.32 How can selene hydrides remove traces of water from organic compounds? 9.33 What do you expect the nature of hydrides is? If formed by elements of atomic numbers 15, 19, 23 and 44 with dihydrogen, compare their behavior towards water. 9.34 Do you expect different products in solution when aluminium perchloride and potassium chloride treated separately with normal water to acidified water? And 3 Alkaline water. Write equations wherever necessary. 9.35 How does H2O2 behave as a bleaching agent? 9.36 What do you understand by the terms I hydrogen economy? 2 Hydrogenation. 3 Syngas. 5 Water gas shift reaction. V fuel cell. 2018 1. The s-block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only 2 electrons, 2 groups 1-2 belong to the s-block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as the alkali metals. These are so called because they form hydroxides on reaction with water which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium and radium. These elements with the exception of beryllium are commonly known as the alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature and these metal oxides are found in the Earth's crust. Among the alkali metals, sodium and potassium are abundant and lithium, rubidium and cesium have much lower abundances. Table 10.1. Francium is highly radioactive. Its longest-lived isotope 223-4 has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the Earth's crust. Strontium and barium have much lower abundances. Beryllium is rare and radium is the rarest of all, comprising only 10-10% of igneous rocks. Table 10.2, page 299. The general electronic configuration of s-block elements is noble gas Ns1 for alkali metals and noble gas Ns2 for alkaline earth metals. Unit 10. After studying this unit, You will be able to describe the general characteristics of the alkali metals and their compounds, explain the general characteristics of the alkaline earth metals and their compounds, describe the manufacture, properties and uses of industrially important sodium and calcium compounds including Portland cement, appreciate the biological significance of sodium, potassium, magnesium and calcium. The S-block elements. The thin, rocky outer layer of the Earth is crust, a type of rock formed from magma molten rock that has cooled and hardened. The first element of alkali and alkaline earth metals differs in many respects from the other members of the group. 300 Chemistry. Lithium and beryllium, the first elements of Group 1 and Group 2 respectively, exhibit some properties which are different from those of the other members of the respective group. In these anomalous properties they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to the similarity in ionic sizes and/or charge radius ratio of the elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. 10.1 Group 1 Elements, Alkali metals. The alkali metals show regular trends in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of alkali metals are discussed below. 1 electronic configuration. All the alkali metals have one valence electron, NS1. Table 10.1 Outside the noble gas core. The loosely held s electron in the outermost valence shell of these elements makes them the most electropositive metals. They readily lose electron to give monovalent M ions, hence they are never found in free state in nature. Increase in atomic number, the atom becomes larger, the monovalent ions M are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on moving down the group, that is, they increase in size while going from Li to Cs. 3 Ionization enthalpy. The ionization enthalpies of the alkali metals are considerably low and decrease down the group from Li to Cs. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. 4 Hydration enthalpy. The hydration enthalpies of alkali metal ions decrease with increase in ionic sizes. Li, Na, K, Rb, Li has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. E.g., LiCl, 2H2O10, 1. 5 Physical properties. All the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have low density which increases down the group from Li to Cs. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is emission of radiation in the visible region of the spectrum as given below. Alkali metals can therefore be detected by the respective flame tests and can be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. Element symbol. Electronic configuration. Lithium Li1s22s 1 sodium Na1s22s 22 p63s 1 potassium K1s22s 22 p63s 23 p64s 1 rubidium Rb1s22s 22 p63s 23 p63 D104s 24 p65s 1 cesium Cs1s22s 22 p63s 23 p63 D104s 24 p64 D105s 25 p66s 1 or Xe6s1 francium 4 Rn7s1 2 Atomic and ionic radii. The alkali metal atoms have the largest sizes in a particular period of the periodic table. With metal Li Na K RBCs color crimson, yellow, violet, red, blue, red, violet, Greek letter lambda NM 670.8 589.2 766 5 780 0 455 5 301 The S-block elements property. Lithium, sodium, potassium, rubidium, cesium, francium, Li Na K RBCs for atomic number 311 1937 55 87 atomic mass G mole -16.9422.9939.1085.47 132.91 223 electronic E2S1 Na3S1 R4S1 KR5S1 XE 6s1rn7s1 configuration ionization 520 496 419 403 376 375 enthalpy kJ mole -1 hydration -506 -406 -330 -310 -276 enthalpy kJ mole -1 metallic 152 186 227 248 265 radius pm ionic radius 76 102 138 152 167 180 mpm MP K 454 371 336 312 302 BPK 1615 1156 1032 961 944 density GCM -30.530.970.86 1.53 1.90 standard potentials -3.04 -2.714 -2.925 -2.930 -2.927 E0 V for mm occurrence in 18 2.27 1.84 78 12 26 10 -18 lithosphere. This property makes cesium and potassium useful as electrodes in photoelectric cells. 6 chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group I reactivity towards air. The alkali metals tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen-forming oxides. Lithium forms monoxide, sodium forms peroxide, the other metals form superoxides. The superoxide O2 ion is stable only in the presence of large cations such as K, Rb, Cs224 Li-O2 Li-O oxide 2222 No peroxide 22MoMo superoxide Mk, Rb, Cs. In all these oxides the oxidation state of the alkali metal is 1. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form the nitride, Li3N as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Problem 10.1 What is the oxidation state of K in KO2 solution? The superoxide species is represented as O2, since the compound is neutral. Therefore, the oxidation state of potassium is 1 ppm part per million, percentage by weight. Lithosphere, the Earth's outer layer, its crust and part of the upper mantle. Table 10.1 Atomic and physical properties of the alkali metals. 302 Chemistry 2 Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. 222 M2HO2 M2OHM an alkali metal. It may be noted that although lithium has most negative E0 value. Table 10.1. Its reaction with water is less vigorous than that of sodium, which has the least negative E0 value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia and alkynes. 3 Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 K, lithium at 1073 K to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. 22 MH2MH5 Reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides, MX. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion. The distortion of electron cloud of the anion by the cation is called polarization. The Li ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since anion with large size can be easily distorted, among halides, lithium iodide is the most covalent in nature. The reducing nature. The alkali metals are strong reducing agents, lithium being the most and sodium the least powerful. Table 10.1. The standard electrode potential E0, which measures the reducing power, represents the overall change. 2 ms-mg sublimation enthalpy mg-mge ionization enthalpy mg-HOM hydration enthalpy. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E0 value and its high reducing power. Problem 10.2 The E0 for Cl2Cl is 1.36, for I2I is 0.53, for Ag is 0.79, Na is -2.71 and for Li is 3.04. Arrange the following ionic species in decreasing order of reducing strength: I, Ag, Cl, Li. Na solution. The order is Li, Na, I, Ag, ClV. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. 3,3x3mxynhmnhenh. The blue color of the solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. M32AM to MENH1MNHUG, where M denotes solution in ammonia. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. 1017 uses. Lithium metal is used to make useful alloys, for example with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. It is used in thermonuclear reactions. Lithium is also used to make electrochemical cells. Sodium is used to make an APB alloy needed to make PbE4 and PbMe4. These organolide compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Potassium has 303 the S-block elements of vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. 10.2 General characteristics of the compounds of the alkali metals. All the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of their compounds are discussed here. 1 oxides and hydroxides on combustion in excess of air. Lithium forms mainly the oxide, Li2O+, and peroxide Li2O2. Sodium forms the peroxide, Na2O2, and some superoxide Na2, whilst potassium, rubidium and cesium form the superoxides, MO2. Under appropriate conditions, pure compounds N2O, M2O2 and MO may second be prepared. The increasing stability of the peroxide or superoxide, as the size of the metal ion increases, is due to the stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form the hydroxides according to the following reactions: 2,2-MOHO2-M2O2, 2,2-MO2HO2-M2OHO2, 2,2-22-MO2HO2-M2OHO. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. Problem 10.3 Why is KO2 paramagnetic? Solution: the superoxide O2 is paramagnetic because of one unpaired electron in Greek letter pi2p molecular orbital. The hydroxides which are obtained by the reaction of the oxides with water are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. 2 halides. The alkali metal halides, MX, XF, Cl, Br, I are all high melting, colorless crystalline solids. They can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid HX. All of these halides have high negative enthalpies of formation. The FH0 values for fluorides become less negative as we go down the group, whilst the reverse is true for FH0 for chlorides, bromides and iodides. For a given metal, FH0 always becomes less negative from fluoride to iodide. The melting and boiling points always follow the trend: fluoride, chloride, bromide, iodide. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas the low solubility of CSI is due to smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. LiCl is soluble in pyridine also. 3 salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom, e.g. carbonic acid, H2CO3OCO2, sulfuric acid, H2SO4O2SO2. The alkali metals form salts with all the oxoacids. They are generally soluble in water and thermally stable. Their carbonates M2CO3 and in most cases the hydrogen carbonates MHCO3 also are highly stable to heat. As the electropositive character increases down the group, the stability of the carbonates and hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium, being very small in size, polarizes a large CO3 ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. 304 Chemistry 10.3 Anomalous properties of lithium. The anomalous behavior of lithium is due to the exceptionally small size of its atom and ion, and too high polarizing power, that is, charge-radius ratio. As a result, there is increased covalent character of lithium compounds, which is responsible for their solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium, which has been discussed subsequently. 1 points of difference between lithium and other alkali metals. Lithium is much harder. Its MP and BP are higher than the other alkali metals. 2 Lithium is least reactive but the strongest reducing agent among all the alkali metals. On combustion in air it forms mainly monoxide, Li2O and the nitride, Li3N, unlike other alkali metals. 3. LiCl is deliquescent and crystallizes as a hydrate, LiCl, 2H2O, whereas other alkali metal chlorides do not form hydrates. Lithium hydrogen carbonate is not obtained in the solid form while all other elements form solid hydrogen carbonates. Lithium, unlike other alkali metals, forms no ethanide-on reaction with ethane. Lithium nitrate when heated gives lithium oxide, Li2O, whereas other alkali metal nitrates decompose to give the corresponding nitrite. 32224 Lino2 Li004 No02 322 Nano2 Nano07 Lif and Li2O are comparatively much less soluble in water than the corresponding compounds of other alkali metals. 103. 2 points of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes, atomic radii. Li 152 pm, Mg 160 pm, ionic radii, Li 76 pm, Mg 272 pm. The main points of similarity are, both lithium and magnesium are harder and lighter than other elements in the respective groups. 2. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble and their hydroxides decompose on heating. Both form a nitrite, Li3N and Mg3N2, by direct combination with nitrogen. 3. The oxides, Li2O and MgO, do not combine with excess oxygen to give any superoxide. The carbonates of lithium and magnesium decompose easily on heating to form the oxides and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Both LiCl and MgCl2 are soluble in ethanol. Both LiCl and MgCl2 are deliquescent and crystallize from aqueous solution as hydrates, LiCl, 2H2O and MgCl2, 8H2O 10.4. Some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride and sodium bicarbonate. The large-scale production of these compounds and their uses are described below. Sodium carbonate washing soda, Na2CO3, 10H2O. Sodium carbonate is generally prepared by solvay process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equations for the complete process may be written as 322-432 2NHHOCO NHCO4 322-432 NHCOHOCO2 NHHCO4343 NHHCO NaCl NHCl NaCO. Sodium hydrogen carbonate crystal separates. These are heated to give sodium carbonate. 305. The S-block elements 323222 NaCO NaCO. In this process NH3 is recovered when the solution containing NH4Cl is treated with CaO2. Calcium chloride is obtained as a byproduct. 43222 2NHCl CaO2 NHClHO. It may be mentioned here that solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Properties: sodium carbonate is a white crystalline solid which exists as a decolhydrate, Na2CO3, 10H2O. This is also called washing soda. It is readily soluble in water, on heating. The decolhydrate loses its water of crystallization to form monohydrate. Above 373 K, the monohydrate becomes completely anhydrous and changes to a white powder called soda ash. 375 K 2322322 NaCO 10HO NaCO 9HOII 373 K 232232 NaCO NaCO carbonate. Part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. 2323 COHOHCOO uses. It is used in water softening, laundering and cleaning. 2. It is used in the manufacture of glass, soap, borax and caustic soda. 3. It is used in paper, paints and textile industries. It is an important laboratory reagent both in qualitative and quantitative analysis. Sodium chloride, NaCl. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9 by mass of the salt. In tropical countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride, CaCl2, and magnesium chloride, MgCl2 are impurities because they are deliquescent, absorb moisture easily from the atmosphere. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separate out. Calcium and magnesium chloride, being more soluble than sodium chloride, remain in solution. Sodium chloride melts at 1081 K. It has a solubility of 36.0 grams in 100 grams of water at 273 K. The solubility does not increase appreciably with increase in temperature. Uses: Iod is used as a common salt or table salt for domestic purpose. 2. It is used for the preparation of Na2O2, NaO and Na2CO3. Sodium hydroxide caustic soda, NaO. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in Kastner-Kellner cell. A brine solution is electrolyzed using a mercury cathode and a carbon anode. Sodium metal discharged at the cathode combines with mercury to form sodium amalgam. Chlorine gas is evolved at the anode, Hg cathode, Na, amalgam 2,1 anode, ClCle. To the amalgam is treated with water to give sodium hydroxide and hydrogen gas. 2 Na amalgam 2H2O2 NaO2HgH2. Sodium hydroxide is a white, translucent solid. It melts at 591 K. It is readily soluble in water to give a strong alkaline solution. Crystals of sodium hydroxide are deliquescent. The sodium hydroxide solution at the surface reacts with the CO2 in the atmosphere to form Na2CO3. 306 Chemistry uses. It is used in the manufacture of soap, paper, artificial silk and a number of chemicals. 2 inches petroleum refining. 3 inches the purification of bauxite. I in the textile industries for mercerizing cotton fabrics. V for the preparation of pure fats and oils, and V as a laboratory reagent. Sodium hydrogen carbonate baking soda. NaCO3 sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide, leaving holes in cakes or pastries and making them light and fluffy. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. 23223 NaCOHOCO2 NaCO sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in fire extinguishers. 10.5 Biological importance of sodium and potassium. A typical 70 kilograms man contains about 90 grams of Na and 170 grams of K, compared with only 5 grams of iron and 0.06 grams of copper. Sodium ions are found primarily on the outside of cells, being located in blood plasma and in the interstitial fluid which surrounds the cells. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes and in the transport of sugars and amino acids into cells. Sodium and potassium, although so similar chemically, differ quantitatively in their ability to penetrate cell membranes, in their transport mechanisms and in their efficiency to activate enzymes. Thus, potassium ions are the most abundant cations within cell fluids, where they activate many enzymes, participate in the oxidation of glucose to produce ADP and, with sodium, are responsible for the transmission of nerve signals. There is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of cell membranes. As a typical example, in blood plasma, sodium is present to the extent of 143 mol-1, whereas the potassium level is only 5 mol-1 within the red blood cells. These concentrations change to 10 mol-1 Na and 105 mol-1 K. These ionic gradients demonstrate that a discriminatory mechanism, called the sodium-potassium pump, operates across the cell membranes, which consumes more than 1/3 of the ADP used by a resting animal and about 15 kilograms per 24H in a resting human. 10.6 Group 2 elements. Alkaline earth metals. The group 2 elements comprise beryllium, magnesium, calcium, strontium, barium and radium. They follow alkali metals in the periodic table. These except beryllium are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members and shows diagonal relationship to aluminium. The atomic and physical properties of the alkaline earth metals are shown in Table 10.2.10.6. 1 Electronic configuration. These elements have 2 electrons in the s orbital of the valence shell. Table 10.2. Their general electronic configuration may be represented as noble gas Ns2. Like alkali metals, the compounds of these elements are also predominantly ionic. Element symbol. Electronic configuration: beryllium B1s22s 2, magnesium Mg1s22s 22, p63s 2, calcium Ca1s22s 22, p63s 23, p64s 2, strontium Sr1s22s 22, p63s 23, p63 D10 4s24, p65s 2, barium Ba1s22s 22, p63s 23, p63 D104s24, p64 D105s25, p66s 2, or Xe6s2, radium Ra Rn7s2 106. 2. Atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the 307. The s-block elements corresponding alkali metals in the same periods. This is due to the increased nuclear charge in these elements. Within the group, The atomic and ionic radii increase with increase in atomic number 1,0,6,3 ionization enthalpies. The alkaline earth metals have low ionization enthalpies due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. Table 10.2. The first ionization enthalpies of the alkaline earth metals are higher than those of the corresponding group 1 metals. This is due to their small size as compared to the corresponding alkali metals. It is interesting to note that the second ionization enthalpies of the alkaline earth metals are smaller than those of the corresponding alkali metals. 1,0,6,4 hydration enthalpies. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decrease with increase in ionic size down the group. B2, Mg2, Ca2, Sr2, Ba2. The hydration enthalpies of alkaline earth metal ions are larger than those of alkali metal ions. Thus, compounds of alkaline earth metals are more extensively hydrated than those of alkali metals. E.g., MgCl2 and CaCl2 exist as MgCl2.6H2O and CaCl2, 6H2O, while NaCl and KCl do not form such hydrates. 1,0,6,5 physical properties. The alkaline earth metals, in general, are silvery white, lustrous and relatively soft but harder than the alkali metals. Beryllium and magnesium appear to be somewhat grayish. The melting and boiling points of these metals are higher than the corresponding alkali metals due to smaller sizes. The trend is, however, not systematic. Because of the low ionization enthalpies, they are strongly electropositive in nature. The electropositive character increases down the group from B to Ba. Calcium. Property: beryllium, magnesium, calcium, strontium, barium, radium, Bmg, Ca, Sr, Bara. Atomic number 4, 12, 20, 38, 56, 88. Atomic mass G mole -19.01, 24.31, 40.08, 87, 62, 137, 33, 226, 03. Electronic E2S2 Net3 S2 R4 S2 KR5 S2 XE6 S2 RN7 S2 configuration. Ionization 899 737 590 549 503 509 enthalpy IKJ mole 1 ionization 1757 1450 1145 1064 965 979 enthalpy 2 kJ mole 1 hydration enthalpy 2494 1921 minus 1577 1443 1305 kJ mole metallic 111 160 197 215 222 radius PM ionic radius 3172 100 118 135 148 square meters PM MP K 1560 924 1124 1062 1002 973 BPK 2745 1363 1767 1655 2078 1973 density GCM 31.84 1.74 1.55 2.63 3.59 5.5 standard potential -1.97 -2.36 -2.84 -2.89 to 2.92 -2.92 E0 V for M2M occurrence in 2.76 4.6 384 390 10-6. Lithosphere table 10.2 atomic and physical properties of the alkaline earth metals ppm part per million, percentage by weight. 308 chemistry strontium and barium impart characteristic brick red, crimson and apple green colors respectively to the flame. In flame the electrons are excited to higher energy levels and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by flame, hence, these elements do not impart any color to the flame. The flame test for Ca, Sr and Ba is helpful in their detection in qualitative analysis and estimation by flame photometry. The alkaline earth metals like those of alkali metals have high electrical and thermal conductivities which are typical characteristics of metals. 1,0,6,6 chemical properties. The alkaline earth metals are less reactive than the alkali metals. The reactivity of these elements increases on going down the group. I reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium burns brilliantly on ignition in air to give Ba and B3N2. Magnesium is more electropositive and burns with dazzling brilliance in air to give MgO and Mg3N2. Calcium, strontium and barium are readily attacked by air to form the oxide and nitride. They also react with water with increasing vigor even in cold to form hydroxides. 2. Reactivity towards the halogens. All the alkaline earth metals combine with halogen at elevated temperatures forming their halides. 2,2-MXMXXF, Cl, Br, L. Thermal decomposition of NH4,2-Bf4 is the best route for the preparation of Bf2, and BCl2 is conveniently made from the oxide. 600 800 K22BaCCl BClCO3 reactivity towards hydrogen. All the elements except beryllium combine with hydrogen upon heating to form their hydrides, MH2. Be2, however, can be prepared by the reaction of BCl2 with LiAlH4, 24232 BCl LiAlH2 BeCl reactivity towards acids. The alkaline earth metals readily react with acids liberating dihydrogen. M2HCl MCl2H2V reducing nature. Like alkali metals, the alkaline earth metals are strong reducing agents. This is indicated by large negative values of their reduction potentials, table 10.2. However, their reducing power is less than those of their corresponding alkali metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy associated with the small size of B2 ion and relatively large value of the atomization enthalpy of the metal. These solutions in liquid ammonia, like alkali metals, the alkaline earth metals dissolve in liquid ammonia to give deep blue-black solutions forming ammoniated ions. 2333XYMXYNHMNH2ENH. From these solutions, the ammoniates, MNH362, can be recovered. 1067 uses. Beryllium is used in the manufacture of alloys. Copper beryllium alloys are used in the preparation of high-strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloys with aluminium, zinc, manganese and tin. Magnesium-aluminium alloys, being light in mass, are used in aircraft construction. Magnesium powder and ribbon is used in flash powders and bulbs, incendiary bombs and signals. A suspension of magnesium hydroxide in water called milk of magnesia is used as antacid and medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperatures, have often been used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, in the treatment of cancer. 309 The S-block elements. 10.7 General characteristics of compounds of the alkaline earth metals. The depositive oxidation state M2 is the predominant valence of group 2 elements. The alkaline earth metals form compounds which are predominantly ionic but less ionic than the corresponding compounds of alkali metals. This is due to increased nuclear charge and smaller size. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large-size members Ca, Sr, Ba. The general characteristics of some of the compounds of alkali earth metals are described below. Oxides and hydroxides. The alkaline earth metals burn in oxygen to form the monoxide, MO, which, except for Ba, have rock salt structure. The Ba is essentially covalent in nature. The enthalpies of formation of these oxides are quite high and consequently they are very stable to heat. Ba is amphoteric while oxides of other elements are ionic in nature. All these oxides except Ba are basic in nature and react with water to form sparingly soluble hydroxides. MOH2O MO to the solubility, thermal stability and the basic character of these hydroxides increase with increasing atomic number from MgO2 to BaO2. The alkaline earth metal hydroxides are, however, less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. BO2-2O BO4-2 berylate ion BO2-2HCl2H2O BO4Cl2 halides, except for beryllium halides. All other halides of alkaline earth metals are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvents. Beryllium chloride has a chain structure in the solid state as shown below. In the vapor phase BCl2 tends to form a chlorobridge dimer which dissociates into the linear monomer at high temperatures of the order of 1200 K. The tendency to form halide hydrates gradually decreases. For example, MgCl2, 8H2O, CaCl2, 6H2O, SrCl2, 6H2O and BaCl2, 2H2O down the group. The dehydration of hydrated chlorides, bromides and iodides of Ca, Sr and Ba can be achieved on heating. However, the corresponding hydrated halides of B and Mg on heating suffer hydrolysis. The fluorides are relatively less soluble than the chlorides owing to their high lattice energies. 3 salts of oxosides. The alkaline earth metals also form salts of oxosides. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of a sodium or ammonium carbonate solution to a solution of a soluble salt of these metals. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. All the carbonates decompose on heating to give carbon dioxide and the oxide. Beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increases with increasing cationic size. Sulfates. The sulfates of the alkaline earth metals are all white solids and stable to heat. BeSO4 and MgSO4 are readily soluble in water. The solubility decreases from CaSO4 to BeSO4. The greater hydration enthalpies of B2 and Mg2 ions overcome the lattice enthalpy factor and therefore their sulfates are soluble in water. Nitrates. The nitrates are made by dissolution of the carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt. This again shows a decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. All of them decompose on heating to give the oxide like lithium nitrate 3222 2M number 2MO4 no OMB. Mg, Ca, Sr, Ba. 310 Chemistry Problem 10.4 Why does the solubility of alkaline earth metal hydroxides in water increase down the group solution among alkaline earth metal hydroxides? The anion being common, the cationic radius will influence the lattice enthalpy. Since lattice enthalpy decreases much more than the hydration enthalpy with increasing ionic size, the solubility increases as we go down the group. Problem 10.5 Why does the solubility of alkaline earth metal carbonates and sulfates in water decrease down the group solution, the size of anions being much larger compared to cations? The lattice enthalpy will remain almost constant within a particular group. Since the hydration enthalpies decrease down the group, solubility will decrease as found for alkaline earth metal carbonates and sulfates. 10.8 Anomalous behavior of beryllium. Beryllium, the first member of the group 2 metals, shows anomalous behavior as compared to magnesium and rest of the members. Further, it shows diagonal relationship to aluminium, which is discussed subsequently. Beryllium has exceptionally small atomic and ionic sizes and thus does not compare well with other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent and get easily hydrolyzed. 2 Beryllium does not exhibit coordination number more than 4 as in its valence shell there are only 4 orbitals. The remaining members of the group can have a coordination number of 6 by making use of d orbitals. 3 The oxide and hydroxide of beryllium, unlike the hydroxides of other elements in the group, are amphoteric in nature. 108. 1 Diagonal relationship between beryllium and aluminium. The ionic radius of B2 is estimated to be 31 pm. The charge radius ratio is nearly the same as that of the Al3 ion. Hence beryllium resembles aluminium in some ways. Some of the similarities are, like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film on the surface of the metal. 2 Beryllium hydroxide dissolves in excess of alkali to give a berylate ion, BO42, just as aluminium hydroxide gives aluminate ion, AlO4. 3 The chlorides of both beryllium and aluminium have Cl, bridged chloride structure in vapor phase. Both the chlorides are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts catalysts. Beryllium and aluminium ions have strong tendency to form complexes, Bef42, Alf63. 10.9 Some important compounds of calcium. Important compounds of calcium are calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate and cement. These are industrially important compounds. The large-scale preparation of these compounds and their uses are described below. Calcium oxide or quicklime, CaO. It is prepared on a commercial scale by heating limestone CaCO3 in a rotary kiln at 1070 1270 K. Heat 32 CaCO-CaO. The carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Calcium oxide is a white amorphous solid. It has a melting point of 2870 K on exposure to atmosphere. It absorbs moisture and carbon dioxide. 311 The S-block elements 2,2-CaOHO CaO2 3-CaO-CO CaCO. The addition of limited amount of water breaks the lump of lime. This process is called slaking of lime. Quicklime slaked with soda gives solid soda lime. Being a basic oxide, it combines with acidic oxides at high temperature. 2,3-CaO-CO CaCO4 10,3,4,2,6-CaOPO2 CaPO. Uses. It is an important primary material for manufacturing cement and is the cheapest form of alkali. 2. It is used in the manufacture of sodium carbonate from caustic soda. 3. It is employed in the purification of sugar and in the manufacture of dyestuffs. Calcium hydroxide slaked lime, CaO2. Calcium hydroxide is prepared by adding water to quicklime. CaO. It is a white amorphous powder. It is sparingly soluble in water. The aqueous solution is known as lime water and a suspension of slaked lime in water is known as milk of lime. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. 2,322 CaO-CO CaCO-HO. On passing excess of carbon dioxide, the precipitate dissolves to form calcium hydrogen carbonate. 3,2,232 CaCO-COHO CaHCO. Milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. 22222 bleaching powder 2-CrO2Cl2HOCl uses. I. It is used in the preparation of mortar, a building material. 2. It is used in whitewash due to its disinfectant nature. 3. It is used in glass making, in tanning industry, for the preparation of bleaching powder and for purification of sugar. Calcium carbonate, CaCO3. Calcium carbonate occurs in nature in several forms like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slaked lime or by the addition of sodium carbonate to calcium chloride. 2,322 CrO-CO CaCO-HO2,233 CaCl NaCO CaCO2 NaCl. Excessive carbon dioxide should be avoided since this leads to the formation of water-soluble calcium hydrogen carbonate. Calcium carbonate is a white fluffy powder. It is almost insoluble in water. When heated to 1200 K, it decomposes to evolve carbon dioxide. 1200 K 32 CaCO-CaOCO. It reacts with dilute acid to liberate carbon dioxide. 3222 CaCO2HCl CaCl-HOCO 324422 CaCO-HCO CaCO-HOCO uses. It is used as a building material in the form of marble and in the manufacture of quicklime. Calcium carbonate along with magnesium carbonate is used as a flux in the extraction of metals such as iron. Specially precipitated CaCO3 is extensively used in the manufacture of high-quality paper. It is also used as an antacid, mild abrasive in toothpaste, a constituent of chewing gum, and a filler in cosmetics. Calcium sulfate plaster of Paris, CaSO4, 1/2 H2O. It is a hemohydrate of calcium sulfate. It is obtained when gypsum CaSO4, 2H2O, is heated to 393 K 424222 CaSO.2HO2 CaSO.HO3HO above 393 K. No water of crystallization is left and anhydrous calcium sulfate, CaSO4, is formed. This is known as dead burnt plaster. 312 Chemistry. It has a remarkable property of setting with water. On mixing with an adequate quantity of water, it forms a plastic mass that gets into a hard solid in 5 to 15 minutes. Uses. The largest use of plaster of Paris is in the building industry as well as plasters. It is used for immobilizing the affected part of organ where there is a bone fracture or sprain. It is also employed in dentistry, in ornamental work and for making casts of statues and busts. Cement. Cement is an important building material. It was first introduced in England in 1824 by Joseph Aspdin. It is also called Portland cement because it resembles with a natural limestone quarried in the Isle of Portland, England. Cement is a product obtained by combining a material rich in lime, CaO, with other materials such as clay which contains silica, CO2, along with the oxides of aluminium, iron and magnesium. The average composition of Portland cement is CaO, 50-60, CO2, 20-25, Al2O3, 510, MgO, 2-3, Fe2O3, 1-2 and SO3, 1-2. For a good quality cement, the ratio of silica CO2 to alumina Al2O3 should be between 2.5 and 4, and the ratio of lime CaO to the total of the oxides of silicon CO2, aluminium Al2O3 and iron Fe2O3 should be as close as possible to 2. The raw materials for the manufacture of cement are limestone and clay. When clay and lime are strongly heated together, they fuse and react to form cement clinker. This clinker is mixed with 2,3 by weight of gypsum CaSO4, 2H2O to form cement. Thus important ingredients present in Portland cement are dicalcium silicate Co2CO426. Tricalcium. Summary. The S block of the periodic table constitutes Group 1 alkaline metals and Group 2 alkaline earth metals. They are so called because their oxides and hydroxides are alkaline in nature. The alkaline metals are characterized by 1s electron and the alkaline earth metals by 2s electrons in the valence shell of their atoms. These are highly reactive metals forming monopositive M and dipositive M2 ions respectively. Silicate Ca3CO551 intercalcium alumina Ca3Al2O611. Setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to the hydration of the molecules of the constituents and their rearrangement. The purpose of adding gypsum is only to slow down the process of setting of the cement so that it gets sufficiently hardened. Uses. Cement has become a commodity of national necessity for any country next to iron and steel. It is used in concrete and reinforced concrete, in plastering and in the construction of bridges, dams and buildings. 10.10 Biological importance of magnesium and calcium. An adult body contains about 25 grams of Mg and 1,200 grams of Ca compared with only 5 grams of iron and 0.06 grams of copper. The daily requirement in the human body has been estimated to be 200-300 milligrams. All enzymes that utilize ADP and phosphate transfer require magnesium as the cofactor. The main pigment for the absorption of light in plants is chlorophyll, which contains magnesium. About 99% of body calcium is present in bones and teeth. It also plays important roles in neuromuscular function, intraneuronal transmission, cell membrane integrity and blood coagulation. The calcium concentration in plasma is regulated at about 100 mgl1. It is maintained by two hormones, calcitonin and parathyroid hormone. Do you know that bone is not an inert and unchanging substance but is continuously being solubilized and redeposited to the extent of 400 mg per day in man? All this calcium passes through the plasma. Exercises 10.1 What are the common physical and chemical features of alkali metals? 10.2 Discuss the general characteristics and gradation and properties of alkaline earth metals. 10.3 Why are alkali metals not found in nature? 10.4 Find out the oxidation state of sodium in Na2O2. 10.5 Explain why is sodium less reactive than potassium. 10.6 Compare the alkali metals and alkaline earth metals with respect to I ionization enthalpy, 2 basicity of oxides and 3 solubility of hydroxides. 10.7 In what ways lithium shows similarities to magnesium in its chemical behavior? 10.8 Explain why can alkali and alkaline earth metals not be obtained by chemical reduction methods? 10.9 Why are potassium and cesium rather than lithium used in photoelectric cells? 10.10 When an alkali metal dissolves in liquid ammonia, the solution can acquire different colors. Explain the reasons for this type of color change. 10.11 Beryllium and magnesium do not give color to flame whereas other alkaline earth metals do so. Why? 10.12 Discuss the various reactions that occur in the Solvay process. 10.13 Potassium carbonate cannot be prepared by Solvay process. Why? 10.14 Why is Li2CO3 decomposed at a lower temperature whereas Na2CO3 at higher temperature? There is a regular trend in the physical and chemical properties of the alkali metal with increasing atomic numbers. The atomic and ionic sizes increase and the ionization enthalpies decrease systematically down the group. Somewhat similar trends are observed among the properties of the alkaline earth metals. The first element in each of these groups, lithium in group 1 and beryllium in group 2, shows similarities in properties to the second member of the next group. Such similarities are termed as the diagonal relationship in the periodic table. As such, these elements are anomalous as far as their group characteristics are concerned. The alkali metals are silvery white, soft and low melting. They are highly reactive. The compounds of alkali metals are predominantly ionic. Their oxides and hydroxides are soluble in water, forming strong alkalis. Important compounds of sodium include sodium carbonate, sodium chloride, sodium hydroxide and sodium hydrogen carbonate. Sodium hydroxide is manufactured by Kastner-Kellner process and sodium carbonate by Solvay process. The chemistry of alkaline earth metals is very much like that of the alkali metals. However, some differences arise because of reduced atomic and ionic sizes and increased cationic charges in case of alkaline earth metals. Their oxides and hydroxides are less basic than the alkali metal oxides and hydroxides. Industrially important compounds of calcium include calcium oxide lime, calcium hydroxide slaked lime, calcium sulfate plaster of Paris, calcium carbonate limestone and cement. Portland cement is an important constructional material. It is manufactured by heating a pulverized mixture of limestone and clay in a rotary kiln. The clinker thus obtained is mixed with some gypsum 2,3 to give a fine powder of cement. All these substances find variety of uses in different areas. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. 314 Chemistry 10.15 Compare the solubility and thermal stability of the following compounds of the alkali metals with those of the alkaline earth metals. A nitrates, bicarbonate, C sulfates. 10.16 Starting with sodium chloride, how would you proceed to prepare I-sodium metal? 2 sodium hydroxide, 3 sodium peroxide, I sodium carbonate. 10.17 What happens when I-magnesium is burnt in air? 2 quicklime is heated with silica, 3 chlorine reacts with slaked lime, I calcium nitrate is heated. 10.18 Describe 2 important uses of each of the following: I caustic soda, 2 sodium carbonate, 3 quicklime. 10.19 Draw the structure of IBCl2 vapor, 2 BCl2 solid. 10.20 The hydroxides and carbonates of sodium and potassium are easily soluble in water while the corresponding salts of magnesium and calcium are sparingly soluble in water. Explain. 10.21 Describe the importance of the following: I limestone, 2 cement, 3 plaster of Paris. 10.22 Why are lithium salts commonly hydrated and those of the other alkali ions usually anhydrous? 10.23 Why is Lith almost insoluble in water whereas LiCl soluble not only in water but also in acetone? 10.24 Explain the significance of sodium, potassium, magnesium and calcium in biological fluids. 10.25 What happens when I-sodium metal is dropped in water? 2 sodium metal is heated in free supply of air, 3 sodium peroxide dissolves in water. 10.26 Comment on each of the following observations. Are the mobilities of the alkali metal ions in aqueous solution are Li, Na, K, Rb, Cs. B. Lithium is the only alkali metal to form a nitride directly. Ce0 for M2 Act2 EMS where MK, SR or Ba is nearly constant 10.27 status to Y a solution of Na2CO3 is alkaline. B alkali metals are prepared by electrolysis of their fused chloride. C sodium is found to be more useful than potassium. 10.28 Write balanced equations for reactions between a Na2O2 and water. BKO2 and water. C Na2O and CO2. 10.29 How would you explain the following observations? IBA is almost insoluble but BSO4 is soluble in water. 2BA is soluble but BaSO4 is insoluble in water. 352 is more soluble than Ki in ethanol. 10.30 Which of the alkali metal is having least melting point in A, B, K, C, R, B, D, C's? 10.31 Which one of the following alkali metals gives hydrated salts? A, Li, B, Na, C, K, D, C's. 10.32 Which one of the alkaline earth metal carbonates is thermally the most stable? Co3, B, CaCO3, C, CrCO3, D, BaCO3. Unit 11 After studying this unit, you will be able to appreciate the general trends in the chemistry of p-block elements, describe the trends in physical and chemical properties of group 13 and 14 elements, explain anomalous behavior of boron and carbon, describe allotropic forms of carbon, know the chemistry of some important compounds of boron, carbon and silicon, list the important uses of group 13 and 14 elements and their compounds. The p-block elements. In p-block elements, the last electron enters the outermost p orbital, as we know that the number of p orbitals is 3n, therefore, the maximum number of electrons that can be accommodated in a set of p orbitals is 6. Consequently, there are 6 groups of p-block elements in the periodic table numbering from 13 to 18. Boron, carbon, nitrogen, oxygen, fluorine and helium head the groups. Their valence shell electronic configuration is ns2np16 except for He. The inner core of the electronic configuration may, however, differ. The difference in inner core of elements greatly influences their physical properties such as atomic and ionic radii, ionization enthalpy, etc., as well as chemical properties. Consequently, a lot of variation in properties of elements in a group of p-block is observed. The maximum oxidation state shown by a p-block element is equal to the total number of valence electrons, that is, the sum of the s and p electrons. Clearly, the number of possible oxidation states increases towards the right of the periodic table. In addition to this so-called group oxidation state, p-block elements may show other oxidation states which normally, but not necessarily, differ from the total number of valence electrons by unit of 2. The important oxidation states exhibited by p-block elements are shown in Table 11.1. In boron, carbon and nitrogen families, the group oxidation state is the most stable state for the lighter elements in the group. However, the oxidation state 2 unit less than the group oxidation state becomes progressively more stable for the heavier elements in each group. The occurrence of oxidation states 2 unit less than the group oxidation states are sometimes attributed to the inert pair effect. The variation in properties of the p-block elements due to the influence of d and f electrons in the inner core of the heavier elements makes their chemistry interesting. 316 Chemistry. The relative stabilities of these 2 oxidation states, group oxidation state and 2 unit less than the group oxidation state, may vary from group to group and will be discussed at appropriate places. It is interesting to note that the nonmetals and metalloids exist only in the p-block of the periodic table. The non-metallic character of elements decreases down the group. In fact, the heaviest element in each p-block group is the most metallic in nature. This change from non-metallic to metallic character brings diversity in the chemistry of these elements depending on the group to which they belong. In general, nonmetals have higher ionization enthalpies and higher electronegativities than the metals. Hence, in contrast to metals which readily form cations, nonmetals readily form anions. The compounds formed by highly reactive nonmetals with highly reactive metals are generally ionic because of large differences in their electronegativities. On the other hand, compounds formed between nonmetals themselves are largely covalent in character because of small differences in their electronegativities. The change of nonmetallic to metallic character can be best illustrated by the nature of oxides they form. The nonmetal oxides are acidic or neutral, whereas metal oxides are basic in nature. The first member of p-block differs from the remaining members of their corresponding group in 2 major respects. First is the size and all other properties which depend on size. Thus, the lightest p-block elements show the same kind of differences as the lightest s-block elements, lithium and beryllium. The second important difference, which applies only to the p-block elements, arises from the effect of d orbitals in the valence shell of heavier elements starting from the 3rd period onwards and their lack in 2nd period elements. The 2nd period elements of p groups starting from boron are restricted to a maximum covalence of 4 using 2s and 3 2p orbitals. In contrast, the 3rd period elements of p groups with the electronic configuration 3s23pn have the vacant 3d orbitals lying between the 3p and the 4s levels of energy. Using these d orbitals, the third period elements can expand their covalence above 4. For example, while boron forms only Bf4, aluminium gives off 6,3 ion. The presence of these d orbitals influences the chemistry of the heavier elements in a number of other ways. The combined effect of size and availability of d orbitals considerably influences the ability of these elements to form Greek letter pi bonds. The first member of a group differs from the heavier members in its ability to form multiple bonds to itself, e.g. CC. Table 11.1 General electronic configuration and oxidation states of p-block elements group 13, 14, 15, 16, 17, 18 General electronic NS2 NP1 NS2 NP2 NS2 NP3 NS2 NP4 NS2 NP5 NS2 NP6 configuration 1s2 for He first member of the BCNOFE group oxidation 3 4 5 6 7 8 state other oxidation 1 2 4 3 3 4 2 -2 5 3 1 -1 6 4 2 states. 317 The p-block elements NN and two other second-row elements e.g., CO, CN, CN, NO. This type of Greek letter pi bonding is not particularly strong for the heavier p-block elements. The heavier elements do form Greek letter pi bonds, but this involves d orbitals. As the d orbitals are of higher energy than the p orbitals, they contribute less to the overall stability of molecules than disc bonding of the second-row elements. However, the coordination number and species of heavier elements may be higher than for the first element in the same oxidation state. For example, in 5-oxidation state both N and P form oxonions. Number 3 coordination with Greek letter pi bond involving 1 nitrogen p orbital and 3 PO4 coordination involving S, P and D orbitals contributing to the Greek letter pi bond. In this unit we will study the chemistry of group 13 and 14 elements of the periodic table. 11.1 Group 13 elements. The boron family. This group elements show a wide variation in properties. Boron is a typical nonmetal. Aluminium is a metal but shows many chemical similarities to boron, and gallium, indium, thallium and nihonium are almost exclusively metallic in character. Boron is a fairly rare element, mainly occurs as orthoboric acid, H3BO3, borax, Na2B4O7, 10H2O, and kernite. Na2B4O7, 4H2O. In India, borax occurs in Puga Valley, Ladakh and Samhur Lake, Rajasthan. The abundance of boron in earth crust is less than 0.0001 by mass. There are two isotopic forms of boron, 10B19 and 11B81. Aluminium is the most abundant metal and the third most abundant element in the Earth's crust, 8.3 by mass after oxygen 45.5 and C27.7. Bauxite, Al2O3, 2H2O and chrylite, Na3Al6 are the important minerals of aluminium. In India it is found as mica in Madhya Pradesh, Karnataka, Orissa and Jammu. Gallium, indium and thallium are less abundant elements in nature. Nihonium has symbol NH, atomic number 113, atomic mass 286 grams mole 1 and electronic configuration RN5F1460 page 2. So far it has been prepared in small amount and half-life of its most stable isotope was 20 seconds. Due to these reasons its chemistry has not been established. Nihonium is a synthetically prepared radioactive element. Here atomic, physical and chemical properties of elements of this group leaving nihonium are discussed below. 1 electronic configuration. The outer electronic configuration of these elements is Ns2np1. A close look at the electronic configuration suggests that while boron and aluminium have noble gas core, gallium and indium have noble gas plus 10d electrons, and thallium has noble gas plus 14f electrons plus 10d electron cores. Thus, the electronic structures of these elements are more complex than for the first two groups of elements discussed in Unit 10. This difference in electronic structures affects the other properties and consequently the chemistry of all the elements of this group. 2 atomic radii on moving down the group. For each successive member 1 extra shell of electrons is added and, therefore, atomic radius is expected to increase. However, a deviation can be seen. Atomic radius of Ga is less than that of Al. This can be understood from the variation in the inner core of the electronic configuration. The presence of additional 10d electrons offer only poor screening effect. Unit 2 for the outer electrons from the increased nuclear charge in gallium. Consequently, the atomic radius of gallium 135 pm is less than that of aluminium 143 pm. 3 ionization enthalpy. The ionization enthalpy values as expected from the general trends do not decrease smoothly down the group. The decrease from B to Al is associated with increase in size. The observed discontinuity in the ionization enthalpy values between Al and Ga and between N and Gl are due to inability of D and F electrons, which have low screening effect, to compensate the increase in nuclear charge. The order of ionization enthalpies, as expected, is I1, I2, I3, the sum of the first three ionization enthalpies for each of the 318 chemistry elements is very high. Effect of this will be apparent when you study their chemical properties. 1 For electronegativity down the group, electronegativity first decreases from B to Al and then increases marginally. Table 11.2. This is because of the discrepancies in atomic size of the elements 1 5 physical properties. Boron is non-metallic in nature. It is extremely hard and black-colored solid. It exists in many allotropic forms. Due to very strong crystal and lattice, boron has unusually high melting point. Rest of the members are soft metals with low melting point and high electrical conductivity. It is worthwhile to note that gallium with unusually low melting point 303 K could exist in liquid state during summer. Its high boiling point 2676 K makes it a useful material for measuring high temperatures. Density of the elements increases down the group from boron to thallium. 6 chemical properties. Oxidation state and trends in chemical reactivity. Due to small size of boron, the sum of its first three ionization enthalpies is very high. This prevents it to form three ions and forces it to form only covalent compounds. But as we move from B to Al, the sum of the first three ionization enthalpies of Al considerably decreases, and is therefore able to form Al3 ions. In fact, aluminium is a highly electropositive metal, however, down the group, due to poor shielding effect of intervening d and f orbitals. The increased effective nuclear charge holds ns electrons tightly responsible for inert pair effect and thereby restricting their participation in bonding. As a result of this, only p orbital electron may be involved in bonding. In fact, in Ga, in and Tl, both 1 and 3 oxidation states are observed. The relative stability of one oxidation state progressively increases for heavier elements, Al, Ga, in, Tl. In thallium, one oxidation state is predominant. Table 11.2 Atomic and physical properties of group 13 elements. A metallic radius. B6 coordination. C Pauling scale. Atomic number 5 13 31 49 81. Atomic mass G mole -110.81 26.98 69 72 114 82 204 38. Electronic E2S22 page 1 Ne3S23 page 1 R3D104S24 page 1 KR4D105S25 page 1 XE4F145 D106S26 page 1 Configuration. Atomic radius PMA 88 143 135 167 170. Ionic radius 2753.5 62.0 80.0 88.5 M3 PMB. Ionic radius 120 140 150 mpm. Ionization I1 801 577 579 558 589. Enthalpy I2 2427 1816 1979 1820 1971. kJ mole 1 I3 3659 2744 2962 2704 2877. Electronegativity 2.01.51.61.71.8. Density GCM3 2.35 2.75.97.31 11.85 at 298 K. Melting point K 2453 933 303 430 576. Boiling point K 3923 2740 2676 2353 1730. EVV for M3M -1.660 56 to 034 1.26. EVV for MM 0.55 0.79. Acid 018 to 034 -1.39. Alkali property element boron aluminium gallium, indium thallium B Al Ga and Tl. 319 The p-block elements. Whereas the 3 oxidation state is highly oxidizing in character, the compounds in 1 oxidation state, as expected from energy considerations, are more ionic than those in 3 oxidation state. In trivalent state, the number of electrons around the central atom in a molecule of the compounds of these elements, e.g., boron and Bf3, will be only 6. Such electron-deficient molecules have tendency to accept a pair of electrons to achieve stable electronic configuration and thus, behave as Lewis acids. The tendency to behave as Lewis acid decreases with the increase in the size down the group. BCl3 easily accepts a lone pair of electrons from ammonia to form BCl3NH3. Solution standard electrode potential values for 2 half-cell reactions suggest that aluminium has high tendency to make Al3 Ag ions. Whereas Tl3 is not only unstable in solution but is a powerful oxidizing agent also, thus Tl is more stable in solution than Tl3. Aluminium, being able to form 3 ions easily, is more electropositive than thallium. I reactivity towards air. Boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3 respectively. With dinitrogen at high temperature they form nitrides. 2,2,3,2,ES3OG2EOS2ESNG2N as the element. The nature of these oxides varies down the group. Boron trioxide is acidic and reacts with basic metallic oxides forming metal borates. Aluminium and gallium oxides are amphoteric and those of indium and thallium are basic in their properties. 2. Reactivity towards acids and alkalis. Boron does not react with acids and alkalis even at moderate temperature, but aluminium dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminium dissolves in dilute HCl and liberates dihydrogen 2Al(S)6HCl(Ac)3H2G. However, concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. Aluminium also reacts with aqueous alkali and liberates dihydrogen 2Al(S)2-NeoAc6H2OL2-NiO4Ac3H2G. Sodium tetrahydroxaluminate 3 in trivalent state. Most of the compounds being covalent are hydrolyzed in water. For example, the trichlorides on hydrolysis in water form tetrahedral 4MO species. The hybridization state of element M is sp3. Aluminium chloride in acidified aqueous solution forms octahedral 3,2,6-Al-HO ion. In this complex ion, the 3d orbitals of Al are involved in the hybridization state of Al is sp3d2. Problem 11.1 Standard electrode potential values. EV for Al3Al is -1.66 V and that of Tl3Tl is 1.26 V. Predict about the formation of M3 ion in solution and compare the electropositive character of the two metals. AlCl3 achieves stability by forming a dimer. 320 Chemistry 3 Reactivity towards halogens. These elements react with halogens to form trihalides except Tli3. 2Es3X2G2X3SXF, Cl, Br. I. Problem 11.2 White fumes appear around the bottle of anhydrous aluminium chloride. Give reason. Solution anhydrous aluminium chloride is partially hydrolyzed with atmospheric moisture to liberate HCl gas. Moist HCl appears white in color. 11.2 Important trends and anomalous properties of boron. Certain important trends can be observed in the chemical behavior of group 13 elements. The trichlorides, bromides and iodides of all these elements being covalent in nature are hydrolyzed in water. Species like tetrahedral MO4 and octahedral MH2O63, except in boron, exist in aqueous medium. The monomeric trihalides, being electron deficient, are strong Lewis acids. Boron trifluoride easily reacts with Lewis bases such as NH3 to complete octet around boron. 3333Fb, NHFbNH. It is due to the absence of d orbitals that the maximum covalence of B is 4. Since the d orbitals are available with Al and other elements, the maximum covalence can be expected beyond 4. Most of the other metal halides e.g., AlCl3 are dimerized through halogen bridging e.g., Al2Cl6. The metal species completes its octet by accepting electrons from halogen in these halogen-bridged molecules. Problem 11.3 Boron is unable to form Bf63 ion. Explain. Solution. Due to non-availability of d orbitals, boron is unable to expand its octet. Therefore, the maximum covalence of boron cannot exceed 4. 11.3 Some important compounds of boron. Some useful compounds of boron are borax, orthoboric acid and diborane. We will briefly study their chemistry. 1.1.3. 1. Borax. It is the most important compound of boron. It is a white crystalline solid of formula Na2B4O710H2O. In fact, it contains the tetranuclear units 2454BOO and correct formula, therefore, is Na2B4O504.8H2O. Borax dissolves in water to give an alkaline solution, Na2B4O77H2O2-NeO4H3BO3. Orthoboric acid on heating. Borax first loses water molecules and swells up. On further heating it turns into a transparent liquid, which solidifies into glass-like material known as borax bead. Na2B4O7.10H2O. Na2B4O72 NaBO2 Sodium B2O3 metabolite boric anhydride. The metabolites of many transition metals have characteristic colors and therefore, borax bead test can be used to identify them in the laboratory. For example, when borax is heated in a Bunsen burner flame with Co on a loop of platinum wire, a blue-colored CoBO22 bead is formed. 1.1.3. 2. Orthoboric acid. Orthoboric acid, H3BO3 is a white crystalline solid, with soapy touch. It is sparingly soluble in water but highly soluble in hot water. It can be prepared by acidifying an aqueous solution of borax, Na2B4O72HCl5H2O2 NaCl4BO3. It is also formed by the hydrolysis reaction with water or dilute acid of most boron compounds, halides, hydrides, etc. It has a 321 The p-block elements problem 11.4 Why is boric acid considered as a weak acid solution? Because it is not able to release H ions on its own. It receives O ions from water molecule to complete its octet and in turn releases H ions. 1,1,3,3-diborane, B2H6. The simplest boron hydride known is diborane. It is prepared by treating boron trifluoride with LiAlH4 and diethyl ether. 4BF33 LiAlH4 2B2H6 3Lith3Alph3. A convenient laboratory method for the preparation of diborane involves the oxidation of sodium borohydride with iodine. 2Nab4I2B2H6 2NiH2 diborane is produced on an industrial scale by the reaction of BF3 with sodium hydride. 326-450K2BF6 NaBH6 NaF diborane is a colorless, highly toxic gas with a BP of 180 K. Diborane catches fire spontaneously upon exposure to air. It burns in oxygen, releasing an enormous amount of energy. 2622321BH3LBO3HO, 1976 kJ/mol VCH. Most of the higher boranes are also spontaneously flammable in air. Boranes are readily hydrolyzed by water to give boric acid. B2H6G6H2OL2BO3Ac6H2G. Diborane undergoes cleavage reactions with Lewis bases L to give borane adducts. BH3LB2H62NMe3-2BH3NMe3B2H62CO2BH3CO. Reaction of ammonia with diborane gives initially B2H6.2NH3, which is formulated as BH2NH3-2BH4. Further heating gives borazine, B3N3H6, known as inorganic benzene in view of its ring structure with alternate BH and NH groups. 26323243362 He3BH6NH3BHNHBH2BNH12H. The structure of diborane is shown in figure 11.2 up. The four terminal hydrogen atoms and the two boron atoms lie in one plane. Above and below this plane, there are two bridging hydrogen atoms. The four terminal BH bonds are regular two-center two-electron bonds, while the two bridge BHB bonds are different and can be described in terms of 3 figure 11.2 of the structure of diborane, B2H6 Fig. 11. 1. Structure of boric acid. The dotted lines represent hydrogen bonds layer structure in which planar BO3 units are joined by hydrogen bonds as shown in Fig. 11.1. Boric acid is a weak monobasic acid. It is not a protonic acid but acts as a Lewis acid by accepting electrons from a hydroxyl ion, BO32HO BO4H3O, on heating. Orthoboric acid above 370 K forms metaboric acid, HBO2, which on further heating yields boric oxide, B2O3. H3BO3HBO2 B2O3. 322 Chemistry Center 2 electron bonds shown in figure 11.2b. Boron also forms a series of hydrodoborates. The most important one is the tetrahedral BH4 ion. Tetrahydrodoborates of several metals are known. Lithium and sodium tetrahydrodoborates, also known as borohydrides, are prepared by the reaction of metal hydrides with B2H6 and diethyl ether. 2MHB2H6-2MBH4M. Lear-Na orthoboric acid is generally used as a mild antiseptic. Aluminium is a bright silvery white metal, with high tensile strength. It has a high electrical and thermal conductivity. On the weight-to-weight basis, the electrical conductivity of aluminium is twice that of copper. Aluminium is used extensively in industry and everyday life. It forms alloys with Cu, Mn, Mg, CnCn. Aluminium and its alloys can be given shapes of pipe, tubes, rods, wires, plates or foils and, therefore, find uses in packing, utensil making, construction, airplane and transportation industry. The use of aluminium and its compounds for domestic purposes is now reduced considerably because of their toxic nature. 11.5 Group 14 elements. The carbon family: carbon, silicon, germanium, tin, lead and flerovium are the members of Group 14. Carbon is the 17th most abundant element by mass in the Earth's crust. It is widely distributed in nature in free as well as in the combined state. In elemental state it is available as coal, graphite and diamond. However, in combined state it is present as metal carbonates, hydrocarbons and carbon dioxide gas 0.03 in air. One can emphatically say that carbon is the most versatile element in the world. Its combination with other elements such as dihydrogen, dioxygen, chlorine and sulfur provides an astonishing array of materials ranging from living tissues to drugs and plastics. Organic chemistry is devoted to carbon-containing compounds. It is an essential constituent of all living organisms. Naturally occurring carbon contains two stable isotopes, 12C and 13C. In addition to these, third isotope, 14C, is also present. It is a radioactive isotope with half-life 5,770 years and used for radiocarbon dating. Silicon is the second 27.7 by mass most abundant element on the Earth's crust and is present in nature in the form of silica and silicates. Silicon is a very important component of ceramics, glass and cement. Germanium exists only in traces. Tin. Both Lib4 and Nad4 are used as reducing agents in organic synthesis. They are useful starting materials for preparing other metal borohydrides. 11.4 Uses of boron and aluminium and their compounds. Boron being extremely hard refractory solid of high melting point, low density and very low electrical conductivity, finds many applications. Boron fibers are used in making bulletproof vest and light composite material for aircraft. The boron 1010B isotope has high ability to absorb neutrons and, therefore, metal borides are used in nuclear industry as protective shields and control rods. The main industrial application of borax and boric acid is in the manufacture of heat-resistant glasses, e.g., Pyrex, glass wool and fiberglass. Borax is also used as a flux for soldering metals, for heat, scratch and stain-resistant glazed coating to earthenwares and as constituent of medicinal soaps. An aqueous solution of figure 11.2b bonding in diborane. Each B atom uses sp3 hybrids for bonding. Out of the 4 sp3 hybrids on each B atom, one is without an electron shown in broken lines. The terminal BH bonds are normal 2-center 2-electron bonds, but the 2 bridge bonds are 3-center 2-electron bonds. The 3-center 2-electron bridge bonds are also referred to as banana bonds. 323 The p-block elements occurs mainly as cassiterite, SNO2 and lead as galena, PBS. Flerovium is synthetically prepared radioactive element. Ultra-pure form of germanium and silicon are used to make transistors and semiconductor devices. Symbol of flerovium is Fl. It has atomic number 114, atomic mass 289 mol1 and electronic configuration Rn5F146D107S27 page 2. It has been prepared only in small amount, its half-life is short and its chemistry has not been established yet. The important atomic and physical properties along with their electronic configuration of the elements of group 14 leaving flerovium are given in table 11.3. Some of the atomic, physical and chemical properties are discussed below. 1.1.5. 1 Electronic configuration. The valence shell electronic configuration of these elements is ns2np2. The inner core of the electronic configuration of elements in this group also differs. 1.1.5. 2 Covalent radius. There is a considerable increase in covalent radius from C to C. Thereafter from C to PB a small increase in radius is observed. This is due to the presence of completely filled E and F orbitals in heavier members. 1.1.5. 3 Ionization enthalpy. The first ionization enthalpy of group 14 members is higher than the corresponding members of group 13. The influence of inner core electrons is visible here also. In general, the ionization enthalpy decreases down the group. Small decrease in I from C to J to Sn and slight increase in I from Sn to Pb is the consequence of poor shielding effect of intervening D and F orbitals and increase in size of the atom. 1.1.5. 4 Electronegativity. Due to small size, the elements of this group are slightly more electronegative than group 13 elements. The electronegativity values for elements from C to Pb are almost the same. Table 11.3 Atomic and physical properties of group 14 elements of for MiV oxidation state, B6 coordination, C Pauling scale, D293 K, E for diamond, for graphite. Density is 2.22, form stable at room temperature. Atomic number 614325082 atomic mass G mol -112.0128.0972.60 207.2 electronic E2S22 page 2 net 3S23 page 2 R3D10 4S24 page 2 KR4D10 5S25 page 2 XE4F14 5D10 6S26 page 2 configuration covalent, radius PM 77, 118, 122, 140, 146, ionic radius M4 PMB 40 53 69 78 ionic radius M2 PMB 73 118 119 ionization I1, 1086, 786, 761, 708, 715 enthalpy, I22, 3521, 5771, 5371, 4111, 450 K, J mol 1 I34, 6203, 2283, 3002, 9423, 081I, 46, 2204, 3544, 409, 3929, 4082, electronegativity C2.51.81.81.81.9 density DGCM-3 3.51E2.345.327.26 F 11.34 melting point K 4373 1693 1218 505 600 boiling point K 3550 3123 2896 2024 electrical resistivity 1014-10 16 50 50 10-5 2x 10-5 ohm cm 293 K, carbon silicon germanium tin lead CC jazz NPB element property. 324 Chemistry 115. 5 Physical properties. All members of group 14 are solids. Carbon and silicon are nonmetals. Germanium is a metalloid, whereas tin and lead are soft metals with low melting points. Melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. 115. 6 Chemical properties. Oxidation states and trends in chemical reactivity. The group 14 elements have 4 electrons in outermost shell. The common oxidation states exhibited by these elements are 4 and 2. Carbon also exhibits negative oxidation states. Since the sum of the first 4 ionization enthalpies is very high, compounds in 4 oxidation state are generally covalent in nature. In heavier members, the tendency to show to oxidation state increases in the sequence gel, Sn, Pb. It is due to the inability of Ns2 electrons of valence shell to participate in bonding. The relative stabilities of these 2 oxidation states vary down the group. Carbon and silicon mostly show 4 oxidation state. Germanium forms stable compounds in 4 state and only few compounds in 2 state. Tin forms compounds in both oxidation states. Sn in 2 state is a reducing agent. Lead compounds in 2 state are stable and in 4 state are strong oxidizing agents. In tetravalent state, the number of electrons around the central atom in a molecule, e.g., carbon and CCl4, is 8. Being electron-precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalence more than 4, other elements of a group can do so. It is because of the presence of d orbital in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, the species like CF62, JCl62, SNO62 exist where the hybridization of the central atom is sp3d2. I reactivity towards oxygen. All members when heated in oxygen form oxides. There are mainly 2 types of oxides, that is, monoxide and dioxide of formula MO and MO2 respectively. CO only exists at high temperature. Oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation states. The dioxides CO2, CO2 and GO2 are acidic, whereas SNO2 and PbO2 are amphoteric in nature. Among monoxides, CO is neutral, GO is distinctly acidic, whereas SNO and PbO are amphoteric. Problem 11.5. Select the member S of group 14 that I forms the most acidic dioxide. 2 is commonly found in 2 oxidation state, 3 used as semiconductor. Solution: I carbon 2 lead 3 silicon and germanium 2 reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas 222SN2HO. SNO2H. Lead is unaffected by water, probably because of a protective oxide film formation. 3 reactivity towards halogen. These elements can form halides of formula MX2 and MX4 where XF, Cl, Br, I. Except carbon, all other members react directly with halogen under suitable condition to make halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergoes sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are SNF4 and PbF4, which are ionic in nature. PbI4 does not exist because PbI bond initially formed during the reaction does not release enough energy to unpair 6 s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Heavier members J to Pb are able to make halides of formula MX2. Stability of D halides increases down the group. Considering the thermal and chemical stability, JX4 is more stable than JX2, whereas PbX2 is more than PbX4. Except CCl4, other tetrachlorides are easily hydrolyzed. 325 The p-block elements by water because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Hydrolysis can be understood by taking the example of CCl4. It undergoes hydrolysis by initially accepting lone pair of electrons from water molecule in d orbitals of C. Finally leading to the formation of CO4 as shown below. Carbon also has unique ability to form multiple bonds with itself and with other atoms of small size and high electronegativity. Few examples of multiple bonding are CC, CC, CO, CS, and CN. Heavier elements do not form bonds because their atomic orbitals are too large and diffuse to have effective overlapping. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. This is because CC bonds are very strong. Down the group the size increases and electronegativity decreases, and, thereby, tendency to show catenation decreases. This can be clearly seen from bond enthalpies values. The order of catenation is C, C, JSN. Lead does not show catenation. Bond enthalpy Kj mol -1 cc 348 cc 297 Jj 260 SN 240 due to property of catenation and bond formation. Carbon is able to show allotropic forms. 11.7 Allotropes of carbon. Carbon exhibits many allotropic forms, both crystalline as well as amorphous. Diamond and graphite are two well-known crystalline forms of carbon. In 1985, third form of carbon known as fullerenes was discovered by H. W. Crotto, E. Smalley and R. F. Curl. For this discovery they were awarded the Nobel Prize in 1996. 117. 1 Diamond. It has a crystalline lattice. In diamond each carbon atom undergoes sp3 hybridization and linked to 4 other carbon atoms by using hybridized orbitals in tetrahedral fashion. The CC bond length is 154 pm. The structure extends in space and produces a rigid three-dimensional network of carbon atoms. In this problem 11.6 if 6.2 is known whereas CCl6.2 not, give possible reasons. Solution. The main reasons are, I6 large chloride ions cannot be accommodated around C4 due to limitation of its size. 2 Interaction between lone pair of chloride ion and C4 is not very strong. 11.6 Important trends and anomalous behavior of carbon. Like first member of other groups, carbon also differs from rest of the members of its group. It is due to its smaller size, higher electronegativity, higher ionization enthalpy and unavailability of d orbitals. In carbon, only s and p orbitals are available for bonding and, therefore, it can accommodate only 4 pairs of electrons around it. This would limit the maximum covalence to 4 whereas other members can expand their covalence due to the presence of d orbitals. 326 Chemistry structure. Figure 11.3 Directional covalent bonds are present throughout the lattice. It is very difficult to break extended covalent bonding and, therefore, diamond is the hardest substance on the Earth. It is used as an abrasive for sharpening hard tools, in making dyes and in the manufacture of tungsten filaments for electric light bulbs. Problem 11.7 Diamond is covalent, yet it has high melting point. Why? Solution. Diamond has a three-dimensional network involving strong CC bonds, which are very difficult to break and, in turn has high melting point. 117. Graphite. Graphite has layered structure. Figure 11.4. Layers are held by van der Waals forces and distance between 2 layers is 340 pm. Each layer is composed of planar hexagonal rings of carbon atoms. CC bond length within the layer is 141.5 pm. Each carbon atom in hexagonal ring undergoes sp2 hybridization and makes 3 sigma bonds with 3 neighboring carbon atoms. Fourth electron forms a Greek letter pi bond. The electrons are delocalized over the whole sheet. Electrons are mobile and, therefore, graphite conducts electricity along the sheet. Graphite cleaves easily between the layers and, therefore, it is very soft and slippery. For this reason graphite is used as a dry lubricant in machines running at high temperature, where oil cannot be used as a lubricant. 117. Fullerenes. Fullerenes are made by the heating of graphite in an electric arc in the presence of inert gases such as helium or argon. The sooty material formed by condensation of vaporized C and small molecules consists of mainly C60 with smaller quantity of C70 and traces of fullerenes consisting of even number of carbon atoms up to 350 or above. Fullerenes are the only pure form of carbon because they have smooth structure without having dangling bonds. Fullerenes are cage-like molecules. C60 molecule has a shape like soccer ball and called Buckminster fullerene Fig. 11.5. It contains 26 membered rings and 12 5-membered rings. A 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. All the carbon atoms are equal and they undergo sp2 hybridization. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electron at each carbon is delocalized in figure 11.3. The structure of diamond. Figure 11.4. The structure of graphite. 327 The p-block elements molecular orbitals, which in turn give aromatic character to molecule. This ball-shaped molecule has 60 vertices and each one is occupied by 1 carbon atom, and it also contains both single and double bonds with CC distances of 143.5 pm and 138.3 pm respectively. Spherical fullerenes are also called buggy balls and short filters to remove organic contaminators and in air conditioning system to control odor. Carbon black is used as black pigment in black ink and as filler in automobile tires. Coke is used as a fuel and largely as a reducing agent in metallurgy. Diamond is a precious stone and used in jewelry. It is measured in carats. 1 carat 200 milligrams. 11.8 Some important compounds of carbon and silicon. Oxides of carbon. 2 important oxides of carbon are carbon monoxide, CO, and carbon dioxide, CO2. 118. 1 carbon monoxide. Direct oxidation of C and limited supply of oxygen or air yields carbon monoxide. 22 CSOG2COG. On small scale pure CO is prepared by dehydration of formic acid with concentrated H2SO4 at 373 K, 242 373 K conc HSOCU HOCO. On commercial scale it is prepared by the passage of steam over hot coke. The mixture of CO and H2 thus produced is known as water gas or synthesis gas. 22 473-1273, KCSHOGCOGHG water gas. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. 222-1273 K2CSOG4 and G2COG4 and G. Producer gas. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas or producer gas can undergo further combustion, forming carbon dioxide with the liberation of heat. Carbon monoxide is a colorless, odorless and almost water-insoluble gas. It is a powerful reducing agent and reduces almost all metal oxides other than those of the alkali and alkaline earth metals, aluminium and a few transition metals. This property of figure 11.5, the structure of C60, Buckminster fullerene. Note that molecule has the shape of a soccer ball football. It is very important to know that graphite is thermodynamically most stable allotrope of carbon and, therefore, FHV of graphite is taken as 0. FHV values of diamond and fullerene, C60 are 1.90 and 38.1 kJ-mol-1, respectively. Other forms of elemental carbon like carbon black, coke, and charcoal are all impure forms of graphite or fullerenes. Carbon black is obtained by burning hydrocarbons in a limited supply of air. Charcoal and coke are obtained by heating wood or coal respectively at high temperatures in the absence of air. 117. 4 uses of carbon. Graphite fibers embedded in plastic material form high-strength, lightweight composites. The composites are used in products such as tennis rackets, fishing rods, aircrafts and canoes. Being good conductor, graphite is used for electrodes in batteries and industrial electrolysis. Crucibles made from graphite are inert to dilute acids and alkalis. Being highly porous, activated charcoal is used in adsorbing poisonous gases, also used in water. 328. Chemistry. CO is used in the extraction of many metals from their oxides. Ors 2322 FeOS3COG2 Fe3COGZNOS and CO molecule. There are 1 sigma and 2 Greek letter pi bonds between carbon and oxygen, CO. Because of the presence of a lone pair on carbon, CO molecule acts as a donor and reacts with certain metals when heated to form metal carbonyls. The highly poisonous nature of CO arises because of its ability to form a complex with hemoglobin, which is about 300 times more stable than the oxygen-hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen round the body and ultimately resulting in death. 118. 2 Carbon dioxide. It is prepared by complete combustion of carbon and carbon-containing fuels in excess of air. 22-CSOGCOG4 222-CHG2OGCOG2HOG. In the laboratory it is conveniently prepared by the action of dilute HCl on calcium carbonate. CaCO3S2HCl at CaCl2AxCO2GH2OL. On commercial scale it is obtained by heating limestone. It is a colorless and odorless gas. Its low solubility in water makes it of immense biochemical and geochemical importance. With water, it forms carbonic acid. H2CO3, which is a weak dibasic acid and dissociates in 2 steps. H2CO3 AC H2OL HCO3 AC H3O AC HCO3 AC H2OL CO3 2 AC H3O AC H2CO3 HCO3. Buffer system helps to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, it combines with alkalis to form metal carbonates. Carbon dioxide, which is normally present to the extent of 0.03 by volume in the atmosphere, is removed from it by the process known as photosynthesis. It is the process by which green plants convert atmospheric CO2 into carbohydrates such as glucose. The overall chemical change can be expressed as 2,2,6,12,622H chlorophyll 6CO12HOCHO6O6HO Greek letter nu. By this process plants make food for themselves as well as for animals and human beings. Unlike CO, it is not poisonous, but the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture in recent years seem to increase the CO2 content of the atmosphere. This may lead to increase in greenhouse effect and thus, raise the temperature of the atmosphere, which might have serious consequences. Carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous CO2 is extensively used to carbonate soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. A substantial amount of CO2 is used to manufacture urea. In CO2 molecule, carbon atom undergoes sp hybridization. 2 sp hybridized orbitals of carbon atom overlap with 2 p orbitals of oxygen atoms to make 2 sigma bonds, while other 2 electrons of carbon atom are involved in bonding with oxygen atom. This results in its linear shape with both CO bonds of equal length 115 pm with no dipole moment. The resonance structures are shown below. Resonance structures of carbon dioxide 118. 3 Silicon dioxide, CO2 95 of the Earth's crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite and tritomite are some of the crystalline forms of silica, and they are interconvertible at suitable temperature. Silicon dioxide is a covalent, three-dimensional. 329 The p-block elements network solid in which each silicon atom is covalently bonded in a tetrahedral manner to 4 oxygen atoms. Each oxygen atom in turn covalently bonded to another silicon atoms as shown in diagram figure 11.6. Each corner is shared with another tetrahedron. The entire crystal may be considered as giant molecule in which 8 membered rings are formed with alternate silicon and oxygen atoms. Substituted chlorosylane of formula MeCCl3, Me2CCl2, Me3CCl with small amount of Me4Cr formed. Hydrolysis of dimethylgichlorosylane, CH32CCl2 followed by condensation polymerization yields straight chain polymers. The chain length of the polymer can be controlled by adding CH33CCl which blocks the ends as shown below, Fig. 11.6 Three-dimensional structure of CO2 silica in its normal form is almost non-reactive because of very high CO bond enthalpy. It resists the attack by halogens, dihydrogen and most of the acids and metals even at elevated temperatures. However, it is attacked by HF and NaO, CO2 2-NaO Na2CO3 H2O CO2 4HF SIT4 2H2O. Quartz is extensively used as a piezoelectric material. It has made possible to develop extremely accurate clocks. Modern radio and television broadcasting and mobile radio communications. Silica gel is used as a drying agent and as a support for chromatographic materials and catalysts. Kieselguhr, an amorphous form of silica, is used in filtration plants. 1,1,8. 4 silicones. They are a group of organosilicon polymers, which have R2CO as a repeating unit. The starting materials for the manufacture of silicones are alkyl or aryl substituted silicon chlorides, RnCCl4n, where R is alkyl or aryl group. When methyl chloride reacts with silicon in the presence of copper as a catalyst at a temperature 573 K, various types of methyl 330 chemistry silicones being surrounded by nonpolar alkyl groups are water-repelling in nature. They have in general high thermal stability, high dielectric strength and resistance to oxidation and chemicals. They have wide applications. They are used as sealant, greases, electrical insulators and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. Problem 11.8 What are silicone solutions? Simple silicones consist of chains in which alkyl or phenyl groups occupy the remaining bonding positions on each silicon. They are hydrophobic, water repellent in nature. 1,1,8. 5 silicates. A large number of silicates minerals exist in nature. Some of the examples are feldspar, zeolites, mica and asbestos. The basic structural unit of silicates is CO4 figure 11.7 in which silicon atom is bonded to 4 oxygen atoms in tetrahedron fashion. In silicates either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3 or 4 oxygen atoms per silicate units. When silicate units are linked together, they form chain, ring, sheet or three-dimensional structures. Negative charge on silicate structure is neutralized by positively charged metal ions. If all the 4 corners are shared with other tetrahedral units, three-dimensional network is formed. 2 important man-made silicates are glass and cement. 1,1,8. 6 zeolites. If aluminium atoms replace few silicon atoms in three-dimensional network of silicon dioxide, overall structure known as aluminosilicate, acquires a negative charge. Cations such as Na, K or Ca2 balance the negative charge. Examples are feldspar and zeolites. Zeolites are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization, e.g., ZSM5, a type of zeolite used to convert alcohols directly into gasoline. Hydrated zeolites are used as ion exchangers in softening of hard water. Summary: P-block of the periodic table is unique in terms of having all types of elements, metals, nonmetals and metalloids. There are 6 groups of p-block elements in the periodic table numbering from 13 to 18. Their valence shell electronic configuration is ns2np1-6 except for He. Differences in the inner core of their electronic configuration greatly influence their physical and chemical properties. As a consequence of this, a lot of variation in properties among these elements is observed. In addition to the group oxidation state, these elements show other oxidation states differing from the total number of valence electrons by unit of 2. While the group oxidation state is the most stable for the lighter elements of the group, lower oxidation states become progressively more stable for the heavier elements. The combined effect of size and availability of d orbitals considerably ab figure 11.7 a tetrahedral structure of CO44 anion, B representation of CO44 unit. 331 The p-block elements influences the ability of these elements to form Greek letter pi bonds, while the lighter elements form Greek letter pi Greek letter pi Greek letter pi Greek letter pipe Greek letter pi Greek letter pi Greek letter pi Greek letter pi bonds. The heavier ones form Greek letter pi Greek letter pi Greek letter pi Greek letter pipe Greek letter pi Greek letter pi Greek letter pi Greek letter pi or Greek letter pi 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 bonds. Absence of d orbital in second period elements limits their maximum covalence to 4 while heavier ones can exceed this limit. Boron is a typical nonmetal and the other members are metals. The availability of 3 valence electrons 2s22 page 1 for covalent bond formation using 4 orbitals 2s, 2px, 2pi and 2pz leads to the so-called electron deficiency in boron compounds. This deficiency makes them good electron acceptor and thus boron compounds behave as Lewis acids. Boron forms covalent molecular compounds with dihydrogenous boranes, the simplest of which is diborane, B2H6. Diborane contains 2 bridging hydrogen atoms between 2 boron atoms. These bridge bonds are considered to be 3-center 2-electron bonds. The important compounds of boron with dioxygen are boric acid and borax. Boric acid, BO3 is a weak monobasic acid. It acts as a Lewis acid by accepting electrons from hydroxyl ion. Borax is a white crystalline solid of formula Na2B4O5O4, 8H2O. The borax B test gives characteristic colors of transition metals. Aluminium exhibits 3 oxidation state. With heavier elements 1 oxidation state gets progressively stabilized on going down the group. This is a consequence of the so-called inert pair effect. Carbon is a typical nonmetal forming covalent bonds employing all its 4 valence electrons 2s22 page 2. It shows the property of catenation, the ability to form chains or rings, not only with CC single bonds but also with multiple bonds CC or CC. The tendency to catenation decreases as C, Jas N, Pb. Carbon provides one of the best examples of allotropy. 3 important allotropes of carbon are diamond, graphite and fullerenes. The members of the carbon family mainly exhibit 4 N2 oxidation states. Compounds in 4 oxidation states are generally covalent in nature. The tendency to show 2 oxidation state increases among heavier elements. Lead in 2 state is stable whereas in 4 oxidation state it is a strong oxidizing agent. Carbon also exhibits negative oxidation states. It forms 2 important oxides, CO and CO2. Carbon monoxide is neutral whereas CO2 is acidic in nature. Carbon monoxide having lone pair of electrons on C forms metal carbonyls. It is deadly poisonous due to higher stability of its hemoglobin complex as compared to that of oxyhemoglobin complex. Carbon dioxide as such is not toxic. However, increased content of CO2 in atmosphere due to combustion of fossil fuels and decomposition of limestone is feared to cause increase in greenhouse effect. This, in turn, raises the temperature of the atmosphere and causes serious complications. Silica, silicates and silicones are important class of compounds and find applications in industry and technology. Exercises 11.1 discuss the pattern of variation in the oxidation states of IB to TL and 2C to PB. 11.2 How can you explain higher stability of BCl3 as compared to TlCl3? 11.3 Why does boron trifluoride behave as a Lewis acid? 11.4 Consider the compounds, BCl3 and CCl4. How will they behave with water? Justify. 11.5 Is boric acid a protic acid? Explain. 11.6 Explain what happens when boric acid is heated. 11.7 Describe the shapes of BF3 and BH4. Assign the hybridization of boron in these species. 11.8 Write reactions to justify amphoteric nature of aluminium. 332 Chemistry. 11.9 What are electron deficient compounds? Are BCl3 and CCl4 electron deficient species? Explain. 11.10 Write the resonance structures of CO32 and HCO3. 11.11 What is the state of hybridization of carbon in a CO32b diamond C graphite? 11.12 Explain the difference in properties of diamond and graphite on the basis of their structures. 11.13 Rationalize the given statements and give chemical reactions. Lead 2 chloride reacts with Cl2 to give PbCl4. Lead IV chloride is highly unstable towards heat. Lead is known not to form an iodide, PbI4. 11.14 Suggest reasons why the BF bond lengths in BF3 130 pm and BF4 143 pm differ. 11.15 If BCl bond has a dipole moment, explain why BCl3 molecule has zero dipole moment. 11.16 Aluminium trifluoride is insoluble in anhydrous HF but dissolves on addition of Nef. Aluminium trifluoride precipitates out of the resulting solution when gaseous BF3 is bubbled through. Give reasons. 11.17 Suggest a reason as to why CO is poisonous. 11.18 How is the excessive content of CO2 responsible for global warming? 11.19 Explain structures of diborane and boric acid. 11.20 What happens when a borax is heated strongly? B. Boric acid is added to water. C. Aluminium is treated with dilute NaO. D. BF3 is reacted with ammonia. 11.21 Explain the following reactions. A silicon is heated with methyl chloride at high temperature in the presence of copper. B. Silicon dioxide is treated with hydrogen fluoride. C. CO is heated with CNO. Dehydrated alumina is treated with aqueous NaO solution. 11.22 Give reasons. I conc. HNO3 can be transported in aluminium container. 2. A mixture of dilute NaO and aluminium pieces is used to open drain. 3. Graphite is used as lubricant. IV diamond is used as an abrasive. V. Aluminium alloys are used to make aircraft body. V. Aluminium utensils should not be kept in water overnight. 7. Aluminium wire is used to make transmission cables. 11.23 Explain why is there a phenomenal decrease in ionization enthalpy from carbon to silicon. 11.24 How would you explain the lower atomic radius of Ga as compared to Al? 11.25 What are allotropes? Sketch the structure of two allotropes of carbon, namely diamond and graphite. What is the impact of structure on physical properties of two allotropes? 333 The p-block elements. 11.26 Classify following oxides as neutral, acidic, basic or amphoteric. CO, B2O3, CO2, CO2, Al2O3, PbO2, Tl2O3b. Write suitable chemical equations to show their nature. 11.27 In some of the reactions thallium resembles aluminium, whereas in others it resembles with group I metals. Support this statement by giving some evidences. 11.28 When metal X is treated with sodium hydroxide, a white precipitate A is obtained, which is soluble in excess of NaO to give soluble complex B. Compound A is soluble in dilute HCl to form compound C. The compound A when heated strongly gives D, which is used to extract metal. Identify X, A, B, C and D. Write suitable equations to support their identities. 11.29 What do you understand by a inert pair effect? B. Allotropy and C. Catenation. 11.30 A certain salt X gives the following results. I. Its aqueous solution is alkaline to litmus. 2. It swells up to a glassy material Y on strong heating. 3. When conc. H2SO4 is added to a hot solution of X, white crystal of an acid Z separates out. Write equations for all the above reactions and identify X, Y and Z. 11.31 Write balanced equations for IBF3 Li2B2H6H2O3 Na B2H6 IVH3BO3 Al NaO VB2H6NH3. 11.32 Give one method for industrial preparation and one for laboratory preparation of CO and CO2 each. 11.33 An aqueous solution of borax is a neutral. B. Amphoteric. C. Basic. D. Acidic. 11.34 Boric acid is polymeric due to its acidic nature. B. The presence of hydrogen bonds. C. Its monobasic nature. D. Its geometry. 11.35 The type of hybridization of boron and diborane is a sp-bsp2-csp3-ddSp2. 11.36 Thermodynamically the most stable form of carbon is a diamond. B. Graphite. C. Fullerenes. D. Coal. 11.37 Elements of group 14 A exhibit oxidation state of 4 only. B. Exhibit oxidation state of 2 and 4. C. Form M2 and M4 ions. D. Form M2 and M4 ions. 11.38 If the starting material for the manufacture of silicones is RsICl3, write the structure of the product formed. Organic chemistry, some basic principles and techniques. After studying this unit, you will be able to understand reasons for tetravalence of carbon and shapes of organic molecules. Write structures of organic molecules in various ways. Classify the organic compounds. Name the compounds according to IUPAC system of nomenclature and also derive their structures from the given names. Understand the concept of organic reaction mechanism. Explain the influence of electronic displacements on structure and reactivity of organic compounds. Recognize the types of organic reactions. Learn the techniques of purification of organic compounds. Write the chemical reactions involved in the qualitative analysis of organic compounds. Understand the principles involved in quantitative analysis of organic compounds. In the previous unit you have learnt that the element carbon has the unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. This unit incorporates some basic principles and techniques of analysis required for understanding the formation and properties of organic compounds. 12.1 General Introduction. Organic compounds are vital for sustaining life on Earth and include complex molecules like genetic information bearing deoxyribonucleic acid DNA and proteins that constitute essential compounds of our blood, muscles and skin. Organic compounds appear in materials like clothing, fuels, polymers, dyes and medicines. These are some of the important areas of application of these compounds. Science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. However, this notion was rejected in 1828 when F. Wohler synthesized an organic compound, urea, from an inorganic compound, ammonium cyanate. 4,2-HCNONHCONH ammonium cyanate urea. The pioneering synthesis of acetic acid by Kolbe 1845 and that of methane by Berthelot 1856 showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. Unit 12. 335 Organic Chemistry, Some Basic Principles and Techniques. The development of electronic theory of covalent bonding ushered organic chemistry into its modern shape. 12.2 Tetravalence of carbon, Shapes of organic compounds. 1. 1. The shapes of carbon compounds. The knowledge of fundamental concepts of molecular structure helps in understanding and predicting the properties of organic compounds. You have already learned theories of valency and molecular structure in Unit 4. Also, you already know that tetravalence of carbon and the formation of covalent bonds by it are explained in terms of its electronic configuration and the hybridization of s and p orbitals. It may be recalled that formation and the shapes of molecules like methane CH4, ethene C2H4, ethene C2H2 are explained in terms of the use of sp3, sp2 and sp hybrid orbitals by carbon atoms in the respective molecules. Hybridization influences the bond length and bond enthalpy strength in compounds. The sp hybrid orbital contains more s character and hence it is closer to its nucleus and forms shorter and stronger bonds than the sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3 and, hence, the length and enthalpy of the bonds it forms, are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50 s character is more electronegative than that possessing sp2 or sp3 hybridized orbitals. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned, about which you will learn in later units. 1. 2. Some characteristic features of Greek letter pi 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 bonds in a Greek letter pi bond formation. Parallel orientation of the two p orbitals on adjacent atoms is necessary for a proper sideways overlap. Thus, in H2CCH2 molecule all the atoms must be in the same plane. The p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. Rotation of one CH2 fragment with respect to other interferes with maximum overlap of p orbitals and, therefore, such rotation about carbon-carbon double bond CC is restricted. The electron charge cloud of the Greek letter pi bond is located above and below the plane of bonding atoms. This results in the electrons being easily available to the attacking reagents. In general, Greek letter pi bonds provide the most reactive centers in the molecules containing multiple bonds. Problem 12.1 How many Greek letter sigma and Greek letter pi bonds are present in each of the following molecules? HCCCHCHCH3BCH2CCHCH3 Solution A Greek letter sigma C, 4, Greek letter sigma CH, 6, Greek letter pi CC:1, Greek letter pi CC2B Greek letter sigma C, 3, Greek letter sigma CH, 6, Greek letter pi CC, 2. Problem 12.2 What is the type of hybridization of each carbon in the following compounds? A CH3Cl, BCH32CO, CCH3CN, DHCONH2, ECH3CHCHCN Solution A sp3, BSP3, sp2, CSP3, sp, DSP2, ESP3, sp2, sp2, sp. Problem 12.3 Write the state of hybridization of carbon in the following compounds and shapes of each of the molecules. A H2CO, BCH3F, CHCN, solution. A sp2 hybridized carbon, trigonal planar, VSP3 hybridized carbon. Tetrahedral, CSP hybridized carbon, linear. 336 Chemistry 12.3 Structural representations of organic compounds 1, 2, 3. 1. Complete, condensed and bond line structural formula. Structures of organic compounds are represented in several ways. The Lewis structure or dot structure, dash structure, condensed structure and bond line structural formulas are some of the specific types. The Lewis structures, however, can be simplified by representing the two-electron covalent bond by a dash. Such a structural formula focuses on the electrons involved in bond formation. A single dash represents a single bond, double dash is used for double bond and a triple dash represents triple bond. Lone pairs of electrons on heteroatoms e.g., oxygen, nitrogen, sulfur, halogens etc. may or may not be shown. Thus, ethane C2H6, ethene C2H4, ethene C2H2 and methanol CH3O can be represented by the following structural formulas. Such structural representations are called complete structural formulas. Similarly, CH3CH2CH2CH2CH2CH2CH2CH3 can be further condensed to CH3CH26CH3. For further simplification, organic chemists use another way of representing the structures, in which only lines are used. In this bond line structural representation of organic compounds, carbon and hydrogen atoms are not shown and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. The terminals denote methyl CH3 groups unless indicated otherwise by a functional group, while the line junctions denote carbon atoms bonded to appropriate number of hydrogens required to satisfy the valency of the carbon atoms. Some of the examples are represented as follows. I3-methyloctane can be represented in various forms as a CH3CH2CH2CH2CH2CH2CH3CH3. These structural formulas can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by indicating the number of identical groups attached to an atom by a subscript. The resulting expression of the compound is called a condensed structural formula. Thus, ethane, ethene and methanol can be written as CH3CH3H2CCH2HCCHCH3O ethene methanol. Two various ways of representing 2-bromobutane are a CH3CHBr CH2CH3BCBC. 337 Organic chemistry, some basic principles and techniques in cyclic compounds. The bond line formulas may be given as follows. Cyclopropane, cyclopentane, chlorocyclohexane. Problem 12.4. Expand each of the following condensed formulas into their complete structural formulas. A CH3CH2CH2BCH3CHCHCH2 solution. B solution condensed formula. A HOCH2 2 B HCN2 bond line formula. A B problem 12.5. For each of the following compounds, write a condensed formula and also their bond line formula. A HOCH2CH2CH2CH3CH3CH3B at problem 12.6. Expand each of the following bond line formulas to show all the atoms including carbon and hydrogen. A BCD solutio. 338 Chemistry framework model. Ball and stick model. Space filling model. Figure 12.212. 3. 2 three-dimensional representation of organic molecules. The three-dimensional 3D structure of organic molecules can be represented on paper by using certain conventions. For example, by using solid and dashed wedge formula, the 3D image of a molecule from a two-dimensional picture can be perceived. In these formulas, the solid wedge is used to indicate a bond projecting out of the plane of paper towards the observer. The dashed wedge is used to depict the bond projecting out of the plane of the paper and away from the observer. Wedges are shown in such a way that the broad end of the wedge is towards the observer. The bonds lying in plane of the paper are depicted by using a normal line. 3D representation of methane molecule on paper has been shown in figure 12.1, Fig. 12.1. Wedge and dash representation of CH4 molecular models. Molecular models are physical devices that are used for a better visualization and perception of three-dimensional shapes of organic molecules. These are made of wood, plastic or metal and are commercially available. Commonly 3 types of molecular models are used: 1 framework model, 2 ball and stick model, and 3 space filling model. In the framework model, only the bonds connecting the atoms of the molecule and not the atoms themselves are shown. This model emphasizes the pattern of bonds of the molecule while ignoring the size of atoms. In the ball and stick model, both the atoms and the bonds are shown. Balls represent atoms and the stick denotes a bond. Compounds containing CCEG, ethene can best be represented by using springs in place of sticks. These models are referred to as ball and spring model. The space filling model emphasizes the relative size of each atom based on its van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphics can also be used for molecular modeling. 339 Organic chemistry, some basic principles and techniques. 12.4 Classification of organic compounds. The existing large number of organic compounds and their ever-increasing numbers has made it necessary to classify them on the basis of their structures. Organic compounds are broadly classified as follows: IA cyclic or open-chain compounds. These compounds are also called as aliphatic compounds and consist of straight or branched chain compounds. For example, Homocyclic, cyclopropane, cyclohexane, cyclohexene. Sometimes atoms other than carbon are also present in the ring. Heterocyclic. Tetrahydrofuran given below is an example of this type of compound. Tetrahydrofuran. These exhibit some of the properties similar to those of aliphatic compounds. B. Aromatic compounds. Aromatic compounds are special types of compounds. You will learn about these compounds in detail in Unit 13. These include benzene and other related ring compounds. Benzenoid, like alicyclic compounds, aromatic compounds may also have heteroatom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of various types of aromatic compounds are benzenoid aromatic compounds: benzene, aniline, naphthalene. Non-benzenoid compound: tropone, isobutane, acetaldehyde, acetic acid, CH3, ethane. 2 cyclic or closed chain or ring compounds. Alicyclic compounds: alicyclic, aliphatic, cyclic compounds contain carbon atoms joined in the form of a ring. 340 Chemistry. Heterocyclic aromatic compounds: furan, thiophene, pyridine. Organic compounds can also be classified on the basis of functional groups into families or homologous series. 1, 2, 4. 1 functional group. The functional group is an atom or a group of atoms joined to the carbon chain which is responsible for the characteristic chemical properties of the organic compounds. The examples are hydroxyl group O, aldehyde group CHO, and carboxylic acid group CO, etc. 1, 2, 4. 2 homologous series. A group or a series of organic compounds each containing a characteristic functional group forms a homologous series, and the members of the series are called homologs. The members of a homologous series can be represented by general molecular formula, and the successive members differ from each other in molecular formula by a CH2 unit. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, haloalkanes, alkanols, alkanones, alkanoic acids, amines, etc. It is also possible that a compound contains 2 or more identical or different functional groups. This gives rise to polyfunctional compounds. 12.5 Nomenclature of organic compounds. Organic chemistry deals with millions of compounds. In order to clearly identify them, a systematic method of naming has been developed and is known as the IUPAC, International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned names based on their origin or certain properties. For instance, citric acid is named so because it is found in citrus fruits, and the acid found in red ant is named formic acid since the Latin word for ant is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster fullerene is a common name given to the newly discovered C60 cluster, a form of carbon, noting its structural similarity to the geodesic domes popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names of some organic compounds are given in Table 12.1. Table 12.1 Common or trivial names of some organic compounds. 1, 2, 5. 1. The IUPAC system of nomenclature. A systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional group S attached to it. See the example given below. 341 Organic chemistry. Some basic principles and techniques. By further using prefixes and suffixes, the parent name can be modified to obtain the actual name. Compounds containing carbon and hydrogen only are called hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bonds. The IUPAC name for a homologous series of such compounds is alkane. Para from Latin, little affinity was the earlier name given to these compounds. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. 1, 2, 5. 2 IUPAC nomenclature of alkane straight-chain hydrocarbons. The names of such compounds are based on their chain structure and end with suffix ane and carrier prefix indicating the number of carbon atoms present in the chain, except from CH4 to C4H10, where the prefixes are derived from trivial names. The IUPAC names of some straight-chain saturated hydrocarbons are given in Table 12.2. The alkanes in Table 12.2 differ from each other by merely the number of CH2 groups in the chain. They are homologs of alkane series. In order to name such compounds, the names of alkyl groups are prefixed to the name of parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen atom from carbon. Thus, CH4 becomes CH3 and is called methyl group. An alkyl group is named by substituting il for ane in the corresponding alkane. Some alkyl groups are listed in Table 12.3. Table 12.3 Some alkyl groups. Table 12.2 IUPAC names of some unbranched saturated hydrocarbons. Branched chain hydrocarbons. In a branched chain compound, small chains of carbon atoms are attached at one or more carbon atoms of the parent chain. the small carbon chain's branches are called alkyl groups. For example, CH3CH, CH2, CH3CH3CH, CH2, CH, CH3CH3CH2, CH3CH3AB. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as Me, ethyl is Et, propyl is PR and butyl is Bu. The alkyl groups can be branched also. Thus, propyl and butyl groups can have branched structures as shown below. CH3CH, CH3CH2, CH3CH, CH2, CH3, CH3 isopropyl sec butyl isobutyl CH3, CH3, CH3 CH2, CH3 tert butyl neopentyl. Common branched groups have specific trivial names. For example, the propyl groups can either be N-propyl group or isopropyl group. The branched butyl groups are called sec-butyl, isobutyl and tert-butyl group. We also encounter the structural unit, CH2CCH33, which is called neopentyl group. Nomenclature of branched chain alkanes. We encounter a number of branched chain alkanes. The rules for naming them are given below. 342 Chemistry separated from the groups by hyphens and there is no break between methyl and nonane 4. If two or more identical substituent groups are present, then the numbers are separated by commas. The names of identical substituents are not repeated. Instead, prefixes such as D for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, etc. are used. While writing the name of the substituents in alphabetical order, these prefixes, however, are not considered. Thus, the following compounds are named as CH3CH3CH3CH3CH3CH3CH2CH3CH3CH3 4-dimethylpentane 2, 4-trimethylpentane H3CH2CCH3CH2CH2CH2CH3CH3 3-ethyl 4-dimethylheptane 5. If the two substituents are found in equivalent positions, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyloctane and not 6-ethyl 3-methyloctane 1 2 3 4 5 6 7 8 CH3CH2 CH2CH2 CH2CH2 CH3 6. The branched alkyl groups can be named by following the above-mentioned procedures. However, the carbon atom of the branch that attaches to the root alkane is numbered 1 as exemplified below. 4321 CH3CH, CH2CH 1, 3-dimethylbutyl 1. First of all, the longest carbon chain in the molecule is identified. In the example I given below, the longest chain has 9 carbons and it is considered as the parent or root chain. Selection of parent chain as shown in 2 is not correct because it has only 8 carbons 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 6 7 2. The carbon atoms of the parent chain are numbered to identify the parent alkane and to locate the positions of the carbon atoms at which branching takes place due to the substitution of alkyl group in place of hydrogen atoms. The numbering is done in such a way that the branched carbon atoms get the lowest possible numbers. Thus, the numbering in the above example should be from left to right branching at carbon atoms 2 and 6 and not from right to left giving numbers 4 and 8 to the carbon atoms at which branches are attached. 1 2 3 4 5 6 7 8 9 C 9 8 7 6 5 4 3 2 1 C 3. The names of alkyl groups attached as a branch are then prefixed to the name of the parent alkane and position of the substituents is indicated by the appropriate numbers. If different alkyl groups are present, they are listed in alphabetical order. Thus, name for the compound shown above is 6-ethyl-2-methylnonane. Note, the numbers are 343. Organic chemistry. Some basic principles and techniques. The name of such branched chain alkyl group is placed in parenthesis while naming the compound. While writing the trivial names of substituents in alphabetical order, the prefixes iso and neo are considered to be the part of the fundamental name of alkyl group. The prefixes sec and tert are not considered to be the part of the fundamental name. The use of iso and related common prefixes for naming alkyl groups is also allowed by the IUPAC nomenclature as long as these are not further substituted. In multi-substituted compounds, the following rules may also be remembered. If there happens to be two chains of equal size, then the chain is to be selected which contains more number of side chains. After selection of the chain, numbering is to be done from the end closer to the substituent 5-2-ethylbutyl 3. 3-dimethyltrycane and not 5-2, 2-dimethylbutyl 3-ethyldecaine 5 seconds butyl 4-isopropyldecane 5-2, 2-dimethylpropylnonane. Problem 12.7 Structures and IUPAC names of some hydrocarbons are given below. Explain why the names given in the parentheses are incorrect. 3-ethyl 1-dimethylcyclohexane not 1-ethyl 3. 3-dimethylcyclohexane 2, 5, 6-trimethyl-octane and not 3, 4. 7-trimethyl-octane 3-ethyl-5-methylheptane and not 5-ethyl-3-methylheptane cyclic compounds. A saturated monocyclic compound is named by prefixing cyclo to the corresponding straight-chain alkane. If side chains are present, then the rules given above are applied. Names of some cyclic compounds are given below. Solution: the lowest locant number, 2, 5, 6 is lower than 3, 5, 7. B substituents are in equivalent position. Lower number is given to the one that comes first in the name according to alphabetical order. 1, 2, 5, 3. Nomenclature of organic compounds having functional group S. A functional group, as defined earlier, is an atom or a group of atoms bonded together in a unique manner which is usually the site O. 344. Chemistry: chemical reactivity in an organic molecule. Compounds having the same functional group undergo similar reactions. For example, CH3O, CH3CH2O, and CH3,2-Cha all having O functional group liberate hydrogen on reaction with sodium metal. The presence of functional groups enables systematization of organic compounds into different classes. Examples of some functional groups with their prefixes and suffixes along with some examples of organic compounds possessing these are given in Table 12.4. First of all, the functional group present in the molecule is identified, which determines the choice of appropriate suffix. The longest chain of carbon atoms containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffixes given in Table 12.4, the name of the compound is arrived at. In the case of polyfunctional compounds, one of the functional groups is chosen as the principal functional group and the compound is then named on its basis. The remaining functional groups, which are subordinate functional groups, are named as substituents using the appropriate prefixes. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional groups is Co, SO3H, Cor-R alkyl group, COCl, CONH2, CN, HCO, CO, O, NH2, CC, CC. The R, C6H5, halogens F, Cl, Br, I, number 2, alkoxy or etc. are always prefix substituents. Thus, a compound containing both an alcohol and a keto group is named as hydroxyalkanone since the keto group is preferred to the hydroxyl group. For example, H2CH23CH2COC3 will be named as 7-hydroxyheptane 2,1 and not as 2-oxyheptane 7-ol. Similarly, BrCH2CHCH2 is named as 3-bromoprop-1-ene and not 1-bromoprop-2-ene. If more than one functional group of the same type are present, their number is indicated by adding D, tri, etc. before the class suffix. In such cases the full name of the parent alkane is written before the class suffix. For example, CH2O is named as ethane 1,2-diol. However, the ending, -, of the parent alkane is dropped in the case of compounds having more than one double or triple bond. For example, CH2CHCHCH2 is named as buta 1,3-diene. Problem 12.8. Write the IUPAC names of the compounds II from their given structures. Solution: the functional group present is an alcohol O. Hence the suffix is ol. The longest chain containing O has 8 carbon atoms, hence the corresponding saturated hydrocarbon is octane. The O is on carbon atom 3. In addition, a methyl group is attached at 6th carbon, hence, the systematic name of this compound is 6-methyloctane 3-ol. Solution: the functional group present is ketone, CO, hence suffix 1. Presence of 2 keto groups is indicated by D, hence suffix becomes dione. The 2 keto groups are at carbons 2 and 4. The longest chain contains 6 carbon atoms, hence, parent hydrocarbon is hexane. Thus, the systematic name is hexane 2,4-dione. 345. Organic chemistry, some basic principles and techniques. Table 12.4. Some functional groups and classes of organic compound. 346. Chemistry solution. Here, 2 functional groups namely ketone and carboxylic acid are present. The principal functional group is the carboxylic acid group, hence the parent chain will be suffixed with oic acid. Numbering of the chain starts from carbon of Co functional group. The keto group in the chain at carbon 5 is indicated by oxo. The longest chain including the principal functional group has 6 carbon atoms, hence the parent hydrocarbon is hexane. The compound is, therefore, named as 5-oxyhexanoic acid. Solution: the 2 CC functional groups are present at carbon atoms 1 and 3, while the CC functional group is present at carbon 5. These groups are indicated by suffixes diene and in respectively. The longest chain containing the functional groups has 6 carbon atoms, hence the parent hydrocarbon is hexane. The name of compound, therefore, is hexa 1,3-diene-5-ene. Problem 12.9. Derive the structure of I2-chlorohexane, 2-pent-4-N-2-ol, 3,3-nitrocyclohexane, IV-cyclohex 2-N-1-ol, V6-hydroxyheptanol. Solution ihexane indicates the presence of 6 carbon atoms in the chain. The functional group chloro is present at carbon 2. Hence, the structure of the compound is CH3CH2CH2CH2CHClCH3. 2-pent indicates that parent hydrocarbon contains 5 carbon atoms in the chain. N and ol correspond to the functional groups CC and O at carbon atoms 4 and 2 respectively. Thus, the structure is CH2CH2CH2CHOCH3. 3-6-membered ring containing a carbon-carbon double bond is implied by cyclohexane, which is numbered as shown in I. The prefix 3-nitro means that a nitro group is present on C3. Thus, complete structural formula of the compound is 2. Double bond is suffixed functional group whereas number 2 is prefixed functional group, therefore double bond gets preference over number 2 group. IV1O means that a O group is present at C1. O is suffixed functional group and gets preference over CC bond. Thus the structure is as shown in 2. D-heptanol indicates the compound to be an aldehyde containing 7 carbon atoms in the parent chain. The 6-hydroxy indicates that O group is present at carbon 6. Thus, the structural formula of the compound is CH3CHOCH2CH2CH2CH2CH. Carbon atom of CHO group is included while numbering the carbon chain 1, 2, 5. For nomenclature of substituted benzene compounds for IUPAC nomenclature of substituted benzene compounds. The substituent is placed as prefix to the word benzene as shown in the following examples. However, common names written in bracket below of many substituted benzene compounds are also universally used. 347 Organic Chemistry. Some basic principles and techniques. 2-chloro-4-methylanisole 4-ethyl-2-methylaniline 1-chloro-2. 4-dinitrobenzene not 4-chloro. 1. 3-dinitrobenzene. If benzene ring is desubstituted, the position of substituents is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest numbers possible. For example, the compound B is named as 1,3-dibromobenzene and not as 1,5-dibromobenzene. Substituent of the base compound is assigned number 1 and then the direction of numbering is chosen such that the next substituent gets the lowest number. The substituents appear in the name in alphabetical order. Some examples are given below. 2-chloro-1-methyl-4-nitrobenzene not 4-methyl-5-chloronitrobenzene 3. 4-dimethylphenylmethylbenzene methoxybenzene aminobenzene toluenanisole aniline nitrobenzene bromobenzene 1. 2-dibromobenzene 1. 3-dibromobenzene 1. 4-dibromobenzene ABC. In the trivial system of nomenclature, the terms ortho-O, meta-M and pod-P are used as prefixes to indicate the relative positions 1, 2, 1, 3 and 1, 4 respectively. Thus, 1,3-dibromobenzene B is named as M-dibromobenzene. Meta is abbreviated as M and the other isomers of dibromobenzene 1, 2 and 1, 4C, are named as ortho or just O and pod-A or just P-dibromobenzene, respectively. For tri or higher substituted benzene derivatives, these prefixes cannot be used and the compounds are named by identifying substituent positions on the ring by following the lowest locant rule. In some cases, common name of benzene derivatives is taken as the base compound. When a benzene ring is attached to an alkane with a functional group, it is considered as substituent, instead of a parent. The name for benzene as substituent is phenyl C6H5, also abbreviated as pH. 348 Chemistry. Different carbon skeletons. These are referred to as chain isomers and the phenomenon is termed as chain isomerism. For example, C5H12 represents 3 compounds: isomerism, structural isomerism, stereoisomerism, chain isomerism, position isomerism, functional group isomerism, metamerism, geometrical isomerism, optical isomerism. 12.6 Isomerism. The phenomenon of existence of 2 or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. The following flowchart shows different types of isomerism. 1, 2, 6. 1. Structural isomerism. Compounds having the same molecular formula but different structures. Manners in which atoms are linked are classified as structural isomers. Some typical examples of different types of structural isomerism are given below. I-chain isomerism, when 2 or more compounds have similar molecular formula but a BCD. Problem 12.10. Write the structural formula of O-ethylanisole, BP-nitroaniline, C2, 3-dibromo-1-phenylpentane, D4-ethyl-1-fluoro-2-nitrobenzene. Solution: CH3CH3CH2CH2CH3CH3CH3CH2CH3 pentane isopentane 2-methylbutane CH3CH3CH3 neopentane 2,2-dimethylpropane 2. Position isomerism, when 2 or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers and this phenomenon is termed as position isomerism. For example, the molecular formula C3H8O represents 2 alcohols, OCH3CH2CH2OCH3CHCH3 Propan 1 all Propan 2 all 3 functional group isomerism. Two or more compounds having the same molecular formula but different functional groups are called functional isomers, and this phenomenon is termed as functional group isomerism. For example, the molecular formula C3H6O represents an aldehyde and a ketone. 349 Organic chemistry. Some basic principles and techniques. OHYXCH3CCH3CH3CH2CO propanone propanyl metamerism. It arises due to different alkyl chains on either side of the functional group in the molecule. For example, C4H10O represents methoxypropane CH3O C3H7 and ethoxyethane C2H5O C2H512, 6. 2 Stereoisomerism. The compounds that have the same constitution and sequence of covalent bonds but differ in relative positions of their atoms or groups in space are called stereoisomers. This special type of isomerism is called as stereoisomerism and can be classified as geometrical and optical isomerism. 12.7 Fundamental concepts in organic reaction mechanism. In an organic reaction, the organic molecule, also referred as a substrate, reacts with an appropriate attacking reagent and leads to the formation of one or more intermediate S and finally product S. The general reaction is depicted as follows. Understanding the reactivity of organic compounds and in planning strategy for their synthesis. In the following sections, we shall learn some of the principles that explain how these reactions take place. 1.2.7. 1. Fission of a covalent bond. A covalent bond can get cleaved either by a heterolytic cleavage or by 2 homolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remains with one of the fragments. After heterolysis, one atom has a sextet electronic structure and a positive charge, and the other, a valence octet with at least one lone pair and a negative charge. Thus, heterolytic cleavage of bromomethane will give 3 CH and Br as shown below. A species having a carbon atom possessing sextets of electrons and a positive charge is called a carbocation, earlier called carbonium ion. The CH3 ion is known as a methyl cation or methyl carbonium ion. Carbocations are classified as primary, secondary or tertiary depending on whether 1, 2 or 3 carbons are directly attached to the positively charged carbon. Some other examples of carbocations are CH3CH2 ethyl cation, a primary carbocation, CH3,2CH isopropyl cation, a secondary carbocation, and CH3,3C tert butyl cation, a tertiary carbocation. Carbocations are highly unstable and reactive species. Alkyl groups directly attached to the positively charged carbon stabilize the carbocations due to inductive and hyperconjugation effects, which you will be studying in the sections 1.2.7, 5 and 1.2.7, 9. The observed order of carbocation stability is CH3, CH3CH2 CH3 2CH, CH3 3C. These carbocations have trigonal planar shape with positively charged carbon being sp2 hybridized. Thus, the shape of CH may third be considered as being derived from the overlap of 3 equivalent CsP2 hybridized orbitals. Organic molecule substrate intermediate product S attacking reagent. Byproduct substrate is that reactant which supplies carbon to the new bond and the other reactant is called reagent. If both the reactants supply carbon to the new bond, then choice is arbitrary, and in that case the molecule on which attention is focused is called substrate. In such a reaction, a covalent bond between 2 carbon atoms or a carbon and some other atom is broken and a new bond is formed. A sequential account of each step, describing details of electron movement, energetics during bond cleavage and bond formation, and the rates of transformation of reactants into products kinetics is referred to as reaction mechanism. The knowledge of reaction mechanism helps I. 350 Chemistry. With one s orbital of each of the 3 hydrogen atoms, each bond may be represented as CsP2H1s sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electrons. Fig. 12.3 a. Figure 12.3 A shape of methyl carbocation. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, when group C attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. Carbon in carbanion is generally sp3 hybridized and its structure is distorted tetrahedron as shown in Fig. 12.3b. Carbanions are also unstable and reactive species. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. The single electron movement is shown by half-headed fishhook, curved arrow. Such cleavage results in the formation of neutral species atom or group which contains an unpaired electron. These species are called free radicals. Like carbocations and carbanions, free radicals are also very reactive. A homolytic cleavage can be shown as alkyl free radical. Alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. Methyl ethyl isopropyl Turk butyl free radical organic reactions, which proceed by homolytic fission, are called free radical or homopolar or nonpolar reactions. 1, 2, 7. 2 substrate and reagent ions are generally not formed in the reactions of organic compounds. Molecules as such participate in the reaction. It is convenient to name one reagent as substrate and other as reagent. In general, a molecule whose carbon is involved in new bond formation is called substrate and the other one is called reagent. When carbon-carbon bond is formed, the choice of naming the reactants as substrate and reagent is arbitrary and depends on molecule under observation. Example: ICH2CH2Br2CH2Br substrate reagent product. 2 nucleophiles and electrophiles reagents attack the reactive site of the substrate. The reactive site may be electron deficient. Figure 12.3b shape of methyl carbanio. 351 Organic chemistry, some basic principles and techniques. Portion of the molecule a positive reactive site, e.g. an atom with incomplete electron shell or the positive end of the dipole in the molecule. If the attacking species is electron-rich, it attacks these sites. If attacking species is electron-deficient, the reactive site for it is the part of the substrate molecule which can supply electrons, e.g., Greek letter pi electrons in a double bond. A reagent that brings an electron pair to the reactive site is called a nucleophile. That is, nucleus seeking in the reaction is then called nucleophilic. A reagent that takes away an electron pair from reactive site is called electrophile. That is, electron seeking in the reaction is called electrophilic. During a polar organic reaction, a nucleophile attacks an electrophilic center of the substrate, which is that specific atom or part of the substrate which is electron deficient. Similarly, the electrophiles attack at nucleophilic center, which is the electron-rich center of the substrate. Thus, the electrophiles receive electron pair from the substrate when the two undergo bonding interaction. A curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Some examples of nucleophiles are the negatively charged ions with lone pair of electrons such as hydroxide HO, cyanide NC ions and carbanions R3C. Neutral molecules such as etc. can also act as nucleophiles due to the presence of lone pair of electrons. Examples of electrophiles include carbocations 3CH and neutral molecules having functional groups like carbonyl group, CO or alkyl halides R3CX, where X is a halogen atom. The carbon atom in carbocations has sextet configuration, hence, it is electron deficient and can receive a pair of electrons from the nucleophiles. In neutral molecules such as alkyl halides, due to the polarity of the CX bond, a partial positive charge is generated on the carbon atom and hence the carbon atom becomes an electrophilic center at which a nucleophile can attack. Problem 12.11 using curved arrow notation, show the formation of reactive intermediates when the following covalent bonds undergo heterolytic cleavage. A CH3, SCH3, BCH3CN, CCH3 solution. Problem 12.12 giving justification, categorize the following molecules ions as nucleophile or electrophile. Solution: nucleophiles. 25323, HS. CHO, CHN, HN. These species have unshared pair of electrons, which can be donated and shared with an electrophile. Electrophiles. 332BF, CL, CHCO. No, reactive sites have only 6 valence electrons, can accept electron pair from a nucleophile. Problem 12.13 identify electrophilic center in the following: CH3CHO, CH3CN, CH3I. Solution among CH3HCO, H3CCN, and H3CI. The starred carbon atoms are electrophilic centers as they will have partial positive charge due to polarity of the bond. 1, 2, 7, 3 Electron movement in organic reactions. The movement of electrons in organic reactions can be shown by curved arrow notation. Capital I. 352 Chemistry shows how changes in bonding occur due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted and it ends at a location to which the pair of electron may move. Presentation of shifting of electron pair is given below. I from Greek letter pi bond to adjacent bond position. 2 from Greek letter pi bond to adjacent atom. 3 from atom to adjacent bond position. Movement of single electron is indicated by a single barbed fish hooks, that is, half-headed curved arrow. For example, in transfer of hydroxide ion giving ethanol and in the dissociation of chloromethane. The movement of electron using curved arrows can be depicted as follows: 1, 2, 7. 4 electron displacement effects in covalent bonds. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group, or in the presence of an appropriate attacking reagent. The electron displacements due to the influence of an atom or a substituent group present in the molecule cause permanent polarization of the bond. Inductive effect and resonance effects are examples of this type of electron displacements. Temporary electron displacement effects are seen in a molecule when a reagent approaches to attack it. This type of electron displacement is called electromeric effect or polarizability effect. In the following sections we will learn about these types of electronic displacements. 1, 2, 7, 5 Inductive effect. When a covalent bond is formed between atoms of different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond. Bond polarity leads to various electronic effects in organic compounds. Let us consider chloroethane CH3CH2Cl, in which the CCl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge Greek letter delta and the chlorine some negative charge Greek letter delta. The fractional electronic charges on the two atoms in a polar covalent bond are denoted by symbol Greek letter delta delta, and the shift of electron density is shown by an arrow that points from Greek letter delta to Greek letter delta end of the polar bond. Greek letter delta Greek letter delta Greek letter delta Greek letter delta CH3CH2Cl21. In turn, carbon 1, which has developed partial positive charge Greek letter delta, draws some electron density towards it from the adjacent CC bond. Consequently, some positive charge Greek letter delta develops on carbon 2 also, where Greek letter delta symbolizes relatively smaller positive charges compared to that on carbon 1. In other words, the polar C-Cl bond induces polarity in the adjacent bonds. Such polarization of Greek letter sigma bond caused by the polarization of adjacent Greek letter sigma bond is referred to as the inductive effect. This effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of intervening bonds increases and becomes vanishingly small after 3 bonds. The inductive effect is related to the ability of substituent S to either withdraw or donate electron density to the attached carbon atom. Based on this ability, the substituents can be classified as electron withdrawing or electron donating groups relative to hydrogen, halogens, and many other groups such as nitro number 2, cyano-CN, carboxy-CoO, ester-COR, aryloxy-OR, e.g. OC6H5, etc. are electron withdrawing groups. On the other hand, the alkyl groups like methyl CH3 and ethyl CH2, CH3 are usually considered as electron donating groups. 353 Organic chemistry. Some basic principles and techniques. Problem 12.14. Which bond is more polar in the following pairs of molecules? A H3CH, H3CBr-BH3CnH2, H3COCH3CO, H3CSH. Solution: a CBr, since Br is more electronegative than H. BCO, CCO. Problem 12.15. In which CC bond of CH3CH2CH2Br, the inductive effect is expected to be the least. Solution: magnitude of inductive effect diminishes as the number of intervening bonds increases. Hence, the effect is least in the bond between carbon 3 and hydrogen 1, 2, 7, 6. Resonance structure. There are many organic molecules whose behavior cannot be explained by a single Lewis structure. An example is that of benzene. Its cyclic structure containing alternating CC single and CC double bonds shown is inadequate for explaining its characteristic properties. As per the above representation, benzene should exhibit 2 different bond lengths, due to CC single and CC double bonds. However, as determined experimentally, benzene has a uniform CC bond distances of 139 pm, a value intermediate between the CC single 154 pm and CC double 134 pm bonds. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented equally well by the energetically identical structures I and 2 be adequately represented by any of these structures. Rather, it is a hybrid of the 2 structures I and 2 called resonance structures. The resonance structures, canonical structures or contributing structures, are hypothetical and individually do not represent any real molecule. They contribute to the actual structure in proportion to their stability. Another example of resonance is provided by nitromethane CH3 number 2, which can be represented by 2 Lewis structures, I and 2. There are 2 types of NO bonds in these structures. However, it is known that the 2 NO bonds of nitromethane are of the same length intermediate between a NO single bond and a NO double bond. The actual structure of nitromethane is therefore a resonance hybrid of the 2 canonical forms I and 2. The energy of actual structure of the molecule, the resonance hybrid, is lower than that of any of the canonical structures. The difference in energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy, or simply the resonance energy. The more the number of important contributing structures, the more is the resonance energy. Resonance is particularly important when the contributing structures are equivalent in energy. The following rules are applied while writing resonance structures. The resonance structures have I the same positions of nuclei and 2 the same number of unpaired electrons. Among the resonance structures, the one which has more number of covalent bonds, all the atoms with octet of electrons except hydrogen which has a duplet. Less separation of opposite charges, a negative charge if any on more electronegative atom, a positive charge if any on more electropositive atom and more dispersal of charge, is more stable than others. Benzene therefore, according to the resonance theory unit for the actual structure of benzene cano. 354 Chemistry Problem 12.16 Write resonance structures of CH3COO, and show the movement of electrons by curved arrows. Solution first, write the structure and put on shared pairs of valence electrons on appropriate atoms. Then draw the arrows one at a time moving the electrons to get the other structures. Problem 12.17 Write resonance structures of CH2CH2. Indicate relative stability of the contributing structures. Solution The two structures are less important contributors as they involve charge separation. Additionally, structure I contains a carbon atom with an incomplete octet. 1 2 7 Resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two Greek letter pi bonds or between a Greek letter pi bond and lone pair of electrons present on an adjacent atom. The effect is transmitted through the chain. There are two types of resonance or mesomeric effect designated as R or M effect. I positive resonance effect. R effect. In this effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. This electron displacement makes certain positions in the molecule at high electron densities. This effect in aniline is shown as stability I, 2, 3I, most stable. More number of covalent bonds. Each carbon and oxygen atom has an octet and no separation of opposite charge. 2, negative charge on more electronegative atom and positive charge on more electropositive atom. 3, does not contribute as oxygen has positive charge and carbon has negative charge, hence least stable. Problem 12.18 Explain why the following two structures, I and 2 cannot be the major contributors to the real structure of CH3COO3. 2 Negative resonance effect. R effect. This effect is observed when the transfer of electrons is towards the atom or substituent group attached to the conjugated system. For example, in nitrobenzene this electron displacement can be depicted as the atoms or substituent groups, which represent R or R electron displacement effects are as follows. R effect, halogen, O. Or, ACOR, NH2, NHR, NR2, NHCOR, R effect, COO, CHOC, OC, NO. 355 Organic Chemistry. Some basic principles and techniques. The presence of alternate single and double bonds in an open chain or cyclic system is termed as a conjugated system. These systems often show abnormal behavior. The examples are 1,3-butadiene, aniline and nitrobenzene, etc. In such systems, the Greek letter pi electrons are delocalized and the system develops polarity 1 2 7 8 electromeric effect. E effect. It is a temporary effect. The organic compounds having a multiple bond, a double or triple bond, show this effect in the presence of an attacking reagent only. It is defined as the complete transfer of a shared pair of Greek letter pi electrons to one of the atoms joined by a multiple bond on the demand of an attacking reagent. The effect is annulled as soon as the attacking reagent is removed from the domain of the reaction. It is represented by E and the shifting of the electrons is shown by a curved arrow. There are two distinct types of electromeric effect. I positive electromeric effect. E effect. In this effect the Greek letter pi electrons of the multiple bond are transferred to that atom to which the reagent gets attached. For example, system or to an atom with an unshared p orbital, the Greek letter sigma electrons of CH bond of the alkyl group enter into partial conjugation with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. To understand hyperconjugation effect, let us take an example of 3,2-CH ethyl cation in which the positively charged carbon atom has an empty p orbital. One of the CH bonds of the methyl group can align in the plane of this empty p orbital, and the electrons constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital as depicted in Fig. 12.42 Negative electromeric effect. E effect. In this effect the Greek letter pi electrons of the multiple bond are transferred to that atom to which the attacking reagent does not get attached. For example, when inductive and electromeric effects operate in opposite directions, the electromeric effect predominates. 1 2 7 9 Hyperconjugation. Hyperconjugation is a general stabilizing interaction. It involves delocalization of Greek letter sigma electrons of CH bond of an alkyl group directly attached to an atom of unsaturated Fig. 12.4 Orbital diagram showing hyperconjugation in ethyl cation. This type of overlap stabilizes the carbocation because electron density from the adjacent Greek letter sigma bond helps in dispersing the positive charge. In general, greater the number of alkyl groups attached to a positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of the cation. Thus, we have the following relative stability of carbocations. 356 Chemistry hyperconjugation is also possible in alkenes and alkylarenes. Delocalization of electrons by hyperconjugation in the case of alkene can be depicted as in Fig. 12.4b. Problem 12.19 Explain why CH33C is more stable than 323CH. CH and CH is the least stable cation. Solution hyperconjugation interaction in CH33C is greater than in 32CH. CH as the CH33C has 9 CH bonds. In 3CH, vacant p orbital is perpendicular to the plane in which CH bonds lie, hence cannot overlap with it. Thus, 3CH lacks hyperconjugative stability. December 7, 2010 Types of organic reactions and mechanisms. Organic reactions can be classified into the following categories: I substitution reactions, 2 addition reactions, 3 elimination reactions, 5 rearrangement reactions. You will be studying these reactions in Unit 13 and later in Class 12. 12.8 Methods of purification of organic compounds. Once an organic compound is extracted from a natural source or synthesized in the laboratory, it is essential to purify it. Various methods used for the purification of organic compounds are based on the nature of the compound and the impurity present in it. The common techniques used for purification are as follows: I sublimation, 2 crystallization, 3 distillation, I differential extraction, and V chromatography. Finally, the purity of a compound is ascertained by determining its melting or boiling point. Most of the pure compounds have sharp melting points and boiling points. New methods of checking the purity of an organic compound are based on different types. Figure 12.4b Orbital diagram showing hyperconjugation in propene. There are various ways of looking at the hyperconjugative effect. One of the way is to regard CH bond as possessing partial ionic character due to resonance. The hyperconjugation may also be regarded as no bond resonance. 357 Organic chemistry. Some basic principles and techniques of chromatographic and spectroscopic techniques. 128. 1. Sublimation. You have learnt earlier that on heating, some solid substances change from solid to vapor state without passing through liquid state. The purification technique based on the above principle is known as sublimation and is used to separate sublimable compounds from non-sublimable impurities. 128. 2. Crystallization. This is one of the most commonly used techniques for the purification of solid organic compounds. It is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. The impure compound is dissolved in a solvent in which it is sparingly soluble at room temperature but appreciably soluble at higher temperature. The solution is concentrated to get a nearly saturated solution. On cooling the solution, pure compound crystallizes out and is removed by filtration. The filtrate mother liquor contains impurities and small quantity of the compound. If the compound is highly soluble in one solvent and very little soluble in another solvent, crystallization can be satisfactorily carried out in a mixture of these solvents. Impurities, which impart color to the solution, are removed by adsorbing over activated charcoal. Repeated crystallization becomes necessary for the purification of compounds containing impurities of comparable solubilities. 128. 3. Distillation. This important method is used to separate volatile liquids from non-volatile impurities and to the liquids having sufficient difference in their boiling points. Liquids having different boiling points vaporize at different temperatures. The vapors are cooled and the liquids so formed are collected separately. Chloroform B page 334K and aniline B page 457K are easily separated by the technique of distillation. Figure 12.5. The liquid mixture is taken in a round bottom flask and heated carefully. On boiling, the vapors of lower boiling component are formed first. The vapors are condensed by using a condenser and the liquid is collected in a receiver. The vapors of higher boiling component form later and the liquid can be collected separately. Fractional distillation. If the difference in boiling points of two liquids is not much, simple distillation cannot be used to separate them. The vapors of such liquids are formed within the same temperature range and are condensed simultaneously. The technique of fractional distillation is used in such cases. In this technique, vapors of a liquid mixture are passed through a fractionating column before condensation. The fractionating column is fitted over the mouth of the round bottom flask. Figure 12.6, page 358. Vapors of a liquid with higher boiling point condense before the vapors of a liquid with lower boiling point. The vapors rising up in the fractionating column become richer and more volatile component. By the time the figure 12.5 simple distillation, the vapors of a substance formed are condensed and the liquid is collected in conical flask. 358 Chemistry vapors reach to the top of the fractionating column. These are rich in the more volatile component. Fractionating columns are available in various sizes and designs as shown in Figure 12.7. A fractionating column provides many surfaces for heat exchange between the ascending vapors and the descending condensed liquid. Some of the condensing liquid in the fractionating column obtains heat from the ascending vapors and revaporizes. The vapors thus become richer in low boiling component. The vapors of low boiling component ascend to the top of the column. On reaching the top, the vapors become pure in low boiling component and pass through the condenser, and the pure liquid is collected in a receiver. After a series of successive distillations, the remaining liquid in the distillation flask gets enriched in high boiling component. Each successive condensation and vaporization unit in the fractionating Figure 12.7 different types of fractionating columns. Column is called a theoretical plate. Commercially, columns with hundreds of plates are available. One of the technological applications of fractional distillation is to separate different fractions of crude oil in petroleum industry. Figure 12.6 Fractional distillation. The vapors of lower boiling fraction reach the top of the column first, followed by vapors of higher boiling fractions. Distillation under reduced pressure. This method is used to purify liquids having very high boiling points and those which decompose at or below their boiling points. Such liquids are made to boil at a temperature lower than their normal boiling points by reducing the pressure on their surface. A liquid boils at a temperature at which its vapor pressure is equal to the external pressure. The pressure is reduced with the help of a water pump or vacuum pump. Figure 12.8. Glycerol can be separated from spent lye in soap industry by using this technique. 359 Organic chemistry. Some basic principles and techniques. Figure 12.8 Distillation under reduced pressure. A liquid boils at a temperature below its vapor pressure by reducing the pressure. Steam distillation. This technique is applied to separate substances which are steam volatile and are immiscible with water. In steam distillation, steam from a steam generator is passed through a heated flask containing the liquid to be distilled. The mixture of steam and the volatile organic compound is condensed and collected. The compound is later separated from water using a separating funnel. In steam distillation, the liquid boils when the sum of vapor pressures due to the organic liquid P1 and that due to water page 2 becomes equal to the atmospheric pressure P, that is, P1 page 2. Since P1 is lower than P, the organic liquid vaporizes at lower temperature than its boiling point. Thus, if one of the substances in the mixture is water and the other, a water-insoluble substance, then the mixture will boil close to but below 373 K. A mixture of water and the substance is obtained which can be separated by using a separating funnel. Aniline is separated by this technique from aniline, water mixture. Figure 12.9. Page 361-8. For differential extraction. When an organic compound is present in an aqueous medium, it is separated by shaking it with an organic solvent in which it is more soluble than in water. The organic solvent and the aqueous solution should be immiscible with each other so that they form two distinct layers which can be separated by separatory funnel. The organic solvent is later removed by distillation or by evaporation to get back the compound. Differential extraction is carried out in a separatory funnel as shown in Fig. 12.10 page 360. If the organic compound is less soluble in the organic solvent, a very large quantity of solvent would be required to extract even a very small quantity of the compound. The technique of continuous extraction is employed in such cases. In this technique, same solvent is repeatedly used for extraction of the compound. 128. 5 Chromatography. Chromatography is an important technique extensively used to separate mixtures into their components, purify compounds and also to test the purity of compounds. The nom. 360 Chemistry. Chromatography is based on the Greek word chroma, for color, since the method was first used for the separation of colored substances found in plants. In this technique, the mixture of substances is applied onto a stationary phase, which may be a solid or a liquid. A pure solvent, a mixture of solvents, or a gas is allowed to move slowly over the stationary phase. The components of the mixture get gradually separated from one another. The moving phase is called the mobile phase. Based on the principle involved, chromatography is classified into different categories. Two of these are A. Adsorption chromatography, and B. Partition chromatography. A. Adsorption chromatography. Adsorption chromatography is based on the fact that different compounds are adsorbed on an adsorbent to different degrees. Commonly used adsorbents are silica gel and alumina. When a mobile phase is allowed to move over a stationary phase adsorbent, the components of the mixture move by varying distances over the stationary phase. Following are two main types of chromatographic techniques based on the principle of differential adsorption. A. Column chromatography, and B. Thin layer chromatography. Figure 12.10 Differential extraction. Extraction of compound takes place based on difference in solubility. Figure 12.9 Steam distillation. Steam volatile component volatilizes the vapors con. 361 Organic chemistry, some basic principles and techniques. Column chromatography. Column chromatography involves separation of a mixture over a column of adsorbent stationary phase packed in a glass tube. The column is fitted with a stopcock at its lower end. Figure 12.11. The mixture adsorbed on adsorbent is placed on the top of the adsorbent column packed in a glass tube. An appropriate eluent, which is a liquid or a mixture of liquids, is allowed to flow down the column slowly. Depending upon the degree to which the compounds are adsorbed, complete separation takes place. The most readily adsorbed substances are retained near the top and others come down to various distances in the column. Figure 12.11. Plate is then placed in a closed jar containing the eluent. Figure 12.12. As the eluent rises up the plate, the components of the mixture move up along with the eluent to different distances depending on their degree of adsorption, and separation takes place. The relative adsorption of each component of the mixture is expressed in terms of its retardation factor, that is, RF value. Figure 12.12b. RF distance moved by the substance from baseline X, distance moved by the solvent from baseline Y. Figure 12.11. Column chromatography. Different stages of separation of components of a mixture. Thin layer chromatography. Thin layer chromatography (TLC) is another type of adsorption chromatography, which involves separation of substances of a mixture over a thin layer of an adsorbent coated on glass plate. A thin layer about 0.2 mm thick of an adsorbent silica gel or alumina is spread over a glass plate of suitable size. The plate is known as thin layer chromatography plate or chromoplate. The solution of the mixture to be separated is applied as a small spot about 2 cm above one end of the TLC plate. The spots of colored compounds are visible on TLC plate due to their original color. The spots of colorless compounds, which are invisible to the eye but fluoresce in ultraviolet light, can be detected by putting the plate under ultraviolet light. Another detection technique is to place the plate in a covered jar containing a few crystals of iodine. Spots of compounds, which adsorb iodine, will show up as brown spots. Sometimes an appropriate reagent may also be sprayed on the plate. For example, amino acids may be detected by spraying the plate with ninhydrin solution. Figure 12.12b. Figure 12.12b. Developed chromatogram. Figure 12.12. A thin layer chromatography, chromatogram being developed. 362 Chemistry. The spots of the separated colorless compounds may be observed either under ultraviolet light or by the use of an appropriate spray reagent as discussed under thin layer chromatography. 12.9 Qualitative analysis of organic compounds. The elements present in organic compounds are carbon and hydrogen. In addition to these, they may also contain oxygen, nitrogen, sulfur, halogens and phosphorus. 129. 1. Detection of carbon and hydrogen. Carbon and hydrogen are detected by heating the compound with copper 2 oxide. Carbon present in the compound is oxidized to carbon dioxide tested with lime water, which develops turbidity, and hydrogen to water tested with anhydrous copper sulfate, which turns blue. C2CuO2 CuCO2 2HCuO CuH2O CO2 CrO2 CaCO3 H2O 5H2O CuSO4 CuSO4.5 H2O white blue. 129. To detection of other elements. Nitrogen, sulfur, halogens and phosphorus present in an organic compound are detected by Lassane's test. The elements present in the compound are converted from covalent form into the ionic form by fusing the compound with sodium metal. Following reactions take place: Na-CN Act2 Na-S Na-2S Na-X Na-XXCl, Br or IC, N, S and X come from organic compound. Cyanide, sulfate and halide of sodium so formed on sodium fusion are extracted from the fused mass by boiling it with distilled water. This extract is known as sodium fusion extract. A test for nitrogen. A sodium fusion extract is boiled with iron 2 sulfate and then acidified with partition chromatography. Partition chromatography is based on continuous differential partitioning of components of a mixture between stationary and mobile phases. Paper chromatography is a type of partition chromatography. In paper chromatography, a special quality paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as the stationary phase. A strip of chromatography paper spotted at the base with the solution of the mixture is suspended in a suitable solvent or a mixture of solvents. Fig. 12.13. This solvent acts as the mobile phase. The solvent rises up the paper by capillary action and flows over the spot. The paper selectively retains different components according to their different partition in the two phases. The paper strip so developed is known as a chromatogram. The spots of the separated colored compounds are visible at different heights from the position of initial spot on the chromatogram. Figure 12.13 Paper chromatography. Chromatography paper in two different shapes. 363 Organic chemistry. Some basic principles and techniques. Concentrated sulfuric acid. The formation of Prussian blue color confirms the presence of nitrogen. Sodium cyanide first reacts with iron 2 sulfate and forms sodium hexocyanidopherate 2. On heating with concentrated sulfuric acid, some iron 2 ions are oxidized to iron 3 ions, which react with sodium hexocyanidophorat 2 to produce iron 3 hexocyanidophorat 2 ferriferous cyanide, which is Prussian blue in color. 6 Fe 2 Fe 6 4 3 Fe 6 4 4 Fe 3 Fe 4 Fe 6 3 XH2O Prussian blue. B test for sulfur. The sodium fusion extract is acidified with acetic acid and lead acetate is added to it. A black precipitate of lead sulfate indicates the presence of sulfur. S2Pb2Pbs black. Beyond treating sodium fusion extract with sodium nitroprusside, appearance of a violet color further indicates the presence of sulfur. S2 Fe CN5 number 2 Fe CN5 NOS 4 violet. In case nitrogen and sulfur both are present in an organic compound, sodium thiocyanate is formed. It gives blood red color and no Prussian blue since there are no free cyanide ions. NaCNS NaSCN Fe 3 SCN Fe SCN2 blood red if sodium fusion is carried out with excessive sodium. The thiocyanate decomposes to yield cyanide and sulfate. These ions give their usual tests. NaSCN2 Non-ACNA2 SC test for halogens. The sodium fusion extract is acidified with nitric acid and then treated with silver nitrate. A white precipitate, soluble in ammonium hydroxide, shows the presence of chlorine. A yellowish precipitate, sparingly soluble in ammonium hydroxide, shows the presence of bromine, and a yellow precipitate, insoluble in ammonium hydroxide, shows the presence of iodine. XAGXX represents a halogen, Cl, Br or I if nitrogen or sulfur is also present in the compound. The sodium fusion extract is first boiled with concentrated nitric acid to decompose cyanide or sulfate of sodium formed during Lassane's test. These ions would otherwise interfere with silver nitrate test for halogens. D test for phosphorus. The compound is heated with an oxidizing agent, sodium peroxide. The phosphorus present in the compound is oxidized to phosphate. The solution is boiled with nitric acid and then treated with ammonium molybdate. A yellow coloration or precipitate indicates the presence of phosphorus. Na3PO4,3HNO3H3PO4,3NO3H3PO412NH4 ammonium molybdate NH4 number 312H2O ammonium phosphomolybdate 12.10 Quantitative analysis. Quantitative analysis of compounds is very important in organic chemistry. It helps chemists in the determination of mass percent of elements present in a compound. You have learned in Unit 1 that mass percent of elements is required for the determination of empirical and molecular formula. The percentage composition of elements present in an organic compound is determined by the following methods. 1 2, 1 0, 1 carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. A known mass of an organic compound is burnt in the presence of excessive oxygen and copper 2 oxide. Carbon and hydrogen in the compound are oxidized to carbon dioxide and water respectively. CX high XY4O2XCO2Y2H2. (364) Chemistry. The mass of water produced is determined by passing the mixture through a wedge U-tube containing anhydrous calcium chloride. Carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. These tubes are connected in series. Figure 12.14. The increase in masses of calcium chloride and potassium hydroxide gives the amounts of water and carbon dioxide from which the percentages of carbon and hydrogen are calculated. Let the mass of organic compound be mg. Mass of water and carbon dioxide produced be m1 and m2g respectively. Percentage of carbon 212 144 xxxmn. Percentage of hydrogen 12 118 xxxmn. Problem 12.20 On complete combustion, 0.246 grams of an organic compound gave 0.198 grams of carbon dioxide and 0.1014 grams of water. Determine the percentage composition of carbon and hydrogen in the compound. Solution 12.0.198 100 percentage of carbon 44 0.246 21.95 xxx percentage of hydrogen 20.1014 118 0.246 xxx 4.5812 10 2 Nitrogen. There are two methods for estimation of nitrogen, Dumas method and 2 Calvel's method. Dumas method. The nitrogen-containing organic compound, when heated with copper oxide in an atmosphere of carbon dioxide, yields free nitrogen in addition to carbon dioxide and water. CX high NZ2 times Y2 CuOx CO2 Y2 H2O Z2 N2 2 times Y2 Cu traces of nitrogen oxides formed. if any, are reduced to nitrogen by passing the gaseous mixture over a heated copper glass. The mixture of gases so produced is collected over an aqueous solution of potassium hydroxide which absorbs carbon dioxide. Nitrogen is collected in the upper part of the graduated tube, figure 12.15. Let the mass of organic compound mg volume of nitrogen collected V1 ml room temperature T1 K11 1 273 volume of nitrogen at STP 760 XX PVT let it be the ml where page 1 and V1 are the pressure and volume of nitrogen. Page 1 is different from the atmospheric pressure at which nitrogen gas is collected. The value of page 1 is obtained by the relation, page 1 atmospheric pressure, aqueous tension 22,400 milliliters N2 at STP weighs 28 grams. Figure 12.14 Estimation of carbon and hydrogen. Water and carbon dioxide formed on oxidation of substance are absorbed in anhydrous calcium chloride and potassium hydroxide solutions respectively contained in U-tubes. (365) Organic chemistry. Some basic principles and techniques. 228 milliliters N at STP weighs G 22,400 xVV. Percentage of nitrogen 28100 22400 XXXVM. Problem 12.21 in Dumas method for estimation of nitrogen. 0.3 grams of an organic compound gave 50 milliliters of nitrogen collected at 300 K temperature and 715 millimeters pressure. Calculate the percentage composition of nitrogen in the compound. Aqueous tension at 300 K 15 mm solution volume of nitrogen collected at 300 K and 715 mm pressure is 50 milliliters actual pressure 715 700 mm 273 750 volume of nitrogen at STP 300 760 41.9 milliliters XXX 22 400 milliliters of N2 at STP weighs 28 grams 2841.9 41.9 milliliters of nitrogen weighs G 22,400 x 2841.9 100% of nitrogen 22,400 0.3 17.46 XXX. Figure 12.15 Dumas method. The organic compound yields nitrogen gas on heating it with copper to oxide in the presence of CO2 gas. The mixture of gases is collected over potassium hydroxide solution in which CO2 is absorbed and volume of nitrogen gas is determined. 2. Kaldal's method. The compound containing nitrogen is heated with concentrated sulfuric acid. Nitrogen in the compound gets converted to ammonium sulfate. Figure 12.16. The resulting acid mixture is then heated with excess of sodium hydroxide. The liberated ammonia gas is absorbed in an excess of standard solution of sulfuric acid. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left. 366 Chemistry after the reaction gives the amount of acid reacted with ammonia. Organic compound H2SO4NH422422322 NaONaSO NHHO2NH3 H2SO4NH42SO4. Let the mass of organic compound taken mg volume of H2SO4 of molarity m taken VML volume of NaO of molarity m. Used for titration of excess of H2SO4 V1 ml V1 ml of NaO of molarity m V1 to milliliters of H2SO4 of molarity m volume of H2SO4 of molarity m unused VV1 to milliliters VV1 to milliliters of H2SO4 of molarity m2 VV1 to milliliters of NH3 solution of molarity m. 1000 milliliters of 1 mNH3 solution contains 17 grams NH3 or 14 grams of N2 VV1 to milliliters of NH3 solution of molarity M contains 114 N2 VV2 grams N1000 XX 114 N2 VV2 100% of N1000 XXX M 11.4 N2 2 XX VVM. Kaldal method is not applicable to compounds containing nitrogen in nitro and acyl groups and nitrogen present in the ring, e.g. pyridine, as nitrogen of these compounds does not change to ammonium sulfate under these conditions. Problem 12.22 During estimation of nitrogen present in an organic compound by Kaldal's method. The ammonia evolved from 0.5 grams of the compound in Kaldal's estimation of nitrogen, neutralized 10 milliliters of 1M-H2SO4. Find out the percentage of nitrogen in the compound. Solution 1M of 10 milliliters H2SO4 1M of 20 milliliters NH3 1000 milliliters of 1M ammonia contains 14 grams nitrogen 20 milliliters of 1M ammonia contains figure 12.16 Kaldal method. Nitrogen-containing compound is treated with concentrated H2SO4 to get ammonium sulfate which liberates ammonia on treating with NaO. Ammonia is absorbed in known volume of standard acid. 367 Organic Chemistry, Some Basic Principles and Techniques 1420 1000 xg Nitrogen Percentage of nitrogen 1420 xxx 1000 05 560, 1210, 3 Halogens Carius Method. A known mass of an organic compound is heated with fuming nitric acid in the presence of silver nitrate contained in a hard glass tube known as Carius tube. Figure 12.17 Percentage of halogen XXX atomic mass molecular S of X mass of AgX 1 meter M100 Problem 12.23 In Carius method of estimation of halogen. 0.15 grams of an organic compound gave 0.12 grams of AgBr. Find out the percentage of bromine in the compound. Solution molar mass of AgBr 108 188 grams mole 1 188 grams AgBr contains 80 grams bromine 0.12 grams AgBr contains 80 1 to 188 x. G bromine 80.12 100 percentage of bromine 188 0.15 34.04 xxx 12 4 sulfur. A known mass of an organic compound is heated in a Carius tube with sodium peroxide or fuming nitric acid. Sulfur present in the compound is oxidized to sulfuric acid. It is precipitated as barium sulfate by adding excessive barium chloride solution in water. The precipitate is filtered, washed, dried and weighed. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of organic compound taken Mg and the mass of barium sulfate formed M1G 1 mole of BaSO4 233 grams BaSO4 32 grams sulfur M1G BaSO4 contains 132 233 x Mg sulfur 132 100 percentage of sulfur 233 xxxmm Fig. 12.17 Carius method. Halogen containing organic compound is heated with fuming nitric acid in the presence of silver nitrate. In a furnace, carbon and hydrogen present in the compound are oxidized to carbon dioxide and water. The halogen present forms the corresponding silver halide AgX. It is filtered, washed, dried and weighed. Let the mass of organic compound taken Mg mass of AgX formed M1G 1 mole of AgX contains 1 mole of X mass of halogen in M1G of AgX 1 atomic mass of Xg molecular mass of AgXXM Problem 12.24 In sulfur estimation. 0.157 grams of an organic compound gave 0.4813 grams O. 368 Chemistry percentage composition 100 and the sum of the percentages of all other elements. However, oxygen can also be estimated directly as follows. A definite mass of an organic compound is decomposed by heating in a stream of nitrogen gas. The mixture of gaseous products containing oxygen is passed over red-hot coke when all the oxygen is converted to carbon monoxide. This mixture is passed through warm iodine pentoxide I2O5 when carbon monoxide is oxidized to carbon dioxide producing iodine. Compound heat O2 other gaseous products 2CO2 1373 K2COX5 AI2055 COI2 5CO2X2B on making the amount of CO produced in equation A equal to the amount of CO used in equation B by multiplying the equations A and B by 5 and 2 respectively, we find that each mole of oxygen liberated from the compound will produce 2 moles of carbon dioxide. Thus 88 grams carbon dioxide is obtained and 32 grams oxygen is liberated. Let the mass of organic compound taken be Mg mass of carbon dioxide produced be M1G carbon dioxide is obtained from X 132 88 meters GO2 percentage of oxygen XXX 132 188 meters and the percentage of oxygen can be derived from the amount of iodine produced also. Presently, the estimation of elements in an organic compound is carried out by using micro-quantities of substances and automatic experimental techniques. The elements, carbon, hydrogen and nitrogen present in a compound are determined by an apparatus known as CHN elemental analyzer. The analyzer requires only a very small amount of the substance 13 mg and displays the values on a screen within a short time. A detailed discussion of such methods is beyond the scope of this book. Barium sulfate. What is the percentage of sulfur in the compound? Solution molecular mass of BaSO4 137 32 64 233 grams 233 grams BaSO4 contains 32 grams sulfur 0.4813 grams BaSO4 contains 32 0.4813 233 xg sulfur 32 0.4813 100 percentage of sulfur 233 0.157 42.10 xxx 12 5 Phosphorus. A known mass of an organic compound is heated with fuming nitric acid whereupon phosphorus present in the compound is oxidized to phosphoric acid. It is precipitated as ammonium phosphomolybdate, NH43PO4.12 Mu3, by adding ammonia and ammonium molybdate. Alternatively, phosphoric acid may be precipitated as MgNH4PO4 by adding magnesium mixture which on ignition yields Mg2P2O7. Let the mass of organic compound taken mg and mass of ammonium phosphomolate at m1 molar mass of NH43PO4.12 mu 3 1877 grams percentage of phosphorus 131, 100, 1877, xxxmm if phosphorus is estimated as Mg2P2O7, percentage of phosphorus 162 100 222 xxxmm where 222 U is the molar mass of Mg2P2O7, m, the mass of organic compound taken, m1, the mass of Mg2P2O7 formed and 62, the mass of 2 phosphorus atoms present in the compound Mg2P2O7. 1210, 6 oxygen. The percentage of oxygen in an organic compound is usually found by difference between the total. Summary: in this unit, we have learned some basic concepts in structure and reactivity of organic compounds, which are formed due to covalent bonding. The nature of the covalent bonding in organic compounds can be described in terms of orbitals hybridization concept, according to which carbon can have sp3, sp2 and sp hybridized orbitals. The sp3, sp2 and sp hybridized carbons are found in compounds like methane, ethene and ethene respectively. The tetrahedral shape of methane, planar shape of ethene and linear shape of ethene can be understood on the basis of this concept. A sp3 hybrid orbital can overlap with one s orbital of hydrogen to give a carbon-hydrogen CH single bond sigma, Greek letter sigma bond. Overlap of sp2 orbital of one carbon with sp2 orbital of another results in the formation of a carbon-carbon Greek letter sigma bond. The unhybridized p orbitals on two adjacent carbons can undergo lateral side-by-side overlap to give a pi Greek letter pi bond. Organic compounds can be represented by various structural formulas. The three-dimensional representation of organic compounds on paper can be drawn by wedge and dash formula. Organic compounds can be classified on the basis of their structure or the functional groups they contain. A functional group is an atom or group of atoms bonded together in a unique fashion and which determines the physical and chemical properties of the compounds. The naming of the organic compounds is carried out by following a set of rules laid down by the International Union of Pure and Applied Chemistry (IUPAC). In IUPAC nomenclature, the names are correlated with the structure in such a way that the reader can deduce the structure from the name. Organic reaction mechanism concepts are based on the structure of the substrate molecule, fission of a covalent bond, the attacking reagents, the electron displacement effects and the conditions of the reaction. These organic reactions involve breaking and making of covalent bonds. A covalent bond may be cleaved in heterolytic or homolytic fashion. A heterolytic cleavage yields carbocations or carbanions, while a homolytic cleavage gives free radicals as reactive intermediate. Reactions proceeding through heterolytic cleavage involve the complementary pairs of reactive species. These are electron pair donor known as nucleophile and an electron pair acceptor known as electrophile. The inductive, resonance, electromeric and hyperconjugation effects may help in the polarization of a bond, making certain carbon atom or other atom positions as places of low or high electron densities. Organic reactions can be broadly classified into following types: substitution, addition, elimination and rearrangement reactions. Purification, qualitative and quantitative analysis of organic compounds are carried out for determining their structures. The methods of purification, namely, sublimation, distillation and differential extraction, are based on the difference in one or more physical properties. Chromatography is a useful technique of separation, identification and purification of compounds. It is classified into two categories: adsorption and partition chromatography. Adsorption chromatography is based on differential adsorption of various components of a mixture on an adsorbent. Partition chromatography involves continuous partitioning of the components of a mixture between stationary and mobile phases. After getting the compound in a pure form, its qualitative analysis is carried out for detection of elements present in it. Nitrogen, sulfur, halogens and phosphorus are detected by Lassane's test. Carbon and hydrogen are estimated by determining the amounts of carbon dioxide and water produced. Nitrogen is estimated by Dumas or Calvel's method and halogens by Carius' method. Sulfur and phosphorus are estimated by oxidizing them to sulfuric and phosphoric acids respectively. The percentage of oxygen is usually determined by difference between the total percentage 100 and the sum of percentages of all other elements present. 370 Chemistry Exercises 12.1 What are hybridization states of each carbon atom in the following compounds: CH2CO, CH3CH2, CH32CO, CH2CHCN, C6H6. 12.2 Indicate the Greek letter sigma and Greek letter pi bonds in the following molecules: C6H6, C6H12, CH2Cl2, CH2CCH2, CH3 number 2, CONH3. 12.3 Write bond line formulas for isopropyl alcohol, 2, 3-dimethylbutanol, heptane 4-1. 12.4 Give the IUPAC names of the following compounds: ABCDEFCl2CHCH2O. 12.5 Which of the following represents the correct IUPAC name for the compounds concerned? 2,2-dimethylpentane or 2-dimethylpentane B2, 4, 7-trimethyl-octane or 2, 5, 7-trimethyl-octane C2 chloro-4-methylpentane or 4-chloro-2-methylpentane D but 3 in 1 all or but 4 all 1 in. 12.6 Draw formulas for the first 5 members of each homologous series beginning with the following compounds: AHQBCH3 COC3CHCHCH2. 12.7 Give condensed and bond line structural formulas and identify the functional group S present, if any, for a 2,2,4-trimethylpentane B2 hydroxy 1, 2, 3 carboxylic acid C-hexanedyl. 12.8 Identify the functional groups in the following compounds: ABC. 12.9 Which of the two, O2 and CH2CH2O or CH3CH2O is expected to be more stable and why? 12.10 Explain why alkyl groups act as electron donors when attached to a Greek letter pi system. 12.11 Draw the resonance structures for the following compounds. Show the electron shift using curved arrow notation. A C6H5O BC6H5 number 2 CCH3CHCHCHOD C6H5 CHO E652 CHCHF3 2 CHCHCHCH. 12.12 What are electrophiles and nucleophiles? Explain with examples. 12.13 Identify the reagents shown in bold in the following equations as nucleophiles or electrophiles. A 332CH2CHCOOHOH. 371 Organic chemistry. Some basic principles and techniques. B3332CH COC CHCCNOCNC66653CH CH COC 3CHCO. 12.14 Classify the following reactions in one of the reaction types studied in this unit. A 3232CHCHBRHSCHCHSHBR B32332 2CHCCHHCLCCHCCHC3222 CHCHBRHOCHCHHOBRDCHCCHOHBRCHCBRCHCHCHO 332322232. 12.15 What is the relationship between the members of following pairs of structures? Are they structural or geometrical isomers or resonance contributors? Of BC. 12.16 For the following bond cleavages, use curved arrows to show the electron flow and classify each as homolysis or heterolysis. Identify reactive intermediate produced as free radical, carbocation and carbanion. Of BCD. 12.17 Explain the terms inductive and electromeric effects. Which electron displacement effect explains the following correct orders of acidity of the carboxylic acids? A Cl3CCOOH, Cl2CHCOOH, ClCH2CuBCH3CH2Cu, CH32CHCOOH, CH33CQ. 12.18 Give a brief description of the principles of the following techniques, taking an example in each case. A crystallization. B distillation. C chromatography. 12.19 Describe the method, which can be used to separate two compounds with different solubilities in a solvent. S. 12.20 What is the difference between distillation under reduced pressure and steam distillation? 372 Chemistry. 12.21 Discuss the chemistry of Lassane's test. 12.2 To differentiate between the principle of estimation of nitrogen in an organic compound by I. Dumas method and 2. Cavell's method. 12.23 Discuss the principle of estimation of halogens, sulfur and phosphorus present in an organic compound. 12.24 Explain the principle of paper chromatography. 12.25 Why is nitric acid added to sodium extract before adding silver nitrate for testing halogens? 12.26 Explain the reason for the fusion of an organic compound with metallic sodium for testing nitrogen, sulfur and halogens. 12.27 Name a suitable technique of separation of the components from a mixture of calcium sulfate and camphor. 12.28 Explain why an organic liquid vaporizes at a temperature below its boiling point in its steam distillation. 12.29 Will CCl4 give white precipitate of AgCl on heating it with silver nitrate? Give reason for your answer. 12.30 Why is a solution of potassium hydroxide used to absorb carbon dioxide evolved during the estimation of carbon present in an organic compound? 12.31 Why is it necessary to use acetic acid and not sulfuric acid for acidification of sodium extract for testing sulfur by lead acetate test? 12.32 An organic compound contains 69 carbon and 4.8 hydrogen, the remainder being oxygen. Calculate the masses of carbon dioxide and water produced when 0.20 grams of this substance is subjected to complete combustion. 12.33 A sample of 0.50 grams of an organic compound was treated according to Cavell's method. The ammonia evolved was absorbed in 50 milliliters of 0.5 mH2SO4. The residual acid required 60 milliliters of 0.5 m solution of NaO for neutralization. Find the percentage composition of nitrogen in the compound. 12.34 0.3780 grams of an organic chloro compound gave 0.5740 grams of silver chloride in Carius estimation. Calculate the percentage of chlorine present in the compound 12.35 in the estimation of sulfur by Carius method. 0.468 grams of an organic sulfur compound afforded 0.668 grams of barium sulfate. Find out the percentage of sulfur in the given compound 12.36 in the organic compound CH2CH, CH2CH2CCH. The pair of hydrogen orbitals involved in the formation of C2C3 bond is sp, sp2b sp3c sp2 sp3d sp3 sp3 12.37 in the Lassane's test for nitrogen in an organic compound. The Prussian blue color is obtained due to the formation of Na4Fe-CN6b Fe4Fe-CN6 3c Fe2Fe-CN6d Fe3Fe-CN6 12.38 Which of the following carbocation is most stable? A CH33C. CH2B CH33C CH3 CH2 CH2D CH3 CH2 CH3 12.39 The best and latest technique for isolation, purification and separation of organic compounds is A. Crystallization, B. Distillation, C. Sublimation, D. Chromatography 12.40 The reaction CH3CH2I coax CH3CH2O key is classified as A. Electrophilic substitution, B. Nucleophilic substitution, C. Elimination, D. Addition. Unit 13 After studying this unit, you will be able to name hydrocarbons according to IUPAC system of nomenclature, recognize and write structures of isomers of alkanes, alkenes, alkynes and aromatic hydrocarbons, learn about various methods of preparation of hydrocarbons, distinguish between alkanes, alkenes, alkynes and aromatic hydrocarbons on the basis of physical and chemical properties, draw and differentiate between various conformations of ethane, appreciate the role of hydrocarbons as sources of energy and for other industrial applications, predict the formation of the addition products of unsymmetrical alkenes and alkynes on the basis of electronic mechanism, comprehend the structure of benzene, explain aromaticity and understand mechanism of electrophilic substitution reactions of benzene, predict the directive influence of substituents in monosubstituted benzene ring, learn about carcinogenicity and toxicity. Hydrocarbons. The term hydrocarbon is self-explanatory, which means compounds of carbon and hydrogen only. Hydrocarbons play a key role in our daily life. You must be familiar with the terms LPG and CNG used as fuels. LPG is the abbreviated form of liquefied petroleum gas, whereas CNG stands for compressed natural gas. Another term, LNG, liquefied natural gas, is also in use these days. This is also a fuel and is obtained by liquefaction of natural gas. Petrol, diesel and kerosene oil are obtained by the fractional distillation of petroleum found under the Earth's crust. Coal gas is obtained by the destructive distillation of coal. Natural gas is found in upper strata during drilling of oil wells. The gas after compression is known as compressed natural gas. LPG is used as a domestic fuel with the least pollution. Kerosene oil is also used as a domestic fuel, but it causes some pollution. Automobiles need fuels like petrol, diesel and CNG. Petrol and CNG operated automobiles cause less pollution. All these fuels contain mixture of hydrocarbons, which are sources of energy. Hydrocarbons are also used for the manufacture of polymers like polythene, polypropylene, polystyrene, etc. Higher hydrocarbons are used as solvents for paints. They are also used as the starting materials for manufacture of many dyes and drugs. Thus, you can well understand the importance of hydrocarbons in your daily life. In this unit, you will learn more about hydrocarbons. 13.1 Classification. Hydrocarbons are of different types. Depending upon the types of carbon-carbon bonds present, they can be classified into three main categories. Isaturated hydrocarbons are the important sources of energy. 374 Chemistry. 2 unsaturated and 3 aromatic hydrocarbons. Saturated hydrocarbons contain carbon-carbon and carbon-hydrogen single bonds. If different carbon atoms are joined together to form open chain of carbon atoms with single bonds, they are termed as alkanes, as you have already studied in Unit 12. On the other hand, if carbon atoms form a closed chain or a ring, they are termed as cycloalkanes. Unsaturated hydrocarbons contain carbon-carbon multiple bonds, double bonds, triple bonds, or both. Aromatic hydrocarbons are a special type of cyclic compounds. You can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. For making models of alkanes, you can use toothpicks for bonds and plasticine balls for atoms. For alkenes, alkynes and aromatic hydrocarbons, spring models can be constructed. 13.2 Alkanes. As already mentioned, alkanes are saturated open-chain hydrocarbons containing carbon-carbon single bonds. Methane CH4 is the first member of this family. Methane is a gas found in coal mines and marshy places. If you replace one hydrogen atom of methane by carbon and join the required number of hydrogens to satisfy the tetravalence of the other carbon atom, what do you get? You get C2H6. This hydrocarbon with molecular formula C2H6 is known as ethane. Thus you can consider C2H6 as derived from CH4 by replacing one hydrogen atom by CH3 group. Go on constructing alkanes by doing this theoretical exercise, that is, replacing hydrogen atom by CH3 group. The next molecules will be C3H8, C4H10. These hydrocarbons are inert under normal conditions as they do not react with acids, bases and other reagents. Hence, they were earlier known as paraffins, Latin, param, little, affinis, affinity. Can you think of the general formula for alkane family or homologous series? If we examine the formula of different alkanes, we find that the general formula for alkanes is CnH2n2. It represents any particular homologue when n is given appropriate value. Can you recall the structure of methane according to VSEPR theory unit 4? Methane has a tetrahedral structure Fig. 13.1, in which carbon atom lies at the center and the 4 hydrogen atoms lie at the 4 corners of a regular tetrahedron. All HCH bond angles are of 109.5 degrees. In alkanes, tetrahedra are joined together in which CC and CH bond lengths are 154 pm and 112 pm respectively unit 12. You have already read that CC and CH Greek letter sigma bonds are formed by head-on overlapping of sp3 hybrid orbitals of carbon and 1s orbitals of hydrogen atoms. 1.3.2.1 Nomenclature and isomerism. You have already read about nomenclature of different classes of organic compounds in Unit 12. Nomenclature and isomerism in alkanes can further be understood with the help of a few more examples. Common names are given in parenthesis. First 3 alkanes, methane, ethane and propane have only one structure, but higher alkanes can have more than one structure. Let us write structures for C4H10. 4 carbon atoms of C4H10 can be joined either in a continuous chain or with a branched chain in the following 2 ways. Fig. 13.1 Structure of methane, butane and butane. B page 273 Ki. 375 hydrocarbons. In how many ways? You can join 5 carbon atoms and 12 hydrogen atoms of C5H12. They can be arranged in 3 ways as shown in structures IIIV structures. They are known as structural isomers. It is also clear that structures I and 3 have continuous chain of carbon atoms, but structures 2, IV and V have a branched chain. Such structural isomers which differ in chain of carbon atoms are known as chain isomers. Thus, you have seen that C4H10 and C5H12 have 2 and 3 chain isomers respectively. Problem 13.1 Write structures of different chain isomers of alkanes corresponding to the molecular formula C6H14. Also write their IUPAC names. Solution ICH3CH2CH2CH2CH2CH3 N-hexane 2-methylpentane 3-methylpentane 2. 3-dimethylbutane 2. 2-dimethylbutane. Based upon the number of carbon atoms attached to a carbon atom, the carbon atom is termed as primary x 31 degree, secondary 2 degrees, tertiary 3 degrees or quaternary 4 degrees. Carbon atom attached to no other carbon atom as in methane or to only one carbon atom as in ethane is called primary carbon atom. Terminal carbon atoms are always primary. Carbon atom attached to 2 carbon atoms is known as secondary. Tertiary carbon is attached to 3 carbon atoms and neo or quaternary carbon is attached to 4 carbon atoms. Can you identify x 31 degree, 2 degrees, 3 degrees and 4 degrees carbon atoms in structures I2 2-methylpropane isobutane B page 261 K? Structures I and 2 possess same molecular formula but differ in their boiling points and other properties. Similarly, structures 3, IV and V possess the same molecular formula but have different properties. Structures I and 2 are isomers of butane, whereas structures 3, IV and V are isomers of pentane. Since difference in properties is due to difference in their 3-pentane and pentane B page 309 K 2-methylbutane isopentane BP. 301 K IV2, 2-dimethylpropane neopentane B page 282.5 kV. 376 Chemistry to V. If you go on constructing structures for higher alkanes, you will be getting still larger number of isomers. C6H14 has got 5 isomers and C7H16 has 9. As many as 75 isomers are possible for C10H22. In structures 2, IV and V, you observe that CH3 group is attached to carbon atom numbered as 2. You will come across groups like CH3, C2H5, C3H7 etc. attached to carbon atoms in alkanes or other classes of compounds. These groups or substituents are known as alkyl groups as they are derived from alkanes by removal of one hydrogen atom. General formula for alkyl groups is CnH2n1 Unit 12. Let us recall the general rules for nomenclature already discussed in Unit 12. Nomenclature of substituted alkanes can further be understood by considering the following problem. Problem 13.2. Write structures of different isomeric alkyl groups corresponding to the molecular formula C5H11. Write IUPAC names of alcohols obtained by attachment of O groups at different carbons of the chain. Solution structures of C5H11 group corresponding alcohols. Name of alcohol ICH3CH2CH2CH2CH2CH3CH2CH2CH2O pentan 1 ol 2 CH3CH CH2CH2CH3CH CH2CH2CH3 pentan 2 ol 3 CH3CH2CH CH2CH3CH3CH2CH CH2CH3 pentan 3 ol CH3CH3 methylbutan 1 olive CH3CH CH2CH2CH3CH CH2CH2O CH3CH3 2 methylbutan 1 ol VCH3CH2CH CH2CH3CH2CH CH2O CH3CH3 2 methyl butan 2 ol VCH3C CH2CH3CH3C CH2CH3O CH3CH3 2 2-dimethylpropan 1 ol 7 CH3C CH2CH3C CH2O CH3CH3CH3CH3O3 methylbutan 2 ol 8 CH3CH CHCH3CH3CH CHCH3 377 Hydrocarbons. Remarks. Lowest sum and alphabetical arrangement. Lowest sum and alphabetical arrangement. Sec is not considered while arranging alphabetically. Isopropyl is taken as one word. Further number into the substituents of the side chain. Alphabetical priority order. Table 13.1 Nomenclature of a few organic compounds. Important to write the correct structure from the given IUPAC name. To do this, first of all, the longest chain of carbon atoms corresponding to the parent alkane is written. Then after numbering it, the substituents are attached to the correct carbon atoms, and finally valence of each carbon atom is satisfied by putting the correct number of hydrogen atoms. This can be clarified by writing the structure of 3-ethyl 2,2-dimethylpentane in the following steps. I draw the chain of 5 carbon atoms, C, 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 C to give number to carbon atoms, C1, C2, C3, C4, C5 structure and IUPAC name A1 CH3-2 CH3 CH24 CH5 CH26 CH34 ethyl 2-methylhexane B8 CH37 CH26 CH25 CH4 CH3 C2 CH21 CH33 3-diethyl 5-isopropyl 4-methyloctane C1 CH3-2 CH2-3 CH2-4 CH5 CH6 CH2-7 CH2-8 CH2-9 CH2-10 CH3 5 seconds butyl 4-isopropyldecane D1 CH3-2 CH2-3 CH2-4 CH2-5 CH6 CH2-7 CH2-8 CH2-9 CH3 5 2-dimethylpropyl non-ane 1 CH3 2 CH2 3 CH4 CH2 5 CH6 CH2 7 CH3 3-ethyl 5-methylheptane. Problem 13.3 Write IUPAC names of the following compounds. ICH33 CCH2 CCH33 2 CH32 CC2H523 tetraterbutylmethane solution I2 2 4 4-tetramethylpentane 2 3 3-dimethylpentane 3 3 3-D-tertbutyl 2 2 4 4-tetramethylpentane. If it is important to write the correct IUPAC name for a given structure, it is equally 378 Chemistry 3 Attach ethyl group at carbon 3 and 2 methyl groups at carbon 2 3 CH C1 2 C3 C4 C5 C3 CH2 5 CH. Satisfy the valence of each carbon atom by putting requisite number of hydrogen atoms 3 CH CH3 C CH CH2 CH3 3 CH2 5 CH. Thus we arrive at the correct structure. If you have understood writing of structure from the given name, attempt the following problems. Problem 13.4 Write structural formulas of the following compounds. I3, 4, 4, 5-tetramethylheptane 2 2. 5-dimethylhexane solution ICH3CH2CH, C, CHCH, CH32CH3CH, CH2CH2CH, CH3. Problem 13.5 Write structures for each of the following compounds. Why are the given names incorrect? Write correct IUPAC names. I2-ethylpentane 2,5-ethylthree-methylheptane solution ICH3CH, CH2CH2CH3. Longest chain is of 6 carbon atoms and not that of 5. Hence, correct name is 3-methylhexane 7,6,5,4,3,2,1,2 CH3CH2CH, CH2CH, CH2CH3 numbering is to be started from the end, which gives lower number to ethyl group. Hence, correct name is 3-ethyl-5-methylheptane 1,3,2. 2 Preparation. Petroleum and natural gas are the main sources of alkanes. However, alkanes can be prepared by following methods. 1. From unsaturated hydrocarbons, dihydrogen gas adds 2 alkenes and alkynes in the presence of finely divided catalysts like platinum, palladium or nickel to form alkanes. This process is called hydrogenation. These metals adsorb dihydrogen gas on their surfaces and activate the hydrogen-hydrogen bond. Platinum and palladium catalyze the reaction at room temperature, but relatively higher temperature and pressure are required with nickel catalysts. 22233 PTPD niche CHHCHCH ethene 13.132233 PTPD niche CHCHHCHCH propene 13.232323 PTPD niche CCH2HCHCHCH propine 13.32. From alkyl halides, alkyl halides except fluorides on reduction with zinc and dilute hydrochloric acid give alkanes. 324ZN, HCHCl HCHHCl 13.4 chloromethane methane. 379 hydrocarbons 25226ZN, HCHCl HCHHCl chlorothane ethane 13.53222323ZN. HCHCHCHCl HCHCHCHCHCl1 chloropropane propane 13.62 alkyl halides on treatment with sodium metal and dry ethereal free from moisture solution give higher alkanes. This reaction is known as Wirtz reaction and is used for the preparation of higher alkanes containing even number of carbon atoms. 3333 dry ether CHBr2 Na Br CHCHCH2 Na Br bromomethane ethane 13.7252525525 dry ether CHBr2 Na Br CHCHCH bromothane and butane 13.8. What will happen if 2 different alkyl halides are taken? 3. From carboxylic acids, isodium salts of carboxylic acids on heating with soda-lime mixture of sodium hydroxide and calcium oxide give alkanes containing 1 carbon atom less than the carboxylic acid. This process of elimination of carbon dioxide from a carboxylic acid is known as decarboxylation. CaO3,4,2,3 non-AOCH NaCO sodium ethanoate problem 13.6 sodium salt, of which acid will be needed for the preparation of propane. Write chemical equation for the reaction. Solution butanoic acid. 322322323 KOCHCHCHCOO non-AOCHCHCH NaCO2 Kolbe's electrolytic method. An aqueous solution of sodium or potassium salt of a carboxylic acid on electrolysis gives alkane containing even number of carbon atoms at the anode. 323322 electrolysis 2CHCOO Na2HO sodium acetate CHCH2COH2 NaO 13.9. The reaction is supposed to follow the following path. 330I2CHCOO Na2CHCO2 Na2 at anode. 3332-2EOO2CHCO2CHCO2CH2CO acetate ion acetate methyl free radical 33333 HCCHHCCH IV cathode 22HOEOH2HH. Methane cannot be prepared by this method. Why? 1.3.2. 3 properties. Physical properties. Alkanes are almost nonpolar molecules because of the covalent nature of CC and CH bonds and due to very little difference of electronegativity between carbon and hydrogen atoms. They possess weak van der Waals forces. Due to the weak forces, the first 4 members, C1 to C4 are gases. C5 to C17 are liquids, and those containing 18 carbon atoms or more are solids. At 298 K they are colorless and odorless. What do you think about solubility of alkanes in water? Based upon nonpolar nature of alkanes, petrol is a mixture of hydrocarbons and is used as a fuel for automobiles. Petrol and lower fractions of petroleum are also used for dry cleaning of clothes to remove grease stains. On the basis of this observation, what do you think about the nature of the greasy substance? You are correct if you say that grease mixture of higher. 380 Chemistry. Alkanes is nonpolar and, hence, hydrophobic in nature. It is generally observed that in relation to solubility of substances in solvents, polar substances are soluble in polar solvents, whereas the nonpolar ones in nonpolar solvents, that is, like dissolves like. Boiling point BP of different alkanes are given in table 13.2, from which it is clear that there is a steady increase in boiling point with increase in molecular mass. This is due to the fact that the intermolecular van der Waals forces increase with increase of the molecular size or the surface area of the molecule. You can make an interesting observation by having a look on the boiling points of 3 isomeric pentanes, viz., pentane, 2-methylbutane and 2,2-dimethylpropane. It is observed table 13.2 that pentane, having a continuous chain of 5 carbon atoms, has the highest boiling point 309.1 K, whereas 2 2-dimethylpropane boils at 282.5 K. With increase in number of branched chains, the molecule attains the shape of a sphere. This results in smaller area of contact and therefore weak intermolecular forces between spherical molecules, which are overcome at relatively lower temperatures. Chemical properties. As already mentioned, alkanes are generally inert towards acids, bases, oxidizing and reducing agents. However, they undergo the following reactions under certain conditions. 1. Substitution reactions. One or more hydrogen atoms of alkanes can be replaced by halogens, nitro group and sulfonic acid group. Halogenation takes place either at higher temperature 573-773 K or in the presence of diffused sunlight or ultraviolet light. Lower alkanes do not undergo nitration and sulfonation reactions. These reactions in which hydrogen atoms of alkanes are substituted are known as substitution reactions. As an example, chlorination of methane is given below. Halogenation 4,2,3-CHCl-CHCl-HCl chloromethane 13.10322-CHCl-CL-CHCl-HCl dichloromethane 13.11222-3CHCl-CL-CHCl-HCl terchloromethane 13.12324-CHCl-CL-CCl-HCl tetrachloromethane 13.13. Table 13.2 Variation of melting point and boiling point in alkanes. Molecular name, molecular BPK NPK formula, mass UCH4 methane 161111090 C2H6 ethane 3184.4101.0 C3H8 propane 442309853 C4H10 butane 582724134 134 C4H10 2 methylpropane 582610114 C5H12 pentane 723091143 C5H12 2-methylbutane 723009113 C5H12 2-dimethylpropane 72282252564 C6H14 hexane 863419178 C7H16 heptane 100-371.4 182.4 C8H18 octane 114-398.7 216.2 C9H20 nonane 128-423.8 222.0 C10H22 decane 142-447.1 243.3 C20H42 ecosane 282-615.0 236.2 381 hydrocarbons 33232 CHCHCl-CHCHCl-HCl chlorothane 13.14 It is found that the rate of reaction of alkanes with halogens is F2, Cl2, Br2, I2. Rate of replacement of hydrogens of alkanes is 3 degrees, 2 degrees, x 31 degree. Fluorination is too violent to be controlled. Iodination is very slow and a reversible reaction. It can be carried out in the presence of oxidizing agents like HO3 or HNO3. 423CHICHI high 13.15322 HEO5 high 3I3HO 13.16 Halogenation is supposed to proceed via free radical chain mechanism involving 3 steps, namely initiation, propagation and termination is given below. Mechanism: I initiation. The reaction is initiated by homolysis of chlorine molecule in the presence of light or heat. The Cl-Cl bond is weaker than the Cc and Ch bond and hence, is easiest to break. Homolysis Cl-Cl-Cl-Cl chlorine free radicals. 2. Propagation. Chlorine free radical attacks the methane molecule and takes the reaction in the forward direction by breaking the CH bond to generate methyl free radical with the formation of HCl. 4.3 A Cl-CH-HCl-CH. The methyl radical thus obtained attacks the second molecule of chlorine to form CH3Cl with the liberation of another chlorine free radical by homolysis of chlorine molecule. H33BCHCl-CL-CHCl-Cl chlorine free radical. Greek letter nu. The chlorine and methyl free radicals generated above repeat steps A and B respectively and thereby set up a chain of reactions. The propagation steps A and B are those which directly give principal products, but many other propagation steps are possible and may occur. 2 such steps given below explain how more highly halogenated products are formed. 32222 CHCl-CL-CHCl-CHCl-CL-CHCl-CL. 3 Termination. The reaction stops after some time due to consumption of reactants and or due to the following side reactions. The possible chain terminating steps are A Cl-Cl-Cl-Cl, B3333HCCH-HCCH, C33HCCl-HCCl, DO and C, CH3Cl. The one of the products is formed but free radicals are consumed and the chain is terminated. The above mechanism helps us to understand the reason for the formation of ethane as a byproduct during chlorination of methane. 2. Combustion alkanes on heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. 42221 CCH2OGCOG2HOL, 890 kmol HV 13.174 102221 CCHG132OG4COG5HOL, 2875.84 kjmol HV 13.18. The general combustion equation for any alkane is N2N22223N1CHONCON1HO2 13.19. Due to the evolution of large amount of heat during combustion, alkanes are used as fuels. During incomplete combustion of alkanes with insufficient amount of air or dioxygen, carbon black is formed, which is used in the manufacture of ink, printer ink, black pigments, and as filters. 382 Chemistry 422 Incomplete combustion CHGOGCS2HOL 13.203. Controlled oxidation alkanes on heating with a regulated supply of dioxygen or air at high pressure and in the presence of suitable catalysts give a variety of oxidation products. 423 Q523 K100 ATMI2CHO2CHO methanol 13.21422223 MO02CHOHCHOHO methanol 13.223322CHCOOMN32CHCH3O2CH2 ethanoic acid 2HO 13.23 IV. Ordinarily alkanes resist oxidation, but alkanes having tertiary H atom can be oxidized to corresponding alcohols by potassium permanganate. 33334 kMNO oxidation 2-methylpropane 2-methylpropanterol CHCHCH Ca 13.244. Isomerization and alkanes on heating in the presence of anhydrous aluminium chloride and hydrogen chloride gas isomerase to branched chain alkanes. Major products are given below. Some minor products are also possible which you can think over. Minor products are generally not reported in organic reactions. 3243322332233 and He. Al-ClHCl 2-methylpentane 3-methylpentane CHCHCH hexane CHCHCHCHCHCHCHCHCHCHCHCHN 13.255. Aromatization and alkanes having 6 or more carbon atoms on heating to 773 K at 1020 atmospheric pressure in the presence of oxides of vanadium, molybdenum or chromium supported over alumina get dehydrogenated and cyclized to benzene and its homologs. This reaction is known as aromatization or reforming. 13.26 Toluene C7H8 is methyl derivative of benzene. Which alkane do you suggest for preparation of toluene 6? Reaction with steam. Methane reacts with steam at 1273 K in the presence of nickel catalyst to form carbon monoxide and dihydrogen. This method is used for industrial preparation of dihydrogen gas 422-NiCHOCO3H 13.277. Pyrolysis. Higher alkanes on heating to higher temperature decompose into lower alkanes, alkenes, etc. Such a decomposition reaction into smaller fragments by the application of heat is called pyrolysis or cracking. 13.28 Pyrolysis of alkanes is believed to be a free radical reaction. Preparation of oil gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. For example, dodecane, a constituent of kerosene oil on heating to 973 K in the presence of platinum, palladium or nickel gives a mixture of heptane and pentene. 1226 7 16 5 10 PTPD Ni 973 K. Other CHCHCH products: dodecane, heptane, pentene 13.29. 383 Hydrocarbons 1 3 2 4 conformations. Alkanes contain carbon-carbon sigma Greek letter sigma bonds. Electron distribution of the sigma molecular orbital is symmetrical around the internuclear axis of the CC bond, which is not disturbed due to rotation about its axis. This permits free rotation about CC single bond. This rotation results into different spatial arrangements of atoms in space which can change into one another. Such spatial arrangements of atoms which can be converted into one another by rotation around a CC single bond are called conformations or conformers or autamers. Alkanes can thus have infinite number of conformations by rotation around CC single bonds. However, it may be remembered that rotation around a CC single bond is not completely free. It is hindered by a small energy barrier of 120 kJ-mol-1 due to weak repulsive interaction between the adjacent bonds. Such a type of repulsive interaction is called torsional strain. Conformations of ethane. Ethane molecule C2H6 contains a carbon-carbon single bond with each carbon atom attached to 3 hydrogen atoms. Considering the ball and stick model of ethane, keep one carbon atom stationary and rotate the other carbon atom around the CC axis. This rotation results into infinite number of spatial arrangements of hydrogen atoms attached to one carbon atom with respect to the hydrogen atoms attached to the other carbon atom. These are called conformational isomers, conformers. Thus there are infinite number of conformations of ethane. However, there are 2 extreme cases. One such conformation in which hydrogen atoms attached to two carbons are as close together as possible is called eclipsed conformation, and the other in which hydrogens are as far apart as possible is known as the staggered conformation. Any other intermediate conformation is called a skew conformation. It may be remembered that in all the conformations, the bond angles and the bond lengths remain the same. Eclipsed and the staggered conformations can be represented by Saharas and Newman projections. 1. Saharas projections. In this projection, the molecule is viewed along the molecular axis. It is then projected on paper by drawing the central CC bond as a somewhat longer straight line. Upper end of the line is slightly tilted towards right or left-hand side. The front carbon is shown at the lower end of the line, whereas the rear carbon is shown at the upper end. Each carbon has 3 lines attached to it corresponding to 3 hydrogen atoms. The lines are inclined at an angle of 120 degrees to each other. Saharas projections of eclipsed and staggered conformations of ethane are depicted in figure 13.2. 2. Newman projections. In this projection, the molecule is viewed at the CC bond head-on. The carbon atom nearer to the eye is represented by a point. 3 hydrogen atoms attached to the front carbon atom are shown by 3 lines drawn at an angle of 120 degrees to each other. The rear carbon atom away from the eye is represented by a circle, and the 3 hydrogen atoms are shown attached to it by the shorter lines drawn at an angle of 120 degrees to each other. The Newman's projections are depicted in figure 13.3. Figure 13.2 Saharas projections of ethane. Fig. 13.3 Newman's projections of ethane. 384 Chemistry. Figure 13.4 Orbital picture of ethene depicting Greek letter sigma bonds. Only relative stability of conformations, as mentioned earlier. In staggered form of ethane, the electron clouds of carbon-hydrogen bonds are as far apart as possible. Thus, there are minimum repulsive forces, minimum energy and maximum stability of the molecule. On the other hand, when the staggered form changes into the eclipsed form, the electron clouds of the carbon-hydrogen bonds come closer to each other, resulting in increase in electron cloud repulsions. To check the increased repulsive forces, molecule will have to possess more energy and thus has lesser stability. As already mentioned, the repulsive interaction between the electron clouds, which affects stability of a conformation, is called torsional strain. Magnitude of torsional strain depends upon the angle of rotation about CC bond. This angle is also called dihedral angle or torsional angle. Of all the conformations of ethane, the staggered form has the least torsional strain, and the eclipsed form, the maximum torsional strain. Therefore, staggered conformation is more stable than the eclipsed conformation. Hence, molecule largely remains in staggered conformation, or we can say that it is preferred conformation. Thus it may be inferred that rotation around CC bond in ethane is not completely free. The energy difference between the two extreme forms is of the order of 12.5 kJ-mol-1, which is very small. Even at ordinary temperatures, the ethane molecule gains thermal or kinetic energy sufficient enough to overcome this energy barrier of 12.5 kJ-mol-1 through intermolecular collisions. Thus, it can be said that rotation about carbon-carbon single bond in ethane is almost free for all practical purposes. It has not been possible to separate and isolate different conformational isomers of ethane. 13.3 Alkenes. Alkenes are unsaturated hydrocarbons containing at least one double bond. What should be the general formula of alkenes? If there is one double bond between 2 carbon atoms in alkenes, they must possess 2 hydrogen atoms less than alkanes. Hence, general formula for alkenes is CnH2n. Alkenes are also known as olefins, oil forming, since the first member, ethylene or ethene C2H4, was found to form an oily liquid on reaction with chlorine. 133. One structure of double bond carbon-carbon double bond in alkenes consists of one strong sigma Greek letter sigma bond enthalpy about 397 kJ-mol-1 due to head-on overlapping of sp2 hybridized orbitals, and one weak pi Greek letter pi bond enthalpy about 284 kJ-mol-1 obtained by lateral or sideways overlapping of the two 2p orbitals of the 2 carbon atoms. The double bond is shorter in bond length 134 pm than the CC single bond 154 pm. You have already read that the pi Greek letter pi bond is a weaker bond due to poor sideways overlapping between the two 2p orbitals. Thus, the presence of the pi Greek letter pi bond makes alkenes behave as sources of loosely held mobile electrons. Therefore, alkenes are easily attacked by reagents or compounds which are in search of electrons. Such reagents are called electrophilic reagents. The presence of weaker Greek letter pi bonds makes alkenes unstable molecules in comparison to alkanes, and thus, alkenes can be changed into single bond compounds by combining with the electrophilic reagents. Strength of the double bond enthalpy, 681 kJ-mol-1, is greater than that of a carbon-carbon single bond in ethane. Bond enthalpy, 348 kJ-mol-1. Orbital diagrams of ethene molecule are shown in figures 13.4 and 13.5. 1.3.3. 2. Nomenclature. For nomenclature of alkenes in IUPAC system, the longest chain of carbon atoms containing the double bond is selected. Numbering of the chain is done from the end which is nearer to 385 hydrocarbons. The double bond, the suffix -ene replaces -ane of alkanes. It may be remembered that first member of alkene series is CH2 replacing N by 1 in CnH2n, known as methene, but has a very short life. As already mentioned, first stable member of alkene series is C2H4, known as ethylene common or ethene IUPAC. IUPAC names of a few members of alkenes are given below. Structure: IUPAC name CH3CH2 propene CH3CH2 but LENECH3CH CH3 but 2 ENECH2CH CH2 but 1 3 diene CH2C CH3 2 methyl prop 1 ENECH3CH2CH CH3 3 methyl but 1 ENECH3. Problem 13.7. Write IUPAC names of the following compounds: ICH3 2CH CHCH CH2CHY CH3CH CHC2H523 CH2C CH2CH2 CH3 2IB CH3 CH2 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 CH3 CH3 CHCHC CH2 CH3 CH3. Solution: I2 8 dimethyl 3 6 decadene 2 1 3 5 7 octatetraene 3 2N propylpent 1 ENE I4 ethyl 2 6 dimethyl December 4 ENE. Problem 13.8. Calculate number of sigma Greek letter sigma and pi Greek letter pi bonds in the above structures. I5. Solution: Greek letter sigma bonds 33, Greek letter pi bonds 2, Greek letter sigma bonds 17, Greek letter pi bonds 4, Greek letter sigma bonds 23, Greek letter pi bond 1, Greek letter sigma bonds 41, Greek letter pi bond 113. 3. Isomerism. Alkenes show both structural isomerism and geometrical isomerism. Structural isomerism, as in alkanes, ethene C2H4 and propene C3H6 can have only one structure, but alkenes higher than propene have different structures. Alkenes possessing C4H8's molecular formula can be written in the following three ways: I1,2,3,4 CH2CH, CH2CH3 but 1 ENEC4H8 1,2,3,4 CH3CH, CH3 but 2 ENEC4H8. Figure 13.5. Orbital picture of ethene showing formation of a Greek letter pi bond. B Greek letter pi cloud and C bond angles and bond lengths. 386. Chemistry 3, 1 2 3 CH2C, CH3 2 methyl 1 ENEC4H8. Structures I and 3 and 2 and 3 are the examples of chain isomerism, whereas structures I and 2 are position isomers. Problem 13.9. Write structures and IUPAC names of different structural isomers of alkenes corresponding to C5H10. Solution: a CH2CH, CH2CH2CH3 pent 1 ENEBCH3CHCH, CH2CH3 pent 2 ENECCH3CCH, CH3CH3 2 methyl but 2 ENEDCH3CH, CHCH2CH3 3 methyl but 1 ENECH2C, CH2CH3 2 methyl but 1 ENE. Geometrical isomerism. Doubly bonded carbon atoms have to satisfy the remaining two valences by joining with two atoms or groups. If the two atoms or groups attached to each carbon atom are different, they can be represented by YXCCXY-like structure. YXCCXY can be represented in space in the following two ways: in A, the two identical atoms, that is, both the X or both the Y lie on the same side of the double bond, but in B the two X or two Y lie across the double bond or on the opposite sides of the double bond. This results in different geometry of A and B, that is, disposition of atoms or groups in space in the two arrangements is different. Therefore, they are stereoisomers. They would have the same geometry if atoms or groups around CC bond can be rotated, but rotation around CC bond is not free. It is restricted. For understanding this concept, take two pieces of strong cardboards and join them with the help of two nails. Hold one cardboard in your one hand and try to rotate the other. Can you really rotate the other cardboard? The answer is no. The rotation is restricted. This illustrates that the restricted rotation of atoms or groups around the doubly bonded carbon atoms gives rise to different geometries of such compounds. The stereoisomers of this type are called geometrical isomers. The isomer of the type A, in which two identical atoms or groups lie on the same side of the double bond, is called cis isomer, and the other isomer of the type B, in which identical atoms or groups lie on the opposite sides of the double bond, is called trans isomer. Thus cis and trans isomers have the same structure but have different configuration arrangement of atoms or groups in space. Due to different arrangement of atoms or groups in space, these isomers differ in their properties like melting point, boiling point, dipole moment, solubility, etc. Geometrical or cis-trans isomers of both 2-ene are represented below. Cis form of alkene is found to be more polar than the trans form. For example, dipole moment of cis both 2-ene is 0.33 dBi, whereas dipole moment of the trans form is almost zero, or it can be said that 387 hydrocarbons trans but 2-ene is nonpolar. This can be understood by drawing geometries of the two forms as given below, from which it is clear that in the trans but 2-ene, the two methyl groups are in opposite directions. Therefore, dipole moments of CCH3 bonds cancel, thus making the trans form nonpolar. 2CH2CBr23C6H5CHCH, CH3IVCH3CHCCl CH3 solution 3 and IV. In structures I and II, two identical groups are attached to one of the doubly bonded carbon atom. 1-3-3-4 Preparation 1. From alkynes. Alkynes on partial reduction with calculated amount of dihydrogen in the presence of palladized charcoal partially deactivated with poisons like sulfur compounds or quinoline give alkenes. Partially deactivated palladized charcoal is known as Lindlar's catalyst. Alkenes thus obtained are having cis geometry. However, alkynes on reduction with sodium in liquid ammonia form transalkenes. 13.30 13.313222 PDCCHCHHCHCH 13.32 ethene ethene I3232 PDCCHCCHCHCH propine propene 13.33 will propene thus obtained show geometrical isomerism. Think for the reason in support of your answer. 2. From alkyl halides. Alkyl halides are exon heating with alcoholic potash potassium hydroxide dissolved in alcohol. In the case of solids, it is observed that the trans isomer has higher melting point than the cis form. Geometrical or cis-trans isomerism is also shown by alkenes of the types Zyg-CXZ and Zyg-CZW. Problem 13.10 Draw cis and trans isomers of the following compounds. Also write their IUPAC names: ICHCl-CHCl2C2H5CCH3CCH3C2H5 Solution Problem 13.11 Which of the following compounds will show cis-trans isomerism? ICH32CCH, C2H5 cis but 2-ene micro 0.33D trans but 2-ene micro 0. 388 Chemistry say, ethanol eliminate one molecule of halogen acid to form alkenes. This reaction is known as dehydrohalogenation, that is, removal of halogen acid. This is example of Greek letter beta 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 elimination reaction. Since hydrogen atom is eliminated from the Greek letter beta carbon atom next to the carbon to which halogen is attached. 13.34 Nature of halogen atom in the alkyl group determine rate of the reaction. It is observed that for halogens, the rate is iodine, bromine, chlorine, while for alkyl groups it is tert, secondary, primary. 3. From vicinal dihalides. Dihalides in which two halogen atoms are attached to two adjacent carbon atoms are known as vicinal dihalides. Vicinal dihalides on treatment with zinc metal lose a molecule of ZnX2 to form an alkene. This reaction is known as dehalogenation. 22222CHBr13.3532322CHCHBr CHCHBr 13.364. From alcohols by acidic dehydration. You have read during nomenclature of different homologous series in Unit 12 that alcohols are the hydroxy derivatives of alkanes. They are represented by R, where R is CnH2n1. Alcohols on heating with concentrated sulfuric acid form alkenes with the elimination of one water molecule. Since a water molecule is eliminated from the alcohol molecule in the presence of an acid, this reaction is known as acidic dehydration of alcohols. This reaction is also the example of Greek letter beta elimination reaction, since O group takes out one hydrogen atom from the Greek letter beta carbon atom. 13.3713. 3. 5 Properties. Physical properties. Alkenes as a class resemble alkanes in physical properties, except in types of isomerism and difference in polar nature. The first 3 members are gases, the next 14 are liquids and the higher ones are solids. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless, insoluble in water but fairly soluble in nonpolar solvents like benzene, petroleum ether. They show a regular increase in boiling point with increase in size, that is, every CH2 group added increases boiling point by 20-30 K like alkanes. Straight chain alkenes have higher boiling point than isomeric branched chain compounds. Chemical properties. Alkenes are the rich source of loosely held pi Greek letter pi electrons, due to which they show addition reactions in which the electrophiles add onto the carbon-carbon double bond to form the addition products. Some reagents also add by free radical mechanism. There are cases when under special conditions, alkenes also undergo free radical substitution reactions. Oxidation and ozonolysis reactions are also quite prominent in alkenes. A brief description of different reactions of alkenes is given below. 1. Addition of dihydrogen. Alkenes add up one molecule of dihydrogen gas in the presence of finely divided nickel, palladium or platinum to form alkanes. Section 1.3.2.2.2. Addition of halogens. Halogens like bromine or chlorine add up to alkene to form vicinal dihalides. However, iodine does not show addition reaction under 389 hydrocarbons. Normal conditions. The reddish-orange color of bromine solution in carbon tetrachloride is discharged when bromine adds up to an unsaturation site. This reaction is used as a test for unsaturation. Addition of halogens to alkenes is an example of electrophilic addition reaction involving cyclic haloneum ion formation, which you will study in higher classes. 13.3832322 CHCHCHClClClCHCHCHCl propene 1 to dichloropropane. 13.393. Addition of hydrogen halides. Hydrogen halides HCl, HBr, high add up to alkenes to form alkyl halides. The order of reactivity of the hydrogen halides is high, HBr HCl, like addition of halogens to alkenes. Addition of hydrogen halides is also an example of electrophilic addition reaction. Let us illustrate this by taking addition of HBr to symmetrical and unsymmetrical alkenes. Addition reaction of HBr to symmetrical alkenes. Addition reactions of HBr to symmetrical alkenes. Similar groups attached to double bond take place by electrophilic addition mechanism. 2232 CHCHHBr CHCHBr 13.4033323 CHCHCHCHHBr CHCHCHCHBr 13.41 Addition reaction of HBr to unsymmetrical alkenes. Markovnikov rule. How will HBr add to propene? The two possible products are I and II. 13.42 Markovnikov, a Russian chemist, made a generalization in 1869 after studying such reactions in detail. These generalizations led Markovnikov to frame a rule called Markovnikov rule. The rule states that negative part of the addendum adding molecule gets attached to the carbon atom which possesses lesser number of hydrogen atoms. Thus, according to this rule, product I, that is, 2-bromopropane, is expected. In actual practice, this is the principal product of the reaction. This generalization of Markovnikov rule can be better understood in terms of mechanism of the reaction. Mechanism: hydrogen bromide provides an electrophile, H, which attacks the double bond to form carbocation as shown below. I, the secondary carbocation B, is more stable than the primary carbocation A. Therefore, the former predominates because it is formed at a faster rate. 2. The carbocation B is attacked by Br ion to form the product as follows: 2-bromopropane major product, a less stable primary carbocation, B more stable secondary carbocation. 390 Chemistry: anti-Markovnikov addition or peroxide effect or Karash effect in the presence of peroxide. Addition of HBr to unsymmetrical alkenes like propene takes place contrary to the Markovnikov rule. This happens only with HBr but not with HCl and HL. This addition reaction was observed by M.S. Karash and Fr. Mayo in 1933 at the University of Chicago. This reaction is known as peroxide or Karash effect or addition reaction anti to Markovnikov rule. 3232262225 CHCOO CHCHCHHBr CHCHCHBr 1-bromopropane X 13.43 Mechanism: peroxide effect proceeds via free radical chain mechanism as given below. 26566 Homolysis CHHBr. The secondary free radical obtained in the above mechanism step 3 is more stable than the primary. This explains the formation of 1-bromopropane as the major product. It may be noted that the peroxide effect is not observed in addition of HCl and high. This may be due to the fact that the HCl bond being stronger 430.5 kJ-mol-1 than HBr bonds 363.7 kJ-mol-1 is not cleaved by the free radical, whereas the HI bond is weaker 296.8 kJ-mol-1 and iodine free radicals combine to form iodine molecules instead of adding to the double bond. Problem 13.12 Write IUPAC names of the products obtained by addition reactions of HBr to Hex-1-EnEI in the absence of peroxide and 2 inches the presence of peroxide. Solution 4. Addition of sulfuric acid. Cold concentrated sulfuric acid adds to alkenes in accordance with Markovnikov rule to form alkyl hydrogen sulfate by the electrophilic addition reaction. I. 391 Hydrocarbons 13.44-13.455 Addition of water. In the presence of a few drops of concentrated sulfuric acid, alkenes react with water to form alcohols, in accordance with the Markovnikov rule. 13.466 Oxidation. Alkenes on reaction with cold, dilute, aqueous solution of potassium permanganate Bayer's reagent produce vicinal glycols. Decolorization of KMnO4 solution is used as a test for unsaturation. 13.47 13.48b Acidic potassium permanganate or acidic potassium dichromate oxidizes alkenes to ketones and or acids depending upon the nature of the alkene and the experimental conditions. 13.493334 kMNOHCHCHCHCH2CH Cuba2ENE, ethanoic acid. 13.507 Ozonolysis. Ozonolysis of alkenes involves the addition of ozone molecule to alkene to form ozonide, and then cleavage of the ozonide by ZnH2O to smaller molecules. This reaction is highly useful in detecting the position of the double bond in alkenes or other unsaturated compounds. 13.51 13.528 Polymerization. You are familiar with polythene bags and polythene sheets. Polythene is obtained by the combination of large number of ethene molecules at high temperature, high pressure and in the presence of a catalyst. The large molecules thus obtained are called polymers. This reaction is known as polymerization. The simple compounds from which polymers 392 chemistry are made are called monomers. Other alkenes also undergo polymerization. 2222N high temp pressure catalyst NCHCHCHCH polythene. 13.53322N3 high temp pressure catalyst NCHCHCHCHCH polypropene. 13.54 polymers are used for the manufacture of plastic bags, squeeze bottles, refrigerator dishes, toys, pipes, radio and TV cabinets, etc. Polypropene is used for the manufacture of milk crates, plastic buckets and other molded articles. Though these materials have now become common, excessive use of polythene and polypropylene is a matter of great concern for all of us. 13.4 Alkynes. Like alkenes, alkynes are also unsaturated hydrocarbons. They contain at least one triple bond between two carbon atoms. The number of hydrogen atoms is still less in alkynes as compared to alkenes or alkanes. Their general formula is CnH2n2. The first stable member of alkyne series is ethene, which is popularly known as acetylene. Acetylene is used for arc welding purposes in the form of oxyacetylene flame obtained by mixing acetylene with oxygen gas. Alkynes are starting materials for a large number of organic compounds. Hence, it is interesting to study this class of organic compounds. 1.3.4. 1 Nomenclature and isomerism in common system. Alkynes are named as derivatives of acetylene. In IUPAC system, they are named as derivatives of the corresponding alkanes, replacing ane by the suffix in. The position of the triple bond is indicated by the first triply bonded carbon. Common and IUPAC names of a few members of alkyne series are given in table 13.2. You have already learnt that ethene and propyne have got only one structure, but there are two possible structures for butene, but 1 in and 2 but 2 in. Since these two compounds differ in their structures due to the position of the triple bond, they are known as position isomers. In how many ways, you can construct the structure for the next homologue, that is, the next alkyne with molecular formula C5H8. Let us try to arrange 5 carbon atoms with a continuous chain and with a side chain. Following are the possible structures. Structure IUPAC name I223123455HCCCHCHCH pent 1 and 2. 323123455HCCCCHCH pent 2 and 3. 34321HCCHCCH3 methyl but 1 in CH3. Structures I and 2 are position isomers and structures I and 3 are 2 and 3 are chain isomers. Problem 13.13 Write structures of different isomers corresponding to the 5DH member of alkyne series. Also write IUPAC names of all the isomers. What type of isomerism is exhibited by different pairs of isomer solution? 5DH member of alkyne has the molecular formula C6H10. The possible isomers are, table 13.2 common and IUPAC names of alkyne CnH2n2 value of N formula structure common name IUPAC name 2C2H2HCCH acetylene ethene 3C3H4CH3CCH methyl acetylene propyne 4C4H6CH3CH2CCH ethyl acetylene but 1 in 4C4H6CH3CC, CH3 dimethyl acetylene but 2 in 393 hydrocarbons IHCC, CH2CH2CH2CH3 hex 1 NBCH3CC, CH2CH2CH3 hex 2 NCCH3CH2CC, CH2CH3 hex 3 and 3 methylpent 1 in 4 methylpent 1 in 4 methylpent 2 and 3, 3 dimethylpent 1 in position and chain isomerism shown by different pairs. 1.3.4. 2 Structure of triple bond ethene is the simplest molecule of alkyne series. Structure of ethene is shown in Fig. 13.6. Each carbon atom of ethene has 2 sp hybridized orbitals. Carbon-carbon sigma Greek letter sigma bond is obtained by the head-on overlapping of the 2 sp hybridized orbitals of the 2 carbon atoms. The remaining sp hybridized orbital of each carbon atom undergoes overlapping along the internuclear axis with the 1s orbital of each of the 2 hydrogen atoms forming 2 CH sigma bonds. HCC bond angle is of 180 degrees. Each carbon has two unhybridized p orbitals which are perpendicular to each other as well as to the plane of the CC sigma bond. The two p orbitals of one carbon atom are parallel to the two p orbitals of the other carbon atom, which undergo lateral or sideways overlapping to form two pi Greek letter pi bonds between two carbon atoms. Thus ethene molecule consists of one CC Greek letter sigma bond, two CH Greek letter sigma bonds and two CC Greek letter pi bonds. The strength of CC bond enthalpy 823 kJ mol 1 is more than those of CC bond enthalpy 681 kJ mol -1 and CC bond enthalpy 348 kJ mol -1. The CC bond length is shorter 120 pm than those of CC 133 pm and CC 154 pm. Electron cloud between two carbon atoms is cylindrically symmetrical about the internuclear axis. Thus, ethene is a linear molecule 1,3,4,3 preparation 1, from calcium carbide. On industrial scale, ethene is prepared by treating calcium carbide with water. Calcium carbide is prepared by heating quicklime with coke. Quicklime can be obtained by heating limestone as shown in the following reactions. 3,2-CaCaOCO 13.55 Fig. 13.6 orbital picture of ethene showing a sigma overlaps b pi overlaps. 394 Chemistry 2-CaO3-CaCaCO 13.56 Calcium carbide 2,2,2,2-CaC2HOCOCH 13.572. From vicinal dihalides. Vicinal dihalides on treatment with alcoholic potassium hydroxide undergo dehydrohalogenation. One molecule of hydrogen halide is eliminated to form alkenyl halide which on treatment with sodomite gives alkyne. 1,3,4. 4 properties. Physical properties of alkynes follow the same trend of alkenes and alkanes. First 3 members are gases, the next 8 are liquids and the higher ones are solids. All alkynes are colorless. Ethylene has characteristic odor, other members are odorless. Alkynes are weakly polar in nature. They are lighter than water and immiscible with water but soluble in organic solvents like ethers, carbon tetrachloride and benzene. Their melting point, boiling point and density increase with increase in molar mass. Chemical properties. Alkynes show acidic nature. Addition reactions and polymerization reactions as follows. A. Acidic character of alkyne. Sodium metal and sodomide Nan2 are strong bases. They react with ethene to form sodium acetylide with the liberation of dihydrogen gas. These reactions have not been observed in case of ethene and ethane, thus indicating that ethene is acidic in nature in comparison to ethene and ethane. Why is it so? Has it something to do with their structures and the hybridization? You have read that hydrogen atoms in ethene are attached to the sp hybridized carbon atoms whereas they are attached to sp2 hybridized carbon atoms in ethene and sp3 hybridized carbons in ethane. Due to the maximum percentage of S character 50, the sp hybridized orbitals of carbon atoms in ethene molecules have highest electronegativity, hence, these attract the shared electron pair of the CH bond of ethene to a greater extent than that of the sp2 hybridized orbitals of carbon in ethene and the sp3 hybridized orbital of carbon in ethane. Thus in ethene, hydrogen atoms can be liberated as protons more easily as compared to ethene and ethane. Hence, hydrogen atoms of ethene attached to triply bonded carbon atom are acidic in nature. You may note that the hydrogen atoms attached to the triply bonded carbons are acidic but not all the hydrogen atoms of alkynes. 2-HCCH NaHCC no monosodium ethanide 13.59, 2-HCC non-CC no disodium ethanide 13.603233CH, CCH na NHCH, CC na NH sodium propanide 13.61. These reactions are not shown by alkenes and alkanes, hence used for distinction between alkynes, alkenes and alkanes. What about the above reactions with but1-in and but2-in alkanes? Alkenes and alkynes follow the following trend in their acidic behavior. I2233HCCH, HCCH, CH2333HCCH, B. Addition reactions. Alkynes contain a triple bond, so they add up 2 molecules of dihydrogen, halogen, hydrogen halides etc. 395 Hydrocarbons. Formation of the addition product takes place according to the following steps. The addition product formed depends upon stability of vinylic cation. Addition in unsymmetrical alkynes takes place according to Markovnikov rule. Majority of the reactions of alkynes are the examples of electrophilic addition reactions. A few addition reactions are given below. I addition of dihydrogen 2,2,2,2,3,3 HPTPD NichCHHCCHCHCH 13.6232322323 PTPD NichCCHHCHCHCH propine propane HCHCHCH propane 13.632 Addition of halogens 13.64 Edish. Orange color of the solution of bromine in carbon tetrachloride is decolorized. This is used as a test for unsaturation 3 addition of hydrogen halides to molecules of hydrogen halides HCl. HBr, hyadd two alkynes to form gemmed halides in which 2 halogens are attached to the same carbon atom 2,2,3-HCCH-HBr-CHBr-CHBr bromothane CH1. 1-dibromothane 13.65-13.66 IV addition of water like alkanes and alkenes. Alkynes are also immiscible and do not react with water. However, 1 molecule of water adds 2 alkynes on warming with mercuric sulfate and dilute sulfuric acid at 333 K to form carbonyl compounds. 13.67-13.6 AV polymerization. A linear polymerization, under suitable conditions. Linear polymerization of ethene takes place to produce polyacetylene or polyethylene, which is a high molecular weight polyene containing repeating units of CHCH. CHCHN can be represented as CHCH, CHCHN under special conditions. This polymer conducts electricity. 396 Chemistry. Thin film of polyacetylene can be used as electrodes in batteries. These films are good conductors, lighter and cheaper than the metal conductors. Bicyclic polymerization. Ethene on passing through red-hot iron tube at 873 K undergoes cyclic polymerization. 3 molecules polymerize to form benzene, which is the starting molecule for the preparation of derivatives of benzene, dyes, drugs and large number of other organic compounds. This is the best route for entering from aliphatic to aromatic compounds as discussed below. 13.69 Problem 13.14 How will you convert ethanoic acid into benzene? Solution 13.5 Aromatic hydrocarbon. These hydrocarbons are also known as arenes, since most of them possess pleasant odor. Greek, aroma meaning pleasant smelling. The class of compounds was named as aromatic compounds. Most of such compounds were found to contain benzene ring. Benzene ring is highly unsaturated, but in a majority of reactions of aromatic compounds, the unsaturation of benzene ring is retained. However, there are examples of aromatic hydrocarbons which do not contain a benzene ring but instead contain other highly unsaturated ring. Aromatic compounds containing benzene ring are known as benzenoids, and those not containing a benzene ring are known as non-benzenoids. Some examples of arenes are given below: benzene, toluene, naphthalene, biphenyl 1,3,5. 1 Nomenclature and isomerism. The nomenclature and isomerism of aromatic hydrocarbons has already been discussed in Unit 12. All 6 hydrogen atoms in benzene are equivalent, so it forms one and only one type of monosubstituted product. When 2 hydrogen atoms in benzene are replaced by 2 similar or different monovalent atoms or groups, 3 different position isomers are possible. The 1, 2 or 1, 6 is known as the ortho-O, the 1, 3 or 1, 5 is meta-M, and the 1, 4 is pod-P substituted compounds. A few examples of derivatives of benzene are given below: methylbenzene 1, 2-dimethylbenzene toluene 1, 3-dimethylbenzene 1, 4-dimethylbenzene xylene p-xylene 1,3,5. 2 Structure of benzene. Benzene was isolated by Michael Faraday in 1825. The molecular formula of benzene, C6H6, indicates a high degree of unsaturation. This molecular formula did not account for its relationship to corresponding alkanes, alkenes and alkynes, which you have studied in earlier sections of this unit. What do you think about its possible structure? Due to its unique properties and unusual stability, it took several years to assign its structure. Benzene was found to be a stable molecule and found to form a triazonide, which indicates the presence of 3 double bonds. Benzene was further found to produce one and only one monosubstituted derivative, which indicated that all the 6 carbon and 6 hydrogen atoms of benzene are identical. On the basis of this observation, Auguste Kekulé in 1865 proposed the following structure for benzene, having cyclic arrangement of 6 carbon atoms with alternate single and double bonds and 1 hydrogen atom attached to each carbon atom. The Kekulé structure indicates the possibility of 2 isomeric 1,2-dibromobenzenes. In one of the isomers, the bromine atoms are attached to the doubly bonded carbon atoms, whereas in the other, they are attached to the singly bonded carbons. Friedrich August Kekulé, a German chemist, was born in 1829 at Darmstadt, Germany. He became professor in 1856 and Fellow of Royal Society in 1875. He made major contribution to structural organic chemistry by proposing in 1858 that carbon atoms can join to one another to form chains, and later in 1865. He found an answer to the challenging problem of benzene structure by suggesting that these chains can cross to form rings. He gave the dynamic structural formula to benzene, which forms the basis for its modern electronic structure. He described the discovery of benzene structure later as, "I was sitting writing at my textbook, but the work did not progress, my thoughts were elsewhere. I turned my chair to the fire, and dozed. Again the atoms were gamboling before my eyes, this time the smaller groups kept modestly in the background. My mental eye, rendered more acute by repeated visions of this kind, could now distinguish larger structures of manifold conformations, long rows, sometimes more closely fitted together, all twisting and turning in snake-like motion. But look, What was that? One of the snakes had seized hold of its own tail, and the form whirled mockingly before my eyes. As if by a flash of lightning I woke. I spent the rest of the night working out the consequences of the hypothesis. Let us learn to dream, gentlemen, and then perhaps we shall learn the truth, but let us beware of making our dreams public before they have been approved by the waking mind. 1890. 100 years later, on the occasion of Kekule's centenary celebrations, a group of compounds having polybenzenoid structures have been named as keculenes. Friedrich August Kekule, September 7, 1829, 13th July 1896. 398 Chemistry. However, benzene was found to form only one orthodesubstituted product. This problem was overcome by Kekule by suggesting the concept of oscillating nature of double bonds in benzene as given below. Even with this modification, Kekule's structure of benzene fails to explain unusual stability and preference to substitution reactions than addition reactions, which could later on be explained by resonance. Resonance unstability of benzene. According to valence bond theory, the concept of oscillating double bonds in benzene is now explained by resonance. Benzene is a hybrid of various resonating structures. The two structures, A and B given by Kekule, are the main contributing structures. The hybrid structure is represented by inserting a circle or a dotted circle in the hexagon as shown in C. The circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene ring. A BC. The orbital overlapping gives us better picture about the structure of benzene. All the 6 carbon atoms in benzene are sp2 hybridized. 2 sp2 hybrid orbitals of each carbon atom overlap with sp2 hybrid orbitals of adjacent carbon atoms to form 6 cc sigma bonds which are in the hexagonal plane. The remaining sp2 hybrid orbital of each carbon atom overlaps with s orbital of a hydrogen atom to form 6 ch sigma bonds. Each carbon atom is now left with one unhybridized p orbital perpendicular to the plane of the ring as shown below. The unhybridized p orbital of carbon atoms are close enough to form a Greek letter pi bond bilateral overlap. There are 2 equal possibilities of forming 3 Greek letter pi bonds by overlap with p orbitals of C1 C2, C3 C4, C5 C6 or C2 C3, C4 C5, C6 C1 respectively as shown in the following figures. Figure 13.7 A. Figure 13.7b. Structures shown in Figure 13.7 A and B correspond to 2 Kekule structure with localized Greek letter pi bonds. The internuclear distance 399 hydrocarbons between all the carbon atoms in the ring has been determined by the X-ray diffraction to be the same. There is equal probability for the p orbital of each carbon atom to overlap with the p orbitals of adjacent carbon atoms. Fig. 13.7c. This can be represented in the form of 2 dotnet rings of electron clouds. Fig. 13.7d, one above and one below the plane of the hexagonal ring as shown below. Figure 13.7c. Fig. 13.7d. The 6 Greek letter pi electrons are thus delocalized and can move freely about the 6 carbon nuclei, instead of any 2 as shown in Fig. 13.6 A or B. The delocalized Greek letter pi electron cloud is attracted more strongly by the nuclei of the carbon atoms than the electron cloud localized between 2 carbon atoms. Therefore, presence of delocalized Greek letter pi electrons in benzene makes it more stable than the hypothetical cyclohexatrine. X-ray diffraction data reveals that benzene is a planar molecule. Had any one of the above structures of benzene A or B been correct, 2 types of CC bond lengths were expected. However, X-ray data indicates that all the 6 CC bond lengths are of the same order 139 pm, which is intermediate between CC single bond 154 pm and CC double bond 133 pm. Thus the absence of pure double bond in benzene accounts for the reluctance of benzene to show addition reactions under normal conditions, thus explaining the unusual behavior of benzene. 1.3.5. 3. Aromaticity. Benzene was considered as parent aromatic compound. Now, the name is applied to all the ring systems whether or not having benzene ring, possessing following characteristics. I-planarity. 2. Complete delocalization of the Greek letter pi electrons in the ring. 3. Presence of 4 and 2 Greek letter pi electrons in the ring where n is an integer n 0, 1, 2. This is often referred to as Huckel rule. Some examples of aromatic compounds are given below. 1.3.5. For preparation of benzene. Benzene is commercially isolated from coal tar. However, it may be prepared in the laboratory by the following methods: acyclic polymerization of ethene, section 1.3.4. 4.2. Decarboxylation of aromatic acids. Sodium salt of benzoic acid on heating with salt lime gives benzene. 13.70. Electron cloud. 400. Chemistry. 3. Reduction of phenol. Phenol is reduced to benzene by passing its vapors over heated zinc dust. 13.7113.5. 5 properties. Physical properties. Aromatic hydrocarbons are nonpolar molecules and are usually colorless liquids or solids with a characteristic aroma. You are also familiar with naphthalene balls, which are used in toilets and for preservation of clothes because of unique smell of the compound and the moth repellent property. Aromatic hydrocarbons are immiscible with water but are readily miscible with organic solvents. They burn with sooty flame. Chemical properties. Arenes are characterized by electrophilic substitution reactions. However, under special conditions they can also undergo addition and oxidation reactions. Electrophilic substitution reactions. The common electrophilic substitution reactions of arenes are nitration, halogenation, sulfonation, Friedel-Crafts alkylation and acylation reactions in which attacking reagent is an electrophile EI nitration. A nitro group is introduced into benzene ring when benzene is heated with a mixture of concentrated nitric acid and concentrated sulfuric acid nitrating mixture. 13.72 Nitrobenzene 2 halogenation. Arenes react with halogens in the presence of a Lewis acid like anhydrous FeCl3, FeBr3 or AlCl3 to yield halorenes. Chlorobenzene 13.733 sulfonation. The replacement of a hydrogen atom by a sulfonic acid group in a ring is called sulfonation. It is carried out by heating benzene with fuming sulfuric acid oleum. 13.74 Friedel-Crafts alkylation reaction. When benzene is treated with an alkyl halide in the presence of anhydrous aluminium chloride, alkylbenene is formed. 13.75 13.76 Why do we get isopropyl benzene on treating benzene with 1-chloropropane instead of N-propyl benzene? The Friedel-Crafts acylation reaction. The reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acids AlCl3 yields isobenzene. 401 Hydrocarbons 13.77 13.78 If excessive electrophilic reagent is used, further substitution reaction may take place in which other hydrogen atoms of benzene ring may also be successively replaced by the electrophile. For example, benzene on treatment with excessive chlorine in the presence of anhydrous AlCl3 can be chlorinated to hexachlorobenzene C6Cl6 13.79 Mechanism of electrophilic substitution reactions. According to experimental evidences, SES substitution, electrophilic reactions are supposed to proceed via the following three steps: a generation of the electrophile, B formation of carbocation intermediate, C removal of proton from the carbocation intermediate, a generation of electrophile E. During chlorination, alkylation and acylation of benzene, anhydrous AlCl3, being a Lewis acid, helps in generation of the electrophile Cl, R, RCO acylium ion respectively by combining with the attacking reagent. In the case of nitration, the electrophile, nitronium ion 2NO is produced by transfer of a proton from sulfuric acid to nitric acid in the following manner. Step by step 2 protonated nitronium nitric acid ion. It is interesting to note that in the process of generation of nitronium ion, sulfuric acid serves as an acid and nitric acid as a base. Thus, it is a simple acid-base equilibrium. B formation of carbocation uranium ion. Attack of electrophile results in the formation of Greek letter sigma complex or uranium ion in which one of the carbon is sp3 hybridized. Sigma complex uranium ion. The uranium ion gets stabilized by resonance. 402 Chemistry. Sigma complex or uranium ion loses its aromatic character because delocalization of electrons stops at sp3 hybridized carbon. C removal of proton. To restore the aromatic character, Greek letter sigma complex releases proton from sp3 hybridized carbon on attack by AlCl4 in case of halogenation, alkylation and acylation, and HSO4 in case of nitration. Addition reactions under vigorous conditions, that is, at high temperature and or pressure in the presence of nickel catalyst. Hydrogenation of benzene gives cyclohexane. Cyclohexane 13.80 under ultraviolet light. 3 chlorine molecules add to benzene to produce benzene hexachloride, C6H6Cl6, which is also called gamoxane. Benzene hexachloride, BHC 13.81 combustion, when heated in air. Benzene burns with sooty flame producing CO2 and H2O6622215CHO6CO3HO2 13.82 General combustion reaction for any hydrocarbon may be given by the following chemical equation: CX high X4YO2XCO2 2YH2O 13.8313. 5. 6. Directive influence of a functional group in monosubstituted benzene when monosubstituted benzene is subjected to further substitution. 3. Possible disubstituted products are not formed in equal amounts. 2 types of behavior are observed. Either ortho and pada products or metaproduct is predominantly formed. It has also been observed that this behavior depends on the nature of the substituent already present in the benzene ring and not on the nature of the entering group. This is known as directive influence of substituents. Reasons for ortho-pada or meta-directive nature of groups are discussed below. Ortho and pada directing groups. The groups which direct the incoming group to ortho and pada positions are called ortho and pada directing groups. As an example, let us discuss the directive influence of phenolic O group. Phenol is resonance hybrid of following structures. It is clear from the above resonating structures that the electron density is more on O and P positions. Hence, the substitution takes place mainly at these positions. However, it may be noted that I effect of O group also operates, due to which the electron density on ortho and pod positions of the benzene ring is slightly reduced. But the overall electron density increases at these positions of the ring due to resonance. Therefore, O group activates the benzene ring for the attack by 403 hydrocarbons and electrophile. Other examples of activating groups are NH2, NHR, NHCOCH3, OC3, CH3, C2H5, etc. In the case of aryl halides, halogens are moderately deactivating. Because of their strong I effect, overall electron density on benzene ring decreases. It makes further substitution difficult. However, due to resonance, the electron density on O and P positions is greater than that at the N position. Hence, they are also O and P directing groups. Resonance structures of chlorobenzene are given below. In this case, the overall electron density on benzene ring decreases, making further substitution difficult. Therefore, these groups are also called deactivating groups. The electron density on O and P position is comparatively less than that at meta position. Hence, the electrophile attacks on comparatively electron-rich meta position, resulting in meta substitution. 13.6 Carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons containing more than 2 benzene rings fused together are toxic and said to possess cancer-producing carcinogenic property. Such polynuclear hydrocarbons are formed on incomplete combustion of organic materials like tobacco, coal and petroleum. They enter into human body and undergo various biochemical reactions and finally damage DNA and cause cancer. Some of the carcinogenic hydrocarbons are given below. See box. Meta-directing group. The groups which direct the incoming group to meta position are called meta-directing groups. Some examples of meta-directing groups are number 2, CN, CHOCOR, CO, COR, SO, 3H, etc. Let us take the example of nitro group. Nitro group reduces the electron density in the benzene ring due to its strong I effect. Nitrobenzene is the resonance hybrid of the following structures. 2018-1. 404 Chemistry summary. Hydrocarbons are the compounds of carbon and hydrogen only. Hydrocarbons are mainly obtained from coal and petroleum, which are the major sources of energy. Petrochemicals are the prominent starting materials used for the manufacture of a large number of commercially important products. LPG, liquefied petroleum gas, and CNG, compressed natural gas, the main sources of energy for domestic fuels and the automobile industry, are obtained from petroleum. Hydrocarbons are classified as open-chain saturated alkanes and unsaturated alkenes and alkynes, cyclic, alicyclic, and aromatic, according to their structure. The important reactions of alkanes are free radical substitution, combustion, oxidation, and aromatization. Alkenes and alkynes undergo addition reactions, which are mainly electrophilic additions. Aromatic hydrocarbons, despite having unsaturation, undergo mainly electrophilic substitution reactions. These undergo addition reactions only under special conditions. Alkanes show conformational isomerism due to free rotation along the C-C sigma bonds. Out of staggered and the eclipsed conformations of ethane, staggered conformation is more stable as hydrogen atoms are farthest apart. Alkenes exhibit geometrical cis-trans isomerism due to restricted rotation around the carbon-carbon double bond. Benzene and benzenoid compounds show aromatic character. Aromaticity, the property of being aromatic, is possessed by compounds having specific electronic structure characterized by Huckel 4 and 2 Greek letter pi electron rule. The nature of groups or substituents attached to benzene ring is responsible for activation or deactivation of the benzene ring towards further electrophilic substitution and also for orientation of the incoming group. Some of the polynuclear hydrocarbons having fused benzene ring system have carcinogenic property. Exercises 13.1 How do you account for the formation of ethane during chlorination of methane? 13.2 Write IUPAC names of the following compounds: a CH3CHCCH3 2BCH2CHCCCH3CDCH2, CH2CHCH2E3242332CFCHCHCHCHCHCHCHCHCH, CH2CHCH, CH, CH2CHCH2C2H5. 13.3 For the following compounds, write structural formulas and IUPAC names for all possible isomers having the number of double or triple bond as indicated. A C4H81 double bond, BC5H81 triple bond. 13.4 Write IUPAC names of the products obtained by the ozonolysis of the following compounds: ipen2-ene2,3, 4-dimethylhep3-ene3,2-ethylbut-1-ene-1-phenylbut-1-ene. 405 Hydrocarbons. 13.5 An alkene on ozonolysis gives a mixture of ethanol and pentan 3,1. Write structure and IUPAC name of A. 13.6 An alkene A contains 3 C, 8 C, H Greek letter sigma bonds and 1 C, Greek letter pi bond. Ionosinolysis gives 2 moles of an aldehyde of molar mass 44 U. Write IUPAC name of A. 13.7 Propanol and pentan 3,1 are the ozonolysis products of an alkene. What is the structural formula of the alkene? 13.8 Write chemical equations for combustion reaction of the following hydrocarbons: ibutane 2-pentene 3-hexynivetoluene. 13.9 Draw the cis and trans structures of hex 2-ene. Which isomer will have higher BP and Y? 13.10 Why is benzene extraordinarily stable though it contains 3 double bonds? 13.11 What are the necessary conditions for any system to be aromatic? 13.12 Explain why the following systems are not aromatic. I23 13.13 How will you convert benzene into IP-nitrobromobenzene 2 meters nitrochlorobenzene 3p nitrotoluene ivacetophenone? 13.14 In the alkane H3C, CH2C CH32 CH2CH CH32, identify x 31 degree, 2 degrees, 3 degrees carbon atoms and give the number of H atoms bonded to each one of these. 13.15 What effect does branching of an alkane chain has on its boiling point? 13.16 Addition of HBr to propene yields 2-bromopropane. While in the presence of benzoyl peroxide, the same reaction yields 1-bromopropane. Explain and give mechanism. 13.17 Write down the products of ozonolysis of 1,2-dimethylbenzeneoxylene. How does the result support Kekulé structure for benzene? 13.18 Arrange benzene, N-hexane and ethene in decreasing order of acidic behavior. Also give reason for this behavior. 13.19 Why does benzene undergo electrophilic substitution reactions easily and nucleophilic substitutions with difficulty? 13.20 How would you convert the following compounds into benzene I-ethene 2-ethene 3-hexane? 13.21 Write structures of all the alkenes which on hydrogenation give 2-methylbutane. 13.22 Arrange the following set of compounds in order of their decreasing relative reactivity with an electrophile. E-chlorobenzene, 2,4-dinitrochlorobenzene, p-nitrochlorobenzene B-toluene, page H3C, C6H4 number 2, page O2N, C6H4 number 2. 13.23 Out of benzene, and dinitrobenzene and toluene which will undergo nitration most easily and why? 13.24 Suggest the name of a Lewis acid other than anhydrous aluminium chloride which can be used during ethylation of benzene. 13.25 Why is Wirt's reaction not preferred for the preparation of alkanes containing odd number of carbon atoms? Illustrate your answer by taking one example. Unit 14 Environmental Chemistry. After studying this unit, you will be able to understand the meaning of environmental chemistry, define atmospheric pollution, list reasons for global warming, greenhouse effect and acid rain, identify causes for ozone layer depletion and its effects, give reasons for water pollution and know about international standards for drinking water, describe causes of soil pollution, suggest and adopt strategies for control of environmental pollution, appreciate the importance of green chemistry in day-to-day life. You have already studied about environment in your earlier classes. Environmental studies deal with the sum of all social, economical, biological, physical and chemical interrelations with our surroundings. In this unit the focus will be on environmental chemistry. Environmental chemistry deals with the study of the origin, transport, reactions, effects and fates of chemical species in the environment. Let us discuss some important aspects of environmental chemistry. 14.1 Environmental pollution. Environmental pollution is the effect of undesirable changes in our surroundings that have harmful effects on plants, animals and human beings. A substance, which causes pollution, is known as pollutant. Pollutants can be solid, liquid or gaseous substances present in greater concentration than in natural abundance and are produced due to human activities or due to natural happenings. Do you know, an average human being requires nearly 12-15 times more air than the food, so, even small amounts of pollutants in the air become significant compared to similar levels present in the food. Pollutants can be degradable, like discarded vegetables which rapidly break down by natural processes. On the other hand, pollutants which are slowly degradable, remain in the environment in an unchanged form for many decades. For example, substances such as dichlorodephényltrichloroethane DDT, plastic materials, heavy metals, many chemicals, nuclear wastes etc., once released into the environment are difficult to remove. The world has achieved brilliance without wisdom, power without conscience. Ours is a world of nuclear giants and ethical infants. Environmental chemistry. 407 Pollutants cannot be degraded by natural processes and are harmful to living organisms. In the process of environmental pollution, pollutants originate from a source and get transported by air or water or are dumped into the soil by human beings. 14.2 Atmospheric pollution. The atmosphere that surrounds the Earth is not of the same thickness at all heights. There are concentric layers of air or regions, and each layer has different density. The lowest region of atmosphere in which the human beings along with other organisms live is called troposphere. It extends up to the height of 10 kilometers from sea level. Above the troposphere, between 10 and 50 kilometers above sea level, lies stratosphere. Troposphere is a turbulent, dusty zone containing air, much water vapor and clouds. This is the region of strong air movement and cloud formation. The stratosphere, on the other hand, contains dinitrogen, dioxygen, ozone and little water vapor. Atmospheric pollution is generally studied as tropospheric and stratospheric pollution. The presence of ozone in the stratosphere prevents about 99.5% of the sun's harmful ultraviolet UV radiations from reaching the Earth's surface and thereby protecting humans and other animals from its effect. 1 Tropospheric pollution. Tropospheric pollution occurs due to the presence of undesirable solid or gaseous particles in the air. The following are the major gaseous and particulate pollutants present in the troposphere. 1. Gaseous air pollutants. These are oxides of sulfur, nitrogen and carbon, hydrogen sulfide, hydrocarbons, ozone and other oxidants. 2. Particulate pollutants. These are dust, mist, fumes, smoke, smog etc. 1. Gaseous air pollutants are oxides of sulfur. Oxides of sulfur are produced when sulfur-containing fossil fuel is burned. The most common species, sulfur dioxide, is a gas that is poisonous to both animals and plants. It has been reported that even a low concentration of sulfur dioxide causes respiratory diseases, e.g., asthma, bronchitis, emphysema in human beings. Sulfur dioxide causes irritation to the eyes, resulting in tears and redness. High concentration of SO2 leads to stiffness of flower buds, which eventually fall off from plants. Uncatalyzed oxidation of sulfur dioxide is slow. However, the presence of particulate matter in polluted air catalyzes the oxidation of sulfur dioxide to sulfur trioxide. 2 SO2GO2G 2 SO3G. The reaction can also be promoted by ozone and hydrogen peroxide. SO2GO3G SO3GO2G SO2GH2O2LH2 SO4ACB. Oxides of nitrogen, dinitrogen and dioxygen are the main constituents of air. These gases do not react with each other at a normal temperature. At high altitudes, when lightning strikes, they combine to form oxides of nitrogen. Number 2 is oxidized to nitrate ion. 3 No, which is washed into soil, where it serves as a fertilizer, in an automobile engine. At high temperature, when fossil fuel is burned, dinitrogen and dioxygen combine to yield significant quantities of nitric oxide NO and nitrogen dioxide. Number 2 is given below. N2GO2G 1483 K2 NO G NO reacts instantly with oxygen to give number 2 NO GO2G 2 Number 2 G. Rate of production of number 2 is faster when nitric oxide reacts with ozone in the stratosphere. No GO3G. Number 2 GO2G. The irritant red haze in the traffic and congested places is due to oxides of nitrogen. Higher concentrations of number 2 damage the leaves of plants and retard the rate of photosynthesis. Nitrogen dioxide is a lung irritant that can lead to an acute respiratory disease in children. It is toxic to living tissues also. Nitrogen dioxide is also harmful to various textile fibers and metals. Chemistry 408C. Hydrocarbons. Hydrocarbons are composed of hydrogen and carbon only and are formed by incomplete combustion of fuel used in automobiles. Hydrocarbons are carcinogenic, that is, they cause cancer. They harm plants by causing aging, breakdown of tissues and shedding of leaves, flowers and twigs. Dioxides of carbon I. Carbon monoxide. Carbon monoxide CO is one of the most serious air pollutants. It is a colorless and odorless gas, highly poisonous to living beings because of its ability to block the delivery of oxygen to the organs and tissues. It is produced as a result of incomplete combustion of carbon. Carbon monoxide is mainly released into the air by automobile exhaust. Other sources, which produce CO, involve incomplete combustion of coal, firewood, petrol, etc. The number of vehicles has been increasing over the years all over the world. Many vehicles are poorly maintained and several have inadequate pollution control equipments, resulting in the release of greater amount of carbon monoxide and other polluting gases. Do you know why carbon monoxide is poisonous? It binds to hemoglobin to form carboxyhemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. In blood, when the concentration of carboxyhemoglobin reaches about 3-4%, the oxygen carrying capacity of blood is greatly reduced. This oxygen deficiency results into headache, weak eyesight, nervousness and cardiovascular disorder. This is the reason why people are advised not to smoke. In pregnant women who have the habit of smoking, the increased CO level in blood may induce premature birth, spontaneous abortions and deformed babies. 2. Carbon dioxide. Carbon dioxide CO2 is released into the atmosphere by respiration, burning of fossil fuels for energy, and by decomposition of limestone during the manufacture of cement. It is also emitted during volcanic eruptions. Carbon dioxide gas is confined to troposphere only. Normally it forms about 0.03% by volume of the atmosphere. With the increased use of fossil fuels, a large amount of carbon dioxide gets released into the atmosphere. Excessive CO2 in the air is removed by green plants, and this maintains an appropriate level of CO2 in the atmosphere. Green plants require CO2 for photosynthesis, and they, in turn, emit oxygen, thus maintaining the delicate balance. As you know, deforestation and burning of fossil fuel increases the CO2 level and disturb the balance in the atmosphere. The increased amount of CO2 in the air is mainly responsible for global warming. Global warming and greenhouse effect. About 75% of the solar energy reaching the Earth is absorbed by the Earth's surface, which increases its temperature. The rest of the heat radiates back to the atmosphere. Some of the heat is trapped by gases such as carbon dioxide, methane, ozone, chlorofluorocarbon compounds CFCs, and water vapor in the atmosphere. Thus, they add to the heating of the atmosphere. This causes global warming. We all know that in cold places flowers, vegetables and fruits are grown in glass-covered areas called greenhouse. Do you know that we humans also live in a greenhouse? Of course, we are not surrounded by glass but a blanket of air called the atmosphere, which has kept the temperature on Earth constant for centuries. But it is now undergoing change, though slowly. Just as the glass in a greenhouse holds the sun's warmth inside, atmosphere traps the sun's heat near the Earth's surface and keeps it warm. This is called natural greenhouse effect because it maintains the temperature and makes the Earth perfect for life. In a greenhouse, solar radiations pass through the transparent glass and heat up the soil and the plants. The warm soil and plants emit infrared radiations. Since glass is opaque to infrared radiation's thermal region, it partly reflects and partly absorbs these radiations. This mechanism keeps the energy of the sun trapped in the greenhouse. Similarly, carbon dioxide molecules also trap heat as they are transparent to sunlight but not to the heat radiation. If the amount of environmental chemistry 409 carbon dioxide crosses the delicate proportion of 0.03%, the natural greenhouse balance may get disturbed. Carbon dioxide is the major contributor to global warming. Besides carbon dioxide, other greenhouse gases are methane, water vapor, nitrous oxide, CFCs, and ozone. Methane is produced naturally when vegetation is burnt, digested, or rotted in the absence of oxygen. Large amounts of methane are released in paddy fields, coal mines, from rotting garbage dumps, and by fossil fuels. Chlorofluorocarbons CFCs are man-made industrial chemicals used in air conditioning, etc. CFCs are also damaging the ozone layer. Section 1.4.2.2. Nitrous oxide occurs naturally in the environment. In recent years, their quantities have increased significantly due to the use of chemical fertilizers and the burning of fossil fuels. If these trends continue, the average global temperature will increase to a level which may lead to melting of polar ice caps and flooding of low-lying areas all over the Earth. Increase in the global temperature increases the incidence of infectious diseases like dengue, malaria, yellow fever, sleeping sickness, etc. Acid rain. We are aware that normally rainwater has a pH of 5.6 due to the presence of H ions formed by the reaction of rainwater with carbon Fig. 14.1 Acid deposition. Think it over. What can we do to reduce the rate of global warming if burning of fossil fuels? Cutting down forests and trees add to greenhouse gases in the atmosphere. We must find ways to use these just efficiently and judiciously. One of the simple things which we can do to reduce global warming is to minimize the use of automobiles. Depending upon the situation, one can use bicycle, public transport system, or go for carpool. We should plant more trees to increase the green cover. Avoid burning of dry leaves, wood, etc. It is illegal to smoke in public places and workplaces, because it is harmful not only for the one who is smoking but also for others, and therefore, we should avoid it. Many people do not understand the greenhouse effect and the global warming. We can help them by sharing the information that we have. Chemistry. 410 dioxide present in the atmosphere. H2OL CO2 GH2CO3 AC H2CO3 AC H AC HCO3 AC. When the pH of the rainwater drops below 5.6, it is called acid rain. Acid rain refers to the ways in which acid from the atmosphere is deposited on the Earth's surface. Oxides of nitrogen and sulfur, which are acidic in nature, can be blown by wind along with solid particles in the atmosphere and finally settle down either on the ground as dry deposition or in water, fog and snow as wet deposition. Figure 14.1. Acid rain is a byproduct of a variety of human activities that emit the oxides of sulfur and nitrogen in the atmosphere. As mentioned earlier, burning of fossil fuels which contain sulfur and nitrogenous matter such as coal and oil in power stations and furnaces, or petrol and diesel in motor engines, produce sulfur dioxide and nitrogen oxides. So too and number 2, after oxidation and reaction with water are major contributors to acid rain, because polluted air usually contains particulate matter that catalyze the oxidation. 2SO2GO2G2H2OL2H2SO4Ac4 number 2GO2G2H2OL4HNO3 Ac. Ammonium salts are also formed and can be seen as an atmospheric haze aerosol of fine particles. Aerosol particles of oxides or ammonium salts in raindrops result in wet deposition. SO2 is also absorbed directly on both solid and liquid ground surfaces and is thus deposited as dry deposition. Acid rain is harmful for agriculture, trees and plants as it dissolves and washes away nutrients needed for their growth. It causes respiratory ailments in human beings and animals, when acid rain falls and flows as groundwater to reach rivers, lakes etc. It affects plants and animal life in aquatic ecosystem. It corrodes water pipes resulting in the leaching of heavy metals such as iron, lead and copper into the drinking water. Acid rain damages buildings and other structures made of stone or metal. The Taj Mahal in India has been affected by acid rain. Activity 1. You can collect samples of water from nearby places and record their pH values. Discuss your results in the class. Let us discuss how we can help to reduce the formation of acid rain. This can be done by reducing the emission of sulfur dioxide and nitrogen dioxide in the atmosphere. We should use less vehicles driven by fossil fuels, use less sulfur content fossil fuels for power plants and industries. We should use natural gas, which is a better fuel than coal, or use coal with less sulfur content. Catalytic converters must be used in cars to reduce the effect of exhaust fumes on the atmosphere. The main component of the converter is a ceramic honeycomb coated with precious metals PD, PT and RH. The exhaust gases containing unburned fuel, CO and NOx, when passed through the converter at 573 K, are converted into CO2 and N2. We can also reduce the acidity of the soil by adding powdered limestone to neutralize the acidity of the soil. Many people do not know of acid rain and its harmful effects. We can make them aware by passing on this information and save the nature. Taj Mahal and acid rain. The air around the city of Agra, where the Taj Mahal is located, contains fairly high levels of sulfur and nitrogen oxides. It is mainly due to a large number of industries and power plants around the area. Use of poor quality of coal, kerosene and firewood as fuel for domestic purposes add up to this problem. The resulting acid rain reacts with marble, CaCO3 of Taj Mahal, CaCO3H2SO4 CaSO4H2O CO2, causing damage to this wonderful monument that has attracted people from around the world. As a result, the monument is being slowly disfigured and the marble is getting discolored and lusterless. The government of India announced an action plan in early 1995 to prevent the disfiguring of this historical monument. Madurai Refinery has already taken suitable measures to check the emission of toxic gases. Environmental Chemistry 411-2, Particulate Pollutants. Pollutants are the minute solid particles or liquid droplets in air. These are present in vehicle emissions, smoke particles from fires, dust particles and ash from industries. Particulates in the atmosphere may be viable or non-viable. The viable particulates, e.g., bacteria, fungi, molds, algae etc., are minute living organisms that are dispersed in the atmosphere. Human beings are allergic to some of the fungi found in air. They can also cause plant diseases. Non-viable particulates may be classified according to their nature and size as follows. A smoke particulates consist of solid or mixture of solid and liquid particles formed during combustion of organic matter. Examples are cigarette smoke, smoke from burning of fossil fuel, garbage and dry leaves, oil smoke etc. B. Dust is composed of fine solid particles over 1 micron in diameter, produced during crushing, grinding and attribution of solid materials. Sand from sandblasting, sawdust from woodworks, pulverized coal, cement and fly ash from factories, dust storms etc., are some typical examples of this type of particulate emission. Sea mists are produced by particles of spray liquids and by condensation of vapors in air. Examples are sulfuric acid mist and herbicides and insecticides that miss their targets and travel through air and form mists. D. Fumes are generally obtained by the condensation of vapors during sublimation, distillation, boiling and several other chemical reactions. Generally, organic solvents, metals and metallic oxides form fume particles. The effects of particulate pollutants are largely dependent on the particle size. Airborne particles such as dust, fumes, mist etc., are dangerous for human health. Particulate pollutants bigger than 5 microns are likely to lodge in the nasal passage, whereas particles of about 10 micron enter into lungs easily. Lead used to be a major air pollutant emitted by vehicles. Leaded petrol used to be the primary source of airborne lead emission in Indian cities. This problem has now been overcome by using unleaded petrol in most of the cities in India. Lead interferes with the development and maturation of red blood cells. Smog. The word smog is derived from smoke and fog. This is the most common example of air pollution that occurs in many cities throughout the world. There are 2 types of smog. A classical smog occurs in cool humid climate. It is a mixture of smoke, fog and sulfur dioxide. Chemically it is a reducing mixture and so it is also called as reducing smog. B. Photochemical smog occurs in warm, dry and sunny climate. The main components of the photochemical smog result from the action of sunlight on unsaturated hydrocarbons and nitrogen oxides produced by automobiles and factories. Photochemical smog has high concentration of oxidizing agents and is, therefore, called as oxidizing smog. Formation of photochemical smog when fossil fuels are burnt. A variety of pollutants are emitted into the earth. This plan aims at clearing the air in the Taj Trapezium, an area that includes the towns of Agra, Firozabad, Mathura and Bharatpur. Under this plan, more than 2,000 polluting industries lying inside the trapezium would switch over to the use of natural gas or liquefied petroleum gas instead of coal or oil. A new natural gas pipeline would bring more than 500,000 cubic meters of natural gas a day to this area. People living in the city will also be encouraged to use liquefied petroleum gas in place of coal, kerosene or firewood. Vehicles plying on highways in the vicinity of Taj would be encouraged to use low sulfur content diesel. Chemistry 412 Troposphere. Two of the pollutants that are emitted are hydrocarbons, unburnt fuels and nitric oxide NO. When these pollutants build up to sufficiently high levels, a chain reaction occurs from their interaction with sunlight in which NO is converted into nitrogen dioxide number 2. This number 2 in turn absorbs energy from sunlight and breaks up into nitric oxide and free oxygen atom Fig. 14.2. Number 2G NO-GOGI oxygen atoms are very reactive and combine with the O2 in air to produce ozone. OgO2-GO3G2. The ozone formed in the above reaction 2 reacts rapidly with the NO-G formed in the reaction I to regenerate number 2. Number 2 is a brown gas and at sufficiently high levels can contribute to haze. NO-GO3G number 2-GO2-G3. Ozone is a toxic gas and both number 2 and O3 are strong oxidizing agents and can react with the unburnt hydrocarbons in the polluted air to produce chemicals such as formaldehyde, acrolein and peroxyacetyl nitrate PAN. 3CH42O3 3CH2O3 H2O formaldehyde CH2CHCHOCH3 CuNO2 acrolein O peroxyacetyl nitrate PAN. Effects of photochemical smog. The common components of photochemical smog are ozone, nitric oxide, acrolein, formaldehyde and peroxyacetyl nitrate PAN. Photochemical smog causes serious health problems. Both ozone and PAN act as powerful eye irritants. Ozone and nitric oxide irritate the nose and throat and their high concentration causes headache, chest pain, dryness of the throat, cough and difficulty in breathing. Photochemical smog leads to cracking of rubber and extensive damage to plant life. It also causes corrosion of metals, stones, building materials, rubber and painted surfaces. Figure 14.2. Photochemical smog occurs where sunlight acts on vehicle pollutants. Environmental chemistry 413. How can photochemical smog be controlled? Many techniques are used to control or reduce the formation of photochemical smog. If we control the primary precursors of photochemical smog, such as number 2 and hydrocarbons, the secondary precursors such as ozone and PAN, the photochemical smog will automatically be reduced. Usually catalytic converters are used in the automobiles, which prevent the release of nitrogen oxide and hydrocarbons to the atmosphere. Certain plants e.g., pinus, juniperus, quercus, pyrus and vitis can metabolize nitrogen oxide and therefore, their plantation could help in this matter. 1.4.2. Stratospheric pollution. Formation and breakdown of ozone. The upper stratosphere consists of considerable amount of ozone O3, which protects us from the harmful ultraviolet UV radiations. Greek letter lambda 255 nm coming from the sun. These radiations cause skin cancer, melanoma in humans. Therefore, it is important to maintain the ozone shield. Ozone in the stratosphere is a product of UV radiations acting on dioxygen O2 molecules. The UV radiations split apart molecular oxygen into free oxygen O atoms. These oxygen atoms combine with the molecular oxygen to form ozone. O2GOGOGO2GO3G. Ozone is thermodynamically unstable and decomposes to molecular oxygen. Thus, a dynamic equilibrium exists between the production and decomposition of ozone molecules. In recent years, there have been reports of the depletion of this protective ozone layer because of the presence of certain chemicals in the stratosphere. The main reason of ozone layer depletion is believed to be the release of chlorofluorocarbon compounds CFCs, also known as freons. These compounds are non-reactive, non-flammable, non-toxic organic molecules and therefore used in refrigerators, air conditioners, in the production of plastic foam and by the electronic industry for cleaning computer parts, etc. Once CFCs are released in the atmosphere, they mix with the normal atmospheric gases and eventually reach the stratosphere. In stratosphere, they get broken down by powerful UV radiations, releasing chlorine-free radical CF2Cl2GC, LGC, F2ClGI. The chlorine radical then react with stratospheric ozone to form chlorine monoxide radicals and molecular oxygen. C. LgO3G Clo. GO2G2 reaction of chlorine monoxide radical with atomic oxygen produces more chlorine radicals. Clo. GOGC. LgO2G3. The chlorine radicals are continuously regenerated and cause the breakdown of ozone. Thus, CFCs are transporting agents for continuously generating chlorine radicals into the stratosphere and damaging the ozone layer. The ozone hole. In 1980s, atmospheric scientists working in Antarctica reported about depletion of ozone layer commonly known as ozone hole over the South Pole. It was found that a unique set of conditions was responsible for the ozone hole. In summer season, nitrogen dioxide and methane react with chlorine monoxide reaction I and chlorine atoms reaction V forming chlorine sinks, preventing much ozone depletion, whereas in winter, special type of clouds called polar stratospheric clouds are formed over Antarctica. These polar stratospheric clouds provide surface on which chlorine nitrate formed reaction I gets hydrolyzed to form hypochlorous acid reaction V. It also reacts with hydrogen chloride produced as per reaction V to give molecular chlorine, Clo, G number 2G clono 2G5C, LgCH4GC, H3GHClGV clono 2GH2OG HOClGHNO3GV clono 2GHClGCl2GHNO3G7. Chemistry 414. When sunlight returns to the Antarctica in the spring, the sun's warmth breaks up the clouds and HOCl and Cl2 are photolyzed by sunlight, as given in reactions 8 and 9. HOClGO, HGC, LgHCl2G2C, Lg9. The chlorine radicals thus formed initiate the chain reaction for ozone depletion as described earlier. Effects of depletion of the ozone layer. With the depletion of ozone layer, more UV radiation filters into troposphere. UV radiations led to aging of skin, cataract, sunburn, skin cancer, killing of many phytoplanktons, damage to fish productivity, etc. It has also been reported that plant proteins get easily affected by UV radiations, which leads to the harmful mutation of cells. It also increases evaporation of surface water through the stomata of the leaves and decreases the moisture content of the soil. Increasing UV radiations damage paints and fibers, causing them to fade faster. 14.3 Water pollution. Water is essential for life. Without water there would be no life. We usually take water as granted for its purity, but we must ensure the quality of water. Pollution of water originates from human activities. Through different paths, pollution reaches surface or groundwater. Easily identified source or place of pollution is called as point source, e.g., municipal and industrial discharge pipes where pollutants enter the water source. Non-point sources of pollution are those where a source of pollution cannot be easily identified, e.g., agricultural runoff from farm, animals and croplands, acid rain, stormwater drainage from streets, parking lots and lawns, etc. Table 14.1 lists the major water pollutants and their sources. 1, 4, 3. 1. Causes of water pollution. I. Pathogens. The most serious water pollutants are the disease-causing agents called pathogens. Pathogens include bacteria and other organisms that enter water from domestic sewage and animal excreta. Human excreta contain bacteria such as Escherichia coli and Streptococcus faecalis, which cause gastrointestinal diseases. 2. Organic wastes. The other major water pollutant is organic matter such as leaves, grass, trash, etc. They pollute water as a consequence of runoff. Excessive phytoplankton growth within water is also a cause of water pollution. These wastes are biodegradable. The large population of bacteria decomposes organic matter present in water. They consume oxygen dissolved in water. The amount of oxygen that water can hold in the solution is limited. In cold water, dissolved oxygen can reach a concentration up to 10 ppm parts per million, whereas oxygen in air is about 200,000 ppm. That is why even a moderate amount of organic matter when decomposes in water can deplete the water of its dissolved oxygen. The concentration of Table 14.1 Major water pollutants. Pollutant source: microorganisms, domestic sewage, organic waste, domestic sewage, animal excreta and waste, decaying animals and plants, discharge from food processing factories, plant nutrients, chemical fertilizers, toxic heavy metals industries and chemical factories, sediments, erosion of soil by agriculture and strip mining, pesticides, chemicals used for killing insects, fungi and weeds, radioactive substances, mining of uranium-containing minerals, heat water used for cooling in industries. Environmental chemistry. 415 Dissolved oxygen in water is very important for aquatic life. If the concentration of dissolved oxygen of water is below 6 ppm, the growth of fish gets inhibited. Oxygen reaches water either through atmosphere or from the process of photosynthesis carried out by many aquatic green plants during daylight. However, during night, photosynthesis stops but the plants continue to respire, resulting in reduction of dissolved oxygen. The dissolved oxygen is also used by microorganisms to oxidize organic matter. If too much of organic matter is added to water, all the available oxygen is used up. This causes oxygen-dependent aquatic life to die. Thus, anaerobic bacteria which do not require oxygen begin to break down the organic waste and produce chemicals that have a foul smell and are harmful to human health. Aerobic oxygen-requiring bacteria degrade these organic wastes and keep the water depleted in dissolved oxygen. Thus, the amount of oxygen required by bacteria to break down the organic matter present in a certain volume of a sample of water is called biochemical oxygen demand BOD. The amount of BOD in the water is a measure of the amount of organic material in the water, in terms of how much oxygen will be required to break it down biologically. Clean water would have BOD value of less than 5 ppm, whereas highly polluted water could have a BOD value of 17 ppm or more. 3. Chemical pollutants. As we know that water is an excellent solvent, water-soluble inorganic chemicals that include heavy metals such as cadmium, mercury, nickel etc. constitute an important class of pollutants. All these metals are dangerous to humans because our body cannot excrete them. Over the time, it crosses the tolerance limit. These metals then can damage kidneys, central nervous system, liver etc. Acids like sulfuric acid from mine drainage and salts from many different sources including raw salt used to melt snow and ice in the colder climates, sodium and calcium chloride are water-soluble chemical pollutants. The organic chemicals are another group of substances that are found in polluted water. Petroleum products pollute many sources of water, e.g., major oil spills in oceans. Other organic substances with serious impacts are the pesticides that drift down from sprays or runoff from lands. Various industrial chemicals like polychlorinated biphenyls, PCBs which are used as cleansing solvent, detergents and fertilizers add to the list of water pollutants. PCBs are suspected to be carcinogenic. Nowadays most of the detergents available are biodegradable. However, their use can create other problems. The bacteria responsible for degrading biodegradable detergent feed on it and grow rapidly. While growing, they may use up all the oxygen dissolved in water. The lack of oxygen kills all other forms of aquatic life such as fish and plants. Fertilizers contain phosphates as additives. The addition of phosphates in water enhances algae growth. Such profuse growth of algae covers the water surface and reduces the oxygen concentration in water. This leads to anaerobic conditions, commonly with accumulation of obnoxious decay and animal death. Thus, bloom-infested water inhibits the growth of other living organisms in the water body. This process, in which nutrient-enriched water bodies support a dense plant population, which kills animal life by depriving it of oxygen and results in subsequent loss of biodiversity, is known as eutrophication. 1.4.3. 2 International Standards for Drinking Water. The international standards for drinking water are given below and they must be followed. Fluoride. For drinking purposes, water should be tested for fluoride ion concentration. Its deficiency in drinking water is harmful to man and causes diseases such as tooth decay etc. Soluble fluoride is often added to drinking water to bring its concentration up to 1 ppm or 1 mg DM-3. The F ions make the enamel on teeth much harder by converting hydroxyapatite, 3Ca3PO42 CrO2, the enamel on the surface of the teeth, into much harder fluorapatite, 3Ca3PO42 CaF2. Chemistry 416. However, F-ion concentration above 2 ppm causes brown mottling of teeth. At the same time, excess fluoride over 10 ppm causes harmful effect to bones and teeth, as reported from some parts of Rajasthan. Lead. Drinking water gets contaminated with lead when lead pipes are used for transportation of water. The prescribed upper limit concentration of lead in drinking water is about 50 ppb. Lead can damage kidney, liver, reproductive system etc. Sulfate. Excessive sulfate, 500 ppm in drinking water causes laxative effect, otherwise at moderate levels it is harmless. Nitrate. The maximum limit of nitrate in drinking water is 50 ppm. Excess nitrate in drinking water can cause disease such as methemoglobinemia, blue baby syndrome. Other metals. The maximum concentration of some common metals recommended in drinking water are given in Table 14.2. Pollution levels. Ensure that appropriate action is taken. You can write to the press also. Do not dump waste into a household or industrial drain which can enter directly to any water body, such as river, pond, stream or lake. Use compost instead of chemical fertilizers in gardens. Avoid the use of pesticides like DDT, malathion etc. at home and try to use dried neem leaves to help keep insects away. Add a few crystals of potassium permanganate KMNO4 or bleaching powder to the water tank of your house. 14.4 Soil pollution. India, being an agriculture-based economy, gives high priority to agriculture, fisheries and livestock development. The surplus production is stored by governmental and non-governmental organizations for the lean season. The food loss during the storage also needs special attention. Have you ever seen the damages caused to the crops? Food items by insects, rodents, weeds and crop diseases etc. How can we protect them? You are acquainted with some insecticides and pesticides for protection of our crops. However, these insecticides, pesticides and herbicides cause soil pollution, hence, there is a need for their judicious use. 1 Pesticides. Prior to World War II, many naturally occurring chemicals such as nicotine by planting tobacco plants in the crop field, were used as pest controlling substance for major crops and agricultural practices. During World War II, DDT was found to be of great use in the control of malaria and other insect-borne diseases. Therefore, after the war, DDT was put to use in agriculture to control the damages caused by insects, rodents, weeds and various crop diseases. However, due to adverse effects, its use has been banned in India. Pesticides are basically synthetic toxic chemicals with ecological repercussions. The repeated use of the same or similar pesticides give rise to pests that are resistant to that metal maximum concentration ppm or mgdm-3 Fe 0.2 mn 0.05 Al 0.2 Cu 3.0 Zn 5.0 Ct 0.005 Table 14.2 Maximum prescribed concentration of some metals in drinking water. Activity 2. You can visit local water sources and observe if the river, lake, tank, pond are unpolluted, slightly polluted, moderately polluted or severely polluted by looking at water or by checking pH of water. Document the name of the river and the nearby urban or industrial site from where the pollution is generated. Inform about this to Pollution Control Board's office set up by government to measure. Environmental Chemistry 417 Group of pesticides, thus making the pesticides ineffective. Therefore, as insect resistance of DDT increased, other organic toxins such as aldrin and dieldrin were introduced in the market by pesticide industry. Most of the organic toxins are water-insoluble and non-biodegradable. These high-persistent toxins are, therefore, transferred from lower trophic level to higher trophic level through food chain figure 14.3. Over the time, the concentration of toxins in higher animals reach a level which causes serious metabolic and physiological disorders. Figure 14.3. At each trophic level, the pollutant gets 10 times concentrated sodium chlorate NaClO3, sodium arsenite natriosO3 and many others. During the first half of the last century, the shift from mechanical to chemical weed control had provided the industry with flourishing economic market. But one must remember that these are also not environment friendly. Most herbicides are toxic to mammals but are not as persistent as organochlorides. These chemicals decompose in a few months. Like organochlorides, these too become concentrated in the food web. Some herbicides cause birth defects. Studies show that cornfields sprayed with herbicides are more prone to insect attack and plant disease than fields that are weeded manually. Pesticides and herbicides represent only a very small portion of widespread chemical pollution. A large number of other compounds that are used regularly in chemical and industrial processes for manufacturing activities are finally released in the atmosphere in one or other form. 14.5 Industrial waste. Industrial solid wastes are also sorted out as biodegradable and non-degradable wastes. Biodegradable wastes are generated by cotton mills, food processing units, paper mills, and textile factories. Non-biodegradable wastes are generated by thermal power plants which produce fly ash, integrated iron and steel plants which produce blast furnace slag and steel melting slag. Industries manufacturing aluminium, zinc and copper produce mud and tailings. Fertilizer industries produce gypsum. Hazardous wastes such as inflammables, composite explosives or highly reactive substances are produced by industries dealing in metals, chemicals, drugs, pharmaceuticals, dyes, pesticides, rubber goods etc. The disposal of non-degradable industrial solid wastes, if not done by a proper and suitable method, may cause serious threat to the environment. New innovations have led to different uses of waste material. Nowadays, fly ash and slag from the steel industry are utilized by the cement industry. Large in response to high persistence of chlorinated organic toxins, a new series of less persistent or more biodegradable products called organophosphates and carbamates have been introduced in the market. But these chemicals are severe nerve toxins and hence more harmful to humans. As a result, there are reports of some pesticides-related deaths of agricultural field workers. Insects have become resistant to these insecticides also. The insecticide industry is engaged in developing new groups of insecticides. But one has to think, is this the only solution to pest menace these days? The pesticide industry has shifted its attention to herbicides such as Chemistry 418. Quantities of toxic wastes are usually destroyed by controlled incineration, whereas small quantities are burnt along with factory garbage in open bins. Moreover, solid wastes, if not managed effectively, affect the components of the environment. Household discards. There are medical, agricultural, industrial and mining wastes. The improper disposal of wastes is one of the major causes of environmental degradation. Therefore, the management of wastes is of utmost importance. You must be aware of the Swachh Bharat Abhiyan or Clean India mission launched by the Government of India. Do you know about waste recycling? Fuel obtained from plastic waste has high octane rating. It contains no lead and is known as green fuel. Due to recent developments made in chemical and textile industries, clothes will be made from recycled plastic waste. These will be available soon in the global textile market. In India, our cities and towns face endless hours of power cut. We can also see piles of rotting garbage here and there. There is a good news that we can get rid from both these problems simultaneously. Technology has now been developed to produce electricity from the garbage. A pilot plant has been set up, where after removing ferrous metals, plastic, glass, paper etc. from garbage, it is mixed with water. It is then cultured with bacterial species for producing methane, commonly known as biogas. The remaining product is used as manure and biogas is used to produce electricity. 14.6 Strategies to control environmental pollution. After studying air, water, soil and industrial waste pollution in this unit, by now you must have started feeling the need of controlling environmental pollution. How can you save your immediate environment? Think of the steps activities which you would like to undertake for controlling air, water, soil and industrial waste pollution in your neighborhood. Here, an idea about the strategies for the management of waste is given. 1.4.6. 1. Waste management. Solid waste is not the only waste, which you see in your household garbage box. Besides, 2 programs are being implemented under the broad umbrella of the Swachh Bharat Abhiyan. These are Swachh Bharat Mission Urban SBMU and Swachh Bharat Mission Gramin SBMG. The SBMU primarily aims at making urban India free from open defecation and achieving 100 scientific management of solid waste in the country. The SBMG targets to bring about an improvement in the general quality of life in rural areas by promoting cleanliness and hygiene, and eliminating open defecation. It is accelerating its efforts to achieve a goal of universal sanitation coverage by October 2, 2019, which is the birth anniversary of Mahatma Gandhi. If you have participated in some event on Swachh Bharat Mission, write your experiences. Collection and disposal. Domestic wastes are collected in small bins, which are then transferred to community bins by private or municipal workers. From these community bins, these are collected and carried to the disposable site. At the site, garbage is sorted out and separated into biodegradable and non-biodegradable materials. Non-biodegradable materials such as plastic, glass, metal scraps etc. are sent for recycling. Biodegradable wastes are deposited in landfills and are converted into compost. The waste, if not collected in garbage bins, finds its way into the sewers. Some of it is eaten by cattle. Non-biodegradable wastes like environmental chemistry. 419 Polythene bag, metal scraps, etc. choke the sewers and cause inconvenience. Polythene bags, if swallowed by animals, can cost their lives also, as a normal practice. Therefore, all domestic wastes should be properly collected and disposed. The poor management causes health problems leading to epidemics due to contamination of groundwater. It is especially hazardous for those who are in direct contact with the waste, such as rag pickers and workers involved in waste disposal, as they are the ones who handle waste materials mostly without protective device such as gloves or waterproof boots and gas masks. What can you do for them? 14.7 Green Chemistry. 1.4.7. 1. Introduction. It is well-known fact that self-sufficiency in food has been achieved in India since late 20th century by using fertilizers and pesticides and exploring improved methods of farming, good quality seeds, irrigation etc. But overexploitation of soil and excessive use of fertilizers and pesticides have resulted in the deterioration of soil, water and air. The solution of this problem does not lie in stopping the process of development that has been set in, but to discover methods which would help in the reduction of deterioration of the environment. Green chemistry is a way of thinking and is about utilizing the existing knowledge and principles of chemistry and other sciences to reduce the adverse impact on environment. Green chemistry is a production process that would bring about minimum pollution or deterioration to the environment. The byproducts generated during a process, if not used gainfully, add to the environmental pollution. Such processes are not only environmental unfriendly but also cost ineffective. The waste generation and its disposal both are economically unsound. Utilization of existing knowledge base for reducing the chemical Nobel goes to green chemists of Chauvin. Institut Français du Pétrole, Rueil-Malmaison, France. Robert H. Grubbs, California Institute of Technology, Caltech. Pasadena, CA, USA, and Richard R. Schrock, Massachusetts Institute of Technology, MIT, Cambridge, MA, USA, won the 2005 Nobel Prize in Chemistry for work that reduces hazardous waste in creating new chemicals. The trio won the award for their development of the metathesis method in organic synthesis, a way to rearrange groups of atoms within molecules that the Royal Swedish Academy of Sciences likened to a dance in which couples change partners. The metathesis has tremendous commercial potential in the pharmaceuticals, biotechnology and foodstuffs production industries. It is also used in the development of revolutionary environmentally friendlier polymers. This represents a great step forward for green chemistry, reducing potentially hazardous waste through smarter production. Metathesis is an example of how important application of basic science is for the benefit of man, society and the environment. Yves Chauvin, Robert H. Grubbs, Richard R. Schrock. Chemistry 420 Hazards along with the developmental activities is the foundation of green chemistry. Have you perceived the idea of green chemistry? It is well known that organic solvents such as benzene, toluene, carbon tetrachloride etc. are highly toxic. One should be careful while using them. As you know, a chemical reaction involves reactants, attacking reagents and the medium in which the reaction takes place. Extent of any reaction depends upon physical parameters like temperature, pressure and use of catalyst. In a chemical reaction, if reactants are fully converted into useful environmental-friendly products by using an environment-friendly medium, then there would be no chemical pollutants introduced in the environment. During a synthesis, care must be taken to choose starting materials that can be converted into end products with yield approximately up to 100%. This can be achieved by arriving at optimum conditions of synthesis. It may be worthwhile to carry out synthetic reactions in aqueous medium since water has high specific heat and low volatility. Water is cost-effective, non-inflammable and devoid of any carcinogenic effects. 1.4.7.2 Green chemistry in day-to-day life. Dry cleaning of clothes. Tetrachloroethene Cl2 was earlier used as solvent for dry cleaning. The compound contaminates the groundwater and is also a suspected carcinogen. The process using this compound is now being replaced by a process where liquefied carbon dioxide, with a suitable detergent, is used. Replacement of halogenated solvent by liquid CO2 will result in less harm to groundwater. These days hydrogen peroxide H2O2 is used for the purpose of bleaching clothes in the process of laundry, which gives better results and makes use of lesser amount of water. 2. Bleaching of paper. Chlorine gas was used earlier for bleaching paper. These days, hydrogen peroxide H2O2. Think it over. What is our responsibility as a human being to protect our environment? Some concepts, if followed by an individual, contribute towards a better quality of our environment and human life. Always set up a compost tin in your garden or any other place in your home and use it to produce manure for your plants to reduce the use of fertilizers. Use a cloth bag and avoid asking for plastic carry bags when you buy groceries, vegetables or any other item. See that all newspapers, glass, aluminum and other items in your area are recycled. We might have to take little trouble to locate such dealers. We must realize that we do not have solutions for every problem, but we can concentrate on issues which we feel strongly about and can do something about. We should take care to put into practice whatever we preach. Always remember, environment protection begins with us. With suitable catalyst, which promotes the bleaching action of hydrogen peroxide, is used 3 synthesis of chemicals. Ethanol CH3CHO is now commercially prepared by one-step oxidation of ethene in the presence of ionic catalyst in aqueous medium with a yield of 90. Catalyst 2,2,2-PD2Cu2 and water 3CHCHO 90 green solution to clean turbid water. Powder of kernel of tamarind seeds has been found to be an effective material to make municipal and industrial wastewater clean. It is not toxic, biodegradable and cost-effective material. This powder is usually discarded as agricultural waste. The present practice is to use alum to treat such water. It has been found that alum increases toxic ions in treated water and can cause diseases. Green chemistry, in a nutshell, is a cost-effective approach which involves reduction in material, energy consumption and waste generation. Summary: environmental chemistry plays a major role in environment. Chemical species present in the environment are either naturally occurring or generated by human activities. Environmental pollution is the effect of undesirable changes in the surrounding that have harmful effects on plants, animals and human beings. Pollutants exist in all the 3 states of matter. We have discussed only those pollutants which are due to human activities and can be controlled. Atmospheric pollution is generally studied as tropospheric and stratospheric pollution. Troposphere is the lowest region of the atmosphere 10 kilometers in which man along with other organisms including plants exist. Whereas stratosphere extends above troposphere up to 50 kilometers above sea level. Ozone layer is one of the important constituents of stratosphere. Tropospheric pollution is basically due to various oxides of sulfur, nitrogen, carbon, halogens and also due to particulate pollutants. The gaseous pollutants come down to the Earth in the form of acid rain. 75 of the solar energy reaching Earth is absorbed by the Earth's surface and rest is radiated back to the atmosphere. These gases mentioned above trap the heat which result into global warming. It is important to realize that these very gases are also responsible for the life on the Earth as they trap the requisite amount of solar energy for the sustenance of life. The increase in the greenhouse gases is raising the temperature of the Earth's atmosphere which, if not checked, may eventually result in melting of polar ice caps and consequently may submerge the coastal landmass. Many human activities are producing chemicals, which are responsible for the depletion of ozone layer in the stratosphere, leading to the formation of ozone hole. Through the ozone hole, ultraviolet radiations can penetrate into the Earth's atmosphere causing mutation of genes. Water is the elixir of life, but the same water, if polluted by pathogens, organic wastes, toxic heavy metals, pesticides etc., will turn into poison. Therefore, one should take care to follow international standards to maintain purity levels of drinking water. Industrial wastes and excessive use of pesticides result into pollution of land mass and water bodies. Judicious use of chemicals required for agricultural practices can lead to sustainable development. Strategies for controlling environmental pollution can be waste management, that is, reduction of the waste and proper disposal, also recycling of materials and energy, to adopting methods in day-to-day life, which results in the reduction of environmental pollution. The second method is a new branch of chemistry, which is in its infancy known as green chemistry. It utilizes the existing knowledge and practices so as to bring about reduction in the production of pollutants. Exercises 14.1 Define environmental chemistry. 14.2 Explain tropospheric pollution in 100 words. 14.3 Carbon monoxide gas is more dangerous than carbon dioxide gas. Why? 14.4 List gases which are responsible for greenhouse effect. 14.5 Statues and monuments in India are affected by acid rain. How? 14.6 What is smog? How is classical smog different from photochemical?